Hi everyone, and welcome to this course on deep learning for computer vision by neurallearn.ai. In this course, we shall make use of tools like Huggingface, TensorFlow, ONNX, and 1DB to build and deploy our different computer vision solutions. Applications of computer vision are everywhere today, going from Tesla self-driving cars to livestock farmers who can now automatically count the number of animals they have, to mobile facial recognition apps, and even in the hospitals where the gastroenterologists could make use of computer vision for much faster diagnostics. Behind these different computer vision solutions is deep learning models like the convolutional neural networks and the vision transformer. Throughout this course, we shall explain in detail how the ConvNet or the vision transformers work. Given that these are all deep learning based models, let's look at a high level how deep learning works. Let's suppose we want to build a system where we get an input like this one and we are able to say that this is a damaged car, or get an input like this one and we say that this car is still intact. Then in that case, we could build and train a deep learning model which takes in this image, for example, and then for its output here, we'll be able to say that this car is damaged. Or in the case where this model takes in this other image, then we'll be able to say that this car is intact. Nonetheless, for this our deep learning model to be intelligent enough to make these kinds of decisions, we need to train it. And the way this training is carried out is we have thousands, hundreds of thousands, or even millions of damaged cars like this, and so our output level is obviously damaged. On the other hand, we have thousands of cars which are still intact and the output level is intact. And so now we have what we'll call our data set, that is these inputs and their corresponding levels. And then in this deep learning model right here, we stack several neural network layers. So we'll have this, we have some other layer, right up to the outputs. Now it should be noted that these neural network layers here are essentially mathematical functions. If you do not have a background in mathematics, you shouldn't be worried, as in this course we shall focus on implementing all this practically. So that said, as we were saying, this we have here, or these layers, these neural network layers we have here, are essentially mathematical functions. And if we have a linear layer, then this means that we could take an input x, multiply this by a weight which we'll call w, and then add some bias which we'll call b, and then this gives us the output, which is that output of a given layer. So here, for example, let's suppose this input is x. We have x here. We'll take x, multiply it by the weight, and then add up the bias to have the output at this level y. Let's call this x1, then this is y1. And then this y1 will be used as input to this next layer, and then we'll have y2 right up to, say, yn. And so during the training process, given that we know the input and the output, our aim will be to obtain the values of this w and this b, which ensure that when we pass in images like this or this, the model is able to know whether it's a damaged or an intact car. Now we see that at every layer we have our weights and biases, which are all going to be updated during the training process, making use obviously of our training data, that is these inputs and the corresponding levels, such that when shown an image which this model has never seen, our deep learning model is able to take the right decision. So in essence, these kinds of models are called deep learning models because we have several layers stacked between the inputs and the outputs. And the number of layers we stack represent the depth of our model. On the other hand, deep learning algorithms fall under a category of artificial intelligence algorithms known as machine learning, where the model learns from the training data. Let's now take a look at what we'll be learning in this course. The way we've designed this course is such that we'll start from the very basics. So we'll suppose that you have no prior experience in deep learning. And so we'll start with basic topics in TensorFlow like the tensors and the variables. And from here, we'll dive into solving our first practical problem, which is that of car price prediction. Now, it should be noted that although this isn't necessarily a computer vision problem, this will permit us learn how to prepare our data with TensorFlow, build simple models like the linear regression model, train these models, evaluate them, and test out this model, such that by the time we move into our next project, which happens to be now a computer vision based project, which is that of malaria diagnosis, we already have what it takes to start building more complex models like the convolutional neural network. But before building them, we'll first of all understand how and why they work. By the end of the section, we should have learned how to build a simple solution for our malaria diagnosis problem. And so now we're ready to dive into building more advanced models with TensorFlow. After looking at these more advanced models, we'll then dive into evaluating classification models. So we'll look at different metrics like the precision, recall, accuracy, and then we'll learn how to come up with the confusion metrics and the ROC plots. Once we're done with this, we'll dive into model performance. Here, we shall look at TensorFlow callbacks, learning rate schedulers, model checkpointing, and then how to solve the problems of overfitting and underfitting. That said, one main way in which we could mitigate the problem of overfitting is by using data augmentation. And so we have the section reserved for data augmentation using TensorFlow and albumentations. Now, once we're done with data augmentation, we'll look at more advanced concepts in TensorFlow like custom losses and metrics, the eager and graph modes, then custom training loops. So we'll learn how to train our model without necessarily using the fit method. We'll look at TensorBoard integration, where we'll learn how to carry out data logging, viewing model graphs, hyperparameter tuning, then profiling and visualizations. We shall move to our next project, which is that of human emotions detection. Again here, we shall prepare our data set, build our model, carry out data augmentation, and then we shall look at TensorFlow records. Now, once we're done with this section, we shall go ahead to look at modern convolutional neural networks like the AlexNets, VGGNets, ResNets, MobileNets, and the efficient net. With all this in place, we'll learn about transfer learning, which should help us now train our models much more efficiently using already pre-trained convolutional neural networks. Then we'll look at how the convolutional neural networks take decisions by visualizing intermediate layers. And so up to this point so far, we've been looking at the convolutional neural networks, and now we'll be set to dive into the vision transformers. We'll understand how they work and even get to fine-tune our own vision transformer using the Huggingface Transformers library. And so now that we have a working solution, the next logical step will be to deploy this such that anyone around the world could make use of our model which we've just built. Now that we've learned how to deploy our computer vision models to the cloud, we could dive into other computer vision problems like object detection. And in this section, we'll look at the basics of object detection and also build and train our own object detection YOLO model from scratch with TensorFlow. Then finally, we'll dive into the domain of image generation, where we'll look at the variational autoencoders and the generative adversarial neural networks, which we shall use for digit generation and face generation. In this course, the coding platform we'll use to build and train our models will be Google Colab. We shall make use of Google's free GPUs to train our models. We've just explained that in order to train a model like this one, we make use of a training data set which has its inputs and its corresponding outputs. These inputs and outputs are multi-dimensional arrays which are commonly known as tensors. In this section, we shall start with tensor basics. Then we'll move on to casting in TensorFlow. We'll look at initialization, indexing, broadcasting, algebraic operations, matrix operations, commonly used functions in machine learning. We'll look at the different types of tensors like the ranked tensors, sparse tensors, and even the string tensors. In the context of deep learning, tensors can be defined as multi-dimensional arrays. An array itself is an ordered arrangement of numbers. It's important we take note of these keywords, as the data we shall be dealing with, like for example this image right here, can be represented using these numbers which have been arranged clearly in an ordered manner and can be represented in multiple dimensions. In the specific case, we have this array which is represented in 2 dimensions. So this is a 2D or 2-dimensional array, or what we generally call a matrix. Now we'll explore different types of arrays based on their dimensionality. So here, for example, we have what we'll call a 0-dimensional array, which is simply because this array or this tensor contains a single element. So let's say we have 21. This is a 0-dimensional array. Let's say we will have 1. This is 0-dimensional, so on and so forth. So essentially, once we have a single element, then it's a 0D array. And then now for our next example, we'll have this 1D tensor right here, which in fact is a combination of several 0D tensors. So if you look at this, you see that this is a 0D tensor, this is another 0D tensor, this is another 0D tensor. So this vector is made of 3 of these kinds of elements. Now we could have other examples like this. Let's say we have 5, 8, and then 3. Or let's change the length. So let's say we have one of length 5, for example. We could have 10, 2, 11, 4, and 7. So this is a 1D tensor we have right here. So far we've looked at the 0D tensor, we've looked at the 1D tensor, and now we could dive into the 2D tensor, which essentially is made of a combination of several 1D tensors. You could see that right here. This is a 1D tensor. Here, this is another 1D tensor. This is another 1D tensor. And finally, here we have a 1D tensor. So when you bring together these 1D tensors, you form this 2D tensor. For a 3-dimensional tensor, you might have guessed this right. You would simply combine several 2-dimensional tensors. So right here, we have this 2D tensor with this other 2D, with this other 2D, and this other 2D, forming a 3D tensor. We could visualize this differently here. So we take this, 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 and this. Now you see we have 1, 2, and the 3rd dimension. Now that we understand this, we're going to take a look at the concept of tensor shapes. Starting with this, given that it's 0-dimensional, then there is no shape. With this one here, it's 1-dimensional, and it's made of 3 elements. And so we could say this is of shape 3. So we have 3 and that's it. Now for this other one, it's made of 1, 2, 3, and 4 1D tensors. And each and every one of this is made of 3 elements. So this here, for example, is made of 3 elements. This made of 3, this 3, this 3. And given that there are 4 of this made of 3 elements, its shape is 4 by 3. So that's it. That's how we obtain the shape for this. Now for the 3D tensor we have here, it's made of 1, 2, 3, 4 2D tensors. So this here we have 4 2D tensors, and each and every one of this is made of 2 1D tensors, where each and every one is made of 3 elements. So what we'll see here is this is 2 by 3. This here, because we have 1 2, is 2 by 3. This is 2 by 3, and this here is 2 by 3. And now given that we have 4 of this different 2 by 3 2D tensors, then we would say the shape of this 3D tensor is 4 by 2 by 3. So similar to this, we have 4 by 3. This is 4 by 2 by 3. Now notice that the number of elements we have here tells us or gives us information about the number of dimensions our tensor is. So here, because we have a 1D tensor or one-dimensional tensor, we have just 1. Here, because it's 2D or two-dimensional, we have 2. And here, because it's 3D, we have 3. Also, in matrix notation, we would say that this here, or this matrix right here, is made of 1, 2, 3, and 4 rows. So number of rows we have here is 4. And then here we have 1, 2, 3 columns. Number of columns is 3. In the case of this 3D tensor we have right here, we have 1, 2 rows and 1, 2, 3 columns for each and every one of this 2D tensor we have right here. Now we have some basic knowledge on tensors. Let's go ahead and create them with TensorFlow. So first things first, we would import TensorFlow as TF. And then you should note that because we're using Colab, we do not need to install TensorFlow before making use of it. All we need to do here is just import and we're good to go. Now, first thing we're going to do is we're going to have our tensor, which we'll call tensor 0D. And the way we're going to create this tensor is by calling on the constant method. So we have TensorFlow's constant method, and then we specify, for example, that we want this to be, let's say, 4. So that's it. That's how we create a 0-dimensional tensor. You could see here from the documentation that this constant method takes in a value, takes in a data type, takes in a shape, and a name. But for now, we pass in only this value right here, and then we could go ahead and print this. So let's have tensor 0D, run that. You could see right here, we've had this tensor, which has value 4. It has no shape, and it's of type int32. With this, we could go ahead and build out our tensor 1D. Tensor 1D, we have, as usual, our constant method. But this time around, because it's 1D, we're going to have a list. We're going to take this list we had here, 2, 0, -3. And then put in this now right here, we have 2, 0, and -3. Now let's print this out. We have tensor 1D, and there we go. You see, we have the value, which is this 1D or this list. We could see shape right here, and then the data type. Now let's modify this and say we have 8 and let's say 90. Let's run this now and check out its shape. You see here, this is our new list, or this is our new tensor, and then you see now it's 5 because we have 5 elements in here. But again, this is still an integer, so let's add this here, change this to a float, and then see what we have. See here, now this is a float, so it's still our inputs, but this time around floats. Same shape, but the data type changes from int to float. Let's get back to integer, and then we move now to the 2D tensor. So we've looked at 0D, 1D to create a 2D tensor. It's going to be quite as simple as we've done with the 0D and 1D. So here we have 2D, and then we have, as usual, our constant, and then let's open up this square brackets. So we have the square brackets right here opened up, and then we would have this 2D tensor we had seen already. So let's have this right here. We have 1, 2, 0. We put a comma to move to the next row or to the next line. We have 3, 5, minus 1. Then we have 1, 5, 6. And then we have 2, 3, 8. Okay, so as you could see here, we have this 1D tensors which we stack and which will form our 2D tensor. Now, as usual, we have our constant method which takes in this value. And you should also take note of the fact that we have this outside of this stacked 1D tensors. Now we have this. Let's go ahead and print out tensor 2D. We have tensor 2D, and there we go. As you could see, we have our 2D tensor. That's it. We have the shape 4 by 3, which is what's expected, and then the data type is int32. From here, we move on to the 3D tensor, which is essentially made of this 2D tensors which have been stacked together. So let's go ahead and see how to create this with TensorFlow. We'll start by putting together those 2D tensors. We had 1, 2, 0, 3, 5, minus 1. So that's it. 3, 5, minus 1. And then we have all those remaining 2D tensors. So let's get here. We have tensor 3D. It's a constant. We have our square bracket here, and then we simply copy this, and then paste this in here. Now let's print this out and see what we get. So here we have tensor 3D. As you could see, we're getting an error, and this comes from the fact that we omitted commas. Now if you look at this, you'll see that between 1D and another 1D to form this 2D, there is a comma. And so this means that between this 2D and this other 2D, there should be a comma. So let's have this comma here. Let's have this comma. Let's have this comma and this comma. Okay, so let's run that again and see what we get. As you could see, we have this our 3D output of shape 4 by 2 by 3, and that's exactly what we expect to get. Data type int32. Now before we move on, we should note that we could also do, let's have this here. We could also do tensor 3D shape to obtain this tensor shape. So you see that we have that right there. We could replace this 0. We could have 1. See, that's 0, that's 1, that's 2. There we go. Let's have 1. That's 1. That's it. Okay, and also we could also have here, let's say 3. We could do ndim, and this gives us a value of 3, showing us that our tensor is a 3D tensor. At this point, we've looked at 0D, 1D, 2D, and even the 3D tensor. Let's go ahead and check out a 4D tensor. But to construct a 4D tensor, we need several 3D tensors. So let's have this here. We have this 3D. Well, we saw this already. This is this 3D. And then we move to this other one right here, or these two others. We have this other 3D and this other 3D. And then now if we stack these three 3Ds up, what we'll obtain would be a 4D tensor. See, we have this one, we add this other, and we have this other. So now we have here a 4-dimensional tensor, which is made of three-dimensional tensors. Now you should know that this could be 2, this could be 4, this could be whatever number. So if we consider only this 2, then we're talking about 2 3-dimensional tensors. But what's so important to note here is the fact that once you stack several 3D tensors, you create a 4D tensor. Now at this point, you could take it as an exercise to create your own 4D tensor. So you could pause the video, but we're going to go ahead and show you how to create this. First things first, we're going to take up our 3D here. We have this 3D tensor. Let's just copy this. There we go. We paste this out here. Let's repeat that operation. Copy and paste again. But now let's modify some values. So let's say we have 13, 26. Let's just randomly modify this. 23. So it's now this other 3D is different from the other one. Say 30. Okay, now let's copy this again and then paste out here. So we have the 3D tensors. Let's say this is 10. Let's just add zeros. We have here 20, 3, 2, 4, and say 2. Okay, so now we have our 3D tensors. We have this one, we have this other one, and then we have this other one. Now to create our 4D tensor, as usual, we call on our constant method. So we have 4D, we have the constant, and as usual we have our square brackets, which will open up, and then now we just simply take this, copy all this to the end, cut this from here, and then paste this out here. Okay, so we see we have 3 of this 3D tensors. Now remember last time when you were separating 2 3D tensors, or between the 3D tensors, we need to have a comma. So here we're gonna have this comma, and then here we're gonna have this comma, and here we have a comma. Okay, so that's it. So let's run this, or let's print this out and then see what we get. So here we have print tensor 4D. There we go. You could see from here we have our 4D tensor. You see it's shape 3 by 4 by 2 by 3, and this is because our 4D tensor is made of 1. Let's take this off. It's made of 1, 2, 3 3D tensors, so that's why we have 3. And then for each and every one of this we have 4. That's 1, 2, 3, 4 2D tensors. So here we have 4, and for every 2D tensor we have 1, 2. That's 2 rows, and 1, 2, 3. That's 3 columns. And that's now exactly what we have here. So we still have the same data type. We have values which we could have here, and that's it. If we get back here, we'll see that we have different data types which we could use. So instead of just this default int, we could have tf float, say 32, and you'll notice that the outputs, as we had seen already, should have these decimals, since we're now dealing with floats. Now the float we have in here is of type float 32, or specifically the float 32, meaning that the precision value here is 32. Now if you reduce this, you'll see that you actually have the same output, but the difference is that less memory is allocated for storing this tensor as compared to maybe even, let's say, the 64, that's float 64. And so in certain contexts where we have the memory constraint, we would want to use the lower precision tensors. In the documentation, you could have all the different data types which are supported in TensorFlow. So here we have quantized data types. And talking about quantization, we're going to treat this in subsequent sections, and so don't bother for now if you don't really master this. Here we have the brain floating point. Here we have the Boolean. Here we have complex in its 128 and 64-bit versions. Here we have the double, which in fact means the double precision floating point. Now this is double because the float 32 is a single precision. So here we have single, the float 16 is half prediction or precision, and then the double is double precision. Here we have the ints and their different versions or the different precisions. We have the quantized ints, we have resource, we have string, we have unsigned int, and then we have variant. Getting back to the code, if for example here we had this float, let's just add this decimal, so we suppose that this is a float, and then now we do int, let's say int 64, we run that, you would see that we would obtain an error. So let's have this here. What do we see? We told that we cannot convert this tensor to eager tensor of the data type int 64. But now if we use the cast method, if we do TensorFlow cast, and then here, or rather, let's take this back. Let's have our TensorFlow or our Tensor 1D, and then let's take this off, or let's just have this float 64. There we go, or let's say float 32, and then let's say we define some casted tensor 1D. And then this casted tensor 1D is simply going to be the casted version of this or 1D tensor. So here we have tensor 1D, and then we specify the data type, and then we say we want this to be in 16, for example. So here we're going to print out the tensor 1D, and we're also going to print out the casted tensor 1D. We get in this error. We should have had tf dot. So let's have this here. There we go. And then let's look at what we have as output. As you could see, thanks to the casting operation, we are able to get from this float to this integer tensor. And so this tells us that instead of coming right here and saying, for example, int 16, or let's say int 32, it's preferable to make use of the cast method. That said, let's say, for example, instead of having this, instead of casting this into an integer, we want to cast this into a Boolean. So let's run this. You see here that we get all true except for this one here, which is false, and that's simply because this is a 0. So it looks like what the casting method does is, for all the values which are different from 0, they're true, but values equal 0 equal false. We could also go ahead and create our own Boolean. So let's say we have tensor bool. Let's call this tensor bool, and then we have this list made of this tensor. So we could have true, true, false, true, true, false. Okay, so let's print out tensor bool and see what we get. As you could see here, we have our output tensor of shape 3, and here is values. You can see the data type bool right here. Now another data type which we could look at is the string. So let's say we want to have tensor string. There we go. Let's say we want to have hello world. Let's print this out, tensor string. There we go. We have our tensor. We could also put this in a list because right now this is a 0-dimensional tensor. So let's put this in the list, and hello world, hi, and we'll close that. And now we have this 1D tensor of shape 2, which is a string. From here, we would also look at how to create or how to convert a NumPy array into a tensor. So let's call this NP array. First of all, we'll start by importing numpy as NP. We could just do that right here. Import numpy as NP. There we go. And then we have NP array. And let's say we have NP array, and then let's take in this here. Let's say 1, 2, 3 or 1, 2, 4. There we go. Print this out. We have NP array right here. Now we could make use of this TensorFlow convert to tensor method. So let's say we have your converted tensor, and we have convert to tensor, which essentially takes in our numpy array. Now let's have this and then print out the converted tensor. With that, getting back to the documentation, we could look at a couple of other methods, like the I method. Here we have this I method right here. As usual, we have the well described method in the documentation, which comes with this short phrase explaining how it works. It comes with this different arguments and also even some examples. So getting back here, we told that this I method permits us construct an identity matrix or a batch of matrices. So now we have this definition. We could simply copy this out and then get back to the code right here, paste this out, and let's say we call this I tensor, and for now we have this number of columns which is known, the batch shape known, data type float 32, name known. Now let's say we want to have 3 rows. So we have number of rows which is equal 3. Now in this case, we'll print this out so we see the kind of output we get. Here we have I tensor, and there we go. As you could see, we have this identity matrix where all the values of the matrix are 0 except for those of the leading diagonal. Let's show clearly this leading diagonal right here. Here we have our matrix, which is this, and then we have this element of the leading diagonal which is equal 1. Now you should note that you could say, for example, let's say 3 times this, and you should have all the elements of the leading diagonal to be equal 3 and the others 0. So in this case, we now have something like this. So you see all this 3 while the rest 0. Now let's get back. Let's take this off. Here we have our I tensor, and then we see that we could specify the number of columns. Now here, or previously where this was set to none, we had a square matrix. That is, when you define the number of rows to be 3, the number of columns automatically takes up the value of 3. So we have a 3 by 3 matrix, and obviously the type here is float 32. We could modify this and say, for example, 16. Run that. Let's try out bool after this. There we go. We have float 16. Let's try out bool. You see everywhere is false, 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 except for the leading diagonal, which has true. Now getting back, let's say here we have 5, and then now number of columns, let's set this to 3. You see right here, this is the output we get. Now it acts like we have a 5 by 5 matrix. So we suppose we had a 5 by 5 matrix where this would be 0, 0, this would have been 0, 0, this would have been 0, 0, this would have been 1 if this was 5 by 5, 0, and then here 0, 1. So this is what we would have had if we did not, if we let this to be known, that is number of rows equal number of columns. But now that we've set number of columns to be 3, this part has been cut off, and so this is what we're left with now. With that said, let's go ahead and take this back to none, and then let's set a batch shape. So let's say this is 3. Run that. As you could see, because we set this batch shape to be 3, here we have this output which is 3 by 5 by 5. Well, let's change this to 2. So you could see that this actually is responsible for deciding on what number of batches we have right here. So here we have 2 by 5 by 5. So essentially saying that you want to have this batch shape to be 2 like this means you want 2 5 by 5 matrices which are identity matrices, that is which have their values all zeros except for those of the leading diagonal which are equal 1. And so we see how we could create this 3D matrix or this 3D tensor from the I method. Now we could go ahead and say, for example, we want 4 here. Let's run this and see what we get. We should get 2 by 4, 2 by 4 by 5 by 5. See here we have 2 by 4 by 5 by 5. And that's it for the I method. We move on to the next method, the fill method. Here we have a method as defined here in the documentation, which creates a tensor filled with a scalar value. So here we have this fill method, which we're going to copy. But before testing out the code, you could see here from this example that with this fill method, we have this tensor which has shape 2 by 3 and which has value 9 on all its different positions. So let's get back here. Paste this out. Let's call this fill tensor, and let's say this dimensions, let's say we have 3 by 4, and then let's say we want to have the value let's say 5. Okay, so let's print this out and see what we get. Fill tensor, and there we go. That's the output we get. Now let's have this one, for example, run that. See, we're able to create this 3D tensor where all the values or all the elements in each position takes the value 5. From here, we'll go on to the once method. And it should be noted that this once method is quite similar to the fill method in the sense that this creates a tensor just like with the fill method, but the only difference is that here all the elements are set to 1. So you notice that here in this definition, we do not have this value argument. Right here we had a value which we pass, but with the once there is no value because the value by default is 1. So let's have this here and then paste out right here. See, we have this once, so we'll call this once tensor. There we go. We specify a shape, let's say 5 by 3, and then we print that out. So here we have once tensor. And there we go. We have this output matrix, which is made of 5 rows, 1, 2, 3, 4, 5, and 3 columns, 1, 2, 3, where all the elements of this tensor take up the value 1. Now you could obviously do this to have or to obtain a 3D tensor. So that's the output we get. See, it's 5 by 3 by 2. From here, we'll look at the ones like. And what this one does is it creates a tensor of all ones that has the same shape as the input. So what this means is if you have an input like this one, let's say we have 12, let's not make that 1, 12, 1, 3, and then 5, 7, 2. This is actually a 2 by 3 matrix. Let's change this. So you see that this is 2. So we have the shape. The shape is 2 by 3. So its shape is 2 by 3. Now, if this is the input here, if this is the input into our once like method, what we'll get as output will be a matrix or tensor with this same shape, that is with shape 2 by 3. So our output is going to be having a shape 2 by 3, meaning that we're going to have 2 rows and then 1, 2, 3 columns. But the output, or rather the values we're going to insert here, will be all ones. So now we're going to have 1, 1, 1, 1, 1, 1. So hence the name once like. So this like is actually for the shape of this. So you're imitating the input with respect to its shape. Now getting back here, you see we had this field tensor, which is a 1 by 3 by 4 tensor. So let's have this right here. Let's say we want to have ones like tensor. There we go, tf ones like, and then we have field tensor. There we go. Okay, so let's print out this ones like tensor. Now before printing, let's try to obtain the output. So here we know that this is field tensor. The shape is 1 by 3 by 4. So it means that we should have an output of shape 1 by 3 by 4 where all these values are ones. So let's run that and make sure that that's the output we have. There we go. It is 1 by 3 by 4 and we have all ones. From here we move to the zeros method. So it's quite similar to the ones here. Just like with the ones, we have all elements set to a given value. With the ones, all the elements were set to 1. With the zeros, all elements are set to 0. So that's essentially it. Now let's just modify the code a little right here. So this was ones tensor. Let's change the shape, this 3 by 2, and then instead of ones here, let's say zeros. Here we have zeros, and let's call this, well, let's say this is, let's just copy this out and put out separately. So here we have this, we paste that out here, we have zeros, and here we have zeros, fine, and here we have zeros. Okay, so let's run that, and there we go. We should have this here. So you see it's 3 by 2, 3 rows, 2 columns. That's fine, and all values are zeros. If you were ones, then you have all values ones, and for the ones or the zeros like is similar to the ones like, so you could take that as a simple exercise. We then move forward. We have this shape method right here where we told that this returns a tensor. Take note of that. It returns a tensor containing the shape of the input tensor. So as we had seen before, we could obtain the shape of a tensor by simply making use of that tensor's name dot shape. Now if we want to have an output, like in our case now we want to have this output tensor which contains the shape of our tensor, then we could make use of this shape method from TensorFlow. So you see here we have the same 4 by 2 by 3, but this is now in this list, and then we have its shape and we also have its data type. Obviously it's made of integers, so we shouldn't expect to have a float data type right here. Another method which we could make use of is the rank method, which simply returns the rank of a tensor. So it takes in the input and then returns its rank. You have a simple example right here where we have this 3D tensor T, and then when you call on the rank method, you see that we obtain the output, which is 3. So let's put that out here. Let's just paste it out here and test that quickly. There we go. As you could see, because the output is a 0-dimensional tensor, the shape, it actually has no shape, but you could see its value right here. That's 3. Now if you take out this and take out this and then take out this other part here, there we go. We run this again. We should have a rank of 2 this time around. That's fine. You see here the rank is 2. We now move to the size here, the size method, which returns the size of a tensor. So you put in an input in the size method and it gives you the size of the tensor. We have, as usual, on the example here, which we could copy, but before running that, we could read this note here where we told this returns a 0D tensor representing the number of elements in the input of type output type. This is the output type here, which by default is int 32. So let's get back here and paste this out and check out the size. As you could see here, we have this size of 12, and that's because we have 12 different positions or 12 different elements in our tensor. Now let's take this off again. Take this off. take this off. There we go. Let's run that. We should have 6. So that's it. You see, we have 6. And yeah, we could also specify this the type. Let's say float 32. We get an error here. Got an unexpected keyword argument D type. Now getting back here, you see this is actually out type, not D type. So let's get back here, and then we have out type. So we have out type. There we go. Run that. And as you could see right now, we have a float instead of an int. The next step we'll take is creating our own random tensors. And that is essentially creating tensors which take up random values. Now in the case of TensorFlow random normal, our output values are going to be from or are going to be drawn from a normal distribution. And we are going to explain, at least at a high level, what this really means. For now, let's just copy this out and get back to the code and run this and see what we get. So right here, let's say we have random tensor. There we go. We need to specify the shape. So we'll say, let's make a matrix or 2D tensor. So let's say it's 3 by 2. Now you see we have this mean value, standard deviation values, which have been given right here by default. And we're gonna look at what this actually means shortly. The data type is float 32, seed you see is known, name known. Now let's run this, or let's print this out and see what we get. So here we have random tensor, and there we go. As you could see, we have this set of values which are all negatives, and if you notice, they are very close to 0. So here we have practically -1, about -2, -0.3, very small number, and -0.5, -0.87. So these are numbers very close to 7. Let's run this again so you see that we're able to randomly generate a matrix with this shape with random values. You see that it takes up different numbers. This time around we have a mixture of positive and negative numbers, but again these numbers are very close to 0. Now what if we modify this mean? So we modify this mean, we'll run this again. Let's see what we obtain. You see that we have these numbers now, which are instead close to 100. And so what this tells us is that we could make use of this mean and the standard deviation to decide on the kinds of random values we want to have here. Now, to better understand what is going on, let's consider this figure from this probability playground by Adam Cunningham from the University of Buffalo. As you had noticed in the code, when we did TensorFlow random normal and the mean, when we specify the mean, the mean is this mu you have here. When we specify the mean to be equal 0, most of the values we had were surrounding 0. And when we set this mean to 100, when we set it to 100, most of the values were surrounding 100. Now, this curve you have here actually explains why. So you have this curve right here, which is bell-shaped. And the idea here is that it permits us randomly pick values around the mean, that's around 0. So that's why you'd notice that at 0 we have the highest probability score. Here our probability score is f of x. So for values around or values surrounding 0, that's this value surrounding 0, there is much higher probability or chance of them being picked as compared to values far away from 0. So let's pick out these two values. Let's say we have let's say we want to pick out the two values 0.5. Let's say 0.5, and we want to pick out -5. you would see from here that the probability of us having -5 is practically 0. That's almost 0. But the probability of us having 0.5, as you could see from here, if you're taking this middle, the probability of us having 0.5 is about 0.35. Now, if we change this value and take 100, as we did with the code, let's take 100. We have that 100. Well, it looks like they fixed this to 6, so we cannot go above this. We could play around this like this. You see, you go from -6 to 6. Okay, let's say the mean is 6, so we have the mean of 6. One thing you can notice is that now this 0.5, as you could see, 0.5. Let's take this off. 0.5 no longer has a probability of about 0.35 of being picked. 0.5 has a probability now of about 0 of being picked, while -5 also still has a probability of about 0 of being picked. But on the other hand, as you could see here, let's take this off. You see that values like 5 have much higher probability of being picked. 7, 8, 6. They now have much higher probabilities of being picked. Now, this means that if this was 100, or if we're able to get to 100, then it will be values like 97, 98, 99, 100, 101, 102. And this explains why when we ran this code with this mean, we had values surrounding 100. And that's simply because those values surrounding the mean have higher probabilities of being picked. Now let's take this back to 0 and then talk about the standard deviation. So we have the 0. Oh, there we go. You see, get back to 0. And now let's talk about the standard deviation. But before getting into any explanations, let's modify this. Let's say we take 10 here. Okay, it looks like the max is fixed at 2.5. Okay, so let's say we have that 2.5. One thing you can notice is we still have this mean at 0. We still have our mean at 0. That's it. Makes sense because we haven't changed this. But our bell curved shape now appears wider. So an increase in sigma here is what we call the standard deviation. So it's what we called stddev in the code. So we had the mean and the standard deviation. So sigma is standard deviation. The sigma square is the variance. So sigma square is the variance. Anyway, what we're trying to say here is an increase in sigma will make this curve wider, and a decrease, let's decrease sigma. You see, a decrease in sigma makes the curve thinner and narrower. Now what this implies is that if we have, let's get back to this, if we have sigma square as 2.5, there are much higher chances now that we could randomly select -5 as compared to before. So if this is -5 here, you see there's a slightly higher probability of -5 being picked as compared to when we reduce this. You see, when we reduce this, you see -5 here is practically 0. But when we increase, see, -5 is at least this time around having some negligible value. And so this is essentially the role that the standard deviation plays. Now if we reduce this again, we find that even 0.5, because this is 0.5 around here, even 0.5, let's take this off. Even 0.5, which used to have a probability of about 0.35 of occurring, now has almost no chance of being picked. Let's increase that back and set it back to 0. Okay. And so that's it. At this point, we could modify this. We could take this to 6 and then take this to 2.5. And you see that we could take values now between 0. See, we go from 0 to about 11. With that said, we will then look at the uniform distribution, or how to generate random numbers or random values drawn from a uniform distribution. So again, we'll just copy this out and then get back to the code. We'll paste this here. There we go. We have the shape. Let's pick this. 1, okay, and then minimum value 0, and now we have maximum value. So you see that unlike here where we had the minimum, the mean and the standard deviation, now we have instead of a minimum value and a maximum value. So let's leave it at this, and then let's say we have random tensor. Okay, so let's print this out. Let's print out our random tensor. There we go, we have random tensor. Let's increase this so we have many more values. 5, run that. Okay, you see we have this values. Now let's say we change this max value and say it's 80, or let's say 8. Okay, let's say 8. Let's run that. And what you notice now is you have much larger values. Well, values between 0 and 8. But before, the values we were getting were values ranging between 0 and 1. Now this tells us that most probably this maximum value by default is 1. So here you see it's default to 1. You could always make use of the documentation whenever you're in doubt. So let's get back here. You see, we'll take this to 100 and then see what we get. You see, we have this values now between 0 and 100. Now the question you may be asking yourself is, what then is the difference between this uniform and this normal distribution? So let's get back again here in our probability playground, and then let's pick out uniform. So there, as you could see, there are many other probability distributions, but we're going to focus on the normal distribution and the uniform distribution. So we get into the uniform distribution, and here's what we get. So we have A and B. Now this is like our mean val, which we saw in the code, and this is like our max val. So when we say mean val -1, max val 1, obviously our values will fall in this range. Now by default this is 0 and this is 1 on TensorFlow. So that's why you saw the values ranging between 0 and 1. Now as the term goes, it's actually uniform. So this means that all these values here have equal chances or probabilities of being picked. And so unlike the normal distribution where we would have something like this, now we have this square instead, or this rectangle. And so simply here, all we're doing is picking the range of values which we want to have, or which we want to be outputted. So we could get here, increase this, where the mean cannot be greater than the max, so that makes sense. Let's reduce this, reduce that. See, from -4 to 4, you see we take all the values. Well, that's it. You see, there we go. We could go from -1 to 2. That's it. Now one great thing is also the fact that we could modify this and have ints. So let's run this and see what we get. You see, we have only integers now. Now let's say we had known. Let's run that. You see we have an error. Must specify a max val in the case where the data type is integer. So this actually reading out here in the documentation. So you could see here now that you need to have this max val. So let's change that to, let's say, 1000. See, we'll get values ranging between 0 and 1000. So we have 5 values here from the shape. We could change this, let's say 5 by 5, and then all those values range between 0 and 1000. Another argument which we haven't spoken of so far is this seed argument. And here we're told that this seed argument, when used in combination with TensorFlow random set seed, will be able to create a reproducible sequence of tensors across multiple calls. And so in cases where we want to produce reproducible experiments, we'll want to set this global seed value and also the seed argument value in this uniform, or let's say normal function. So let's go ahead and copy this out. We get back to the code. There we go. Let's just run this right here. let's take up some parts and print this out. So we print this out, then we modify the shape and the max values. So we have exactly the same value for the seed here, which is 10, and then here we set this global seed to 5. Let's run this. You see it outputs 431, 432, 111, and 133. Now let's create another cell. Let's copy this. There we go. Paste this out here, and you see we have the same global seed, and then we have the seed of 10. Now let's run this again, and as you could see, we have exactly the same output as this one. See, 431, 431, 432, 432, 111, 111, and 133. Now obviously modifying this and taking, for example, 1 gives us something different. But if you take 10 again, you see you should have exact same output. Now you also see that here when we take this off, if we take this off and we run this cell, you see we have different outputs. But when we get back here, let's run this again. See, we have another set of different outputs. But when we take this, run that, you see we have exact same output we had already. And now if you want to have more details about certain seeds, you could always check out this the documentation. Let's now dive into this new section on TensorFlow indexing. So let's suppose we have this tensor, which we'll call tensor indexed, and we simply define this 1D tensor with some values. So we have 2, 4, 9, 0, 4, 5, 6, 7, and then let's run this. And then we say, okay, we want to get, let's say this value 4. Now to obtain this value 4, we are going to make use of its index. In general, in programming, the first index is 0. So this is going to be 0, 1, 2, 3, 4, 5, 6, and then 7. So if we want to get this 4 here, we're going to have to specify the index 1. If we want to get 2, we'll have to specify the index 0, and so on and so forth for the rest. So let's, after running this, that's after getting or creating this tensor indexed, we could simply print out tensor indexed and then specify an index. So let's say we want to pick out this third, so tensor indexed 3. We'll put this 3 in a square bracket. We run that. You see that it's going to give us the value 0, which matches with this arrangement. Now, if we say we want to get the last element, or if we want to get the first element, then we'll specify 0. So the 0th index, we run that, and you see we should get 2. See, we have 2. Now, if we want to have the last element, so let's say we want to have the last element, we could pick 7, or we could say we want to have tensor indexed, and then we say -1. So when you specify -1, then you're specifying the last element. Given that we know the exact index for the last element, which in this case is 7, then we could specify 7. So let's run this and then see what we get. There we go. You see we have 7, and then we have 7. So that's how easy it is for us to obtain a value based on its position in the tensor. Now, let's say we want to get a segment or part of this 1D tensor. Let's say we want to get this segment. We want to get 4904. Now, this 4904, as we could see here, matches with the indices 1 to 4. Or let's pick another one. Let's say 4, 9045, 6. This matches with 1 to 6. You see? So let's just run this and see what we get. Tensor indexed, and here instead of selecting each and every one of this, we would do 1, because remember, we want to pick out these elements 4, 9, 0, 4, 5, 6. Then we'll specify the indices 1 right up to 6. But we are not going to say 1, 2, 3, 4, 5, and then 6, and then try to run that. You see, we get an error here. So what we're instead going to do is we're going to say we want to go from 1 to 6 by specifying or by putting between 1, that's the start index, and the end index, a colon. So we just put that colon, we run that, and there we go. You see, we have this part which we wanted. That's 490,456. But when you look at this output, it's actually 49045. Now what this tells us is, actually when we say 1 right up to 6, we're going from 1, or let's put it out this way. When we say 1 up to 6, we're actually going from 1 right up to 6 minus 1. So we're actually going from 1 right up to 5. And so if we want to go, or if we want to pick out 490,456, then we'll need to say here that we want to go to 7. So such that we'll go from 1 to 7, and or we'll go from 1 to 7 minus 1. That will be 1 to 6. So let's take that off, run that again, and you can see now that we have 490,456. So in general, what we'll do is, if we want to go from a given start, so we'll do a start to the end, but instead of end, we'll do start to end minus 1. And so in general, if we want to go from index start right up to index end, we should instead do tensor slides or tensor indexed start right up to end plus 1, so that when we do n plus 1 minus 1, it falls back at end. So that's it. Now you could pause the video at this point and try to do, for example, or get this first 3. You see that you have 2, 4, 9. That's going to be 0 to 2. Hopefully you got the answer. Let's just get that done. So we'll do tensor indexed, and then we'll do, because we're going from 0 to 2, so we'll do 0 to 2 plus 1. See, let's run that. Could take this off so that we could see the original tensor indexed. So let's take that off. There we go. You see, 0 to 2 plus 1, you see we have 2, 4, 9. Now, if we're starting from the very first index, if we're starting from the 0th index, then we must not put this. So taking the 0 off already tells us that it's actually 0. So we could have the 0, or you may not have the 0. So you see it's the same answer. Now, if let's say we want to get from 0 right up to the end, what we'll do here, we'll have 3 right up to 7. So we'll do 3 up to 7. Remember, plus 1. So we run that again, and you see we should have 0, 4, 5, 6, 7. 0, 4, 5, 6, 7, exactly as we expect. Now, given that we're going right up to the end, we could also decide not to put anything. So if you're going, if you're starting from the 0th index, you may not put anything. If you're going right up to the end, you may also decide not to put any value. So let's run that and see what we get. You see, we have exact same output, 0, 4, 5, 6, 7, the same as we would have with 7 plus 1, 0, 4, 5, 6, 7. So that's it. Now, if you want to go right up to the last but one value, you could say we're going from 3 right up to minus 1. So remember when we specified, or when we had tensor indexed, and then we specified minus 1, the value we got was 7, which was the last value. But when we specify, or when we go from a start index to that end index, and we specify this minus 1, obviously we'll go from start to end, and the end would instead be the value before the actual end. So it's just like what we've seen already, where if we're going from, let's say 3, let's take this start off. If we're going from 3 to 7, then what we'll actually get by doing this, if we just took 3 to 7, what we'll actually get will be 3 to 6. You see, so when we do 3 to -1, is the same as going from 3 to 7. So that's actually 3 to 6. So when let's run in this, you see we should get 0, 4, 5, 6. So that's it. Now if we want to get to the second to the last, that's 3 to negative 2. See, now we have 0, 4, 5. Then we could do third to the last. We have, or we should have 0, 4, so on and so forth. So that's it. Then another thing we could do is, let's get back to say 6. Another thing we could do is we could get these values in steps. Let's take that from the beginning to the seat, or let's even take the 7th value. So let's go to 7. So if we run this, we have from 0 to 7, then we have 2, 4, 9, 0, 4, 5, 6. That's fine. Now we could get these values in steps of 2. So if we put 2, see, specifying this 2 would make us get 2, and then we'll skip this one, 9, we'll skip this one, 4, we'll skip this one, and then 6. So let's just run this. Let's print this out here. Tensor indexed, and let's say go 0 to 7. Let's write out explicitly 0 to 7, and then here we have 0 to 7 but with steps of 2. So let's print this out. Let's print that out. There we go. So as you could see, we have 2, 4, 9, 0, 4, 5, 6. But now when we specify steps of 2, we'll take 2, and then we'll skip 4, we get 9. See, that's 9 here. And then we skip 0, we get 4. That's 4 here. And then we skip 6, or rather we skip 5, and then we get 6, and that's 6 there. So that's it. So essentially this is the same as having 1, so not skipping any value. So that's it. We've just looked at indexing with 1D tensors. So let's take an example of a 2-dimensional tensor. So here we have again tensor indexed, and then we have this 2D tensor. We simply fill out those values. So we have 2, 3, 4, 5, 6, and then we have, say, 9, 0, 4, 2, 1, and then we have 0, 0, 1, or well 0, 0, 0, 0, 1, 7, 0. Okay, so we have this tensor which turns out to be a 5, or rather 3 by 5 tensor. It's 2D, so we have to add this square bracket. There we go, we add the square bracket here and at this position. So this is our 2D tensor, and then we want to get a specific value. Now let's suppose that we want to get the value, or this value 9 at this position. So what we'll do is we'll start by saying how many rows do we have? We have 1, 2, 3. And what we'll do is we'll locate the row in which this 9 is found and the column. So this is the first row, second row, and third row. While this is the first column, that's 2, 9, 0. First column, second column, third column, fourth column, and fifth column. Now this 9 is found on the second row, but since we start counting from 0, we have the 0th row and the first row. So here we'll say we want to have tensor indexed, and then we'll specify we want to have 1. So index 1 because this is 0, this is 1, and then this is 2. Now for the column, we have column 0 because this is the first column, or this is the 0th column, or column with index 0, column index 1, index 2, index 3, and then index 4. So since this is index 0, we're going to have 0. But we separate this 2 with a comma. So unlike in the 1D where we didn't separate with a comma because obviously it's one-dimensional, now we have 2 dimensions. So that to the left of the comma is the first dimension, that to the right of the comma is the second dimension. Essentially this is the rows, to the left obviously, rows, and then columns. So let's run this and then see what we get. See, we have this tensor, and the value in this tensor is 9. So that's it. So you see we obtain 9. Now let's say we want to get this 2 right here. You see it will be the same row but different column. So this is 0, 1, 2, 3. So here we'll replace 0 with 3. Run that again and we should get 2. So that's fine. Now let's suppose we want to get this 042, or let's say you want to get 170. Let's say you want to get this 170. Now unlike here where we had a single value, so we just pick out a specific index, now we have a range. So just like what we have seen with a 1D tensor where we could pick out a range, now we're also going to pick out this range of values. So we have 170 which we want to pick out. What we'll do is we'll go again, 0th row, first row, second row. So here we pick second row. There we go. So because all those values fall in the second row, we just pick that second row. And then for the columns, because the values we want to pick fall in a range of columns, this is 0, 1, 2. This is where 1 starts, so column 2. See here we have 2. Remember, this is after the comma, or to the right of the comma. And then we go from 2 right up to this column. So we have 2, 3, 4. Now again, if we want to get to the 4th column, then we will do 4 plus 1, just as we had seen with a 1D. So let's run this and then see what we get. You see we have 170. But if we did 2, 4, we would have only 1, 7. So let's have that 4 plus 1. And that's fine. So that's how we obtain this. Now let's say we want to obtain just 6 and 1. So we want to obtain 6, 1. Now in this case we would have 6, 1. So this 6 belongs to row 0, 1 belongs to row 2. So we want to go from row 0 right up to row 2. But because we want to get the specific value, we'll say 2 plus 1, just as we had seen already. So 2 plus 1. And then we have the comma. So this is the first, this is for the row, and then this is now for the columns. So the one to the right is for the columns. Now we are having these values on the same column, so we'll just simply say 0, 1, 2, 3, 4. So we'll specify 4, run that, and there we go. You see we have 6, 1, 0. Because we want to have only 6 and 1, we are going to take off this 1 from here, because going from 0 to 2 is simply having 0 and then 2 minus 1, which is 1. So that's exactly what we want to have. So no need adding plus 1. That was actually an error. We would have added plus 1 if we wanted to get all these elements. That's 6, 1, 0. So let's run this again and see what we obtain. See we have 6, 1. Now let's say we want to have 6, 1, 0. Actually, if we wanted to have 6, 1, 0, instead of doing from 0 to 2 plus 1, obviously this will give you 6, 1, 0. We could take this off and just put the column. So now by putting the column, what you're saying is you want to work with all the rows. So here we work with all the rows, which is obviously the same as going from 0 to 2 plus 1. So we run this and see what we get. See we have 6, 1, 0. We could do the same for the columns. We could decide to, obviously if you say you want to work with all the columns and all the rows, then you would have the original tensor. But if we pick out a specific row, let's say the row 1, or let's say we want to go from 0 to 1, let's run that, see what we get. You see we have 2, 3, 4, 5, 6. We have this, because obviously going from 0 to 1 is like going from 0 to 1 minus 1, which is still picking only the 0th row. So we have 2, 3, 4, 5, 6. That's because we've picked all the columns. Now another way of picking all the columns is by working with 3 dots. So if we do 3 dots, we should get the exact same output. You see here we have 2, 3, 4, 5, 6. Now again, instead of picking or going from 0 to 1, we could just say 0. We'll run that again, and we have 2, 3, 4, 5, 6. But there's a difference. Let's put this side by side. So let's print out tensor indexed, and then we say 0 to 1, and then we have all the columns. Then yeah, let's just print this out. So we print this out, and then we also print out the shape. So well, the shape is given, so let's just run this. There we go. You'll notice that although we have the exact same values picked, the output has 2 different shapes. So the output of this first one is different from the output of the second one. And this is simply because when you pick out 0 like this, you are selecting a specific row. And so now since you've picked out a specific row, you are dealing with a 1D tensor, and that's why the output here is 1D. But when you select a set of rows, you're still having to do with a 2D tensor, because this 0, 1, although it's picking only this row in this case, it would have picked this 2. So when you're dealing with a range, there we have a 2D tensor, because this dimension still counts. Whereas when you pick a specific value, then you're dealing with a 1D tensor. Now let's suppose we want to pick 4, 5, 4, 2. So we want to pick 4, 5 and then 4, 2. What we'll do in this case is simple. We could pause the video and try to reflect on that. But simply what we'll do is we would have tensor indexed, and then because we want to have 4, 5, 4, 2, which belong to column 0 and column 1, we'll simply go from 0 right up to 1, or rather right up to 2, because we want to have 0, 1. It's actually 1 plus 1, that's it, which is 2. So we go from 0 right up to 2, and then for the columns we go from, this is 0, 1, 2, 3. We're going from 2 right up to 3. So we'll have 2 to 3, but obviously 3 plus 1, which is 4. So let's run that and then see what we get. You see we have 4, 5, 4, 2, exactly as we expect. After exploring the 2D tensor indexing, let's look at the 3D tensor indexing. So let's suppose that, let's first of all run this, and then we suppose that we want to obtain this value 9, which we have right here. Let's rearrange this a little so it's clearer. There we go. We want to have that value of 9, which is found at this position. So first of all, we have tensor indexed, and then as with the 2D, where we had a single comma separating the 2 dimensions, here we'll have 2 commas separating the 3 dimensions. So we have the first, second, and third dimension. Now if we print out this tensor indexed, let's create a new cell right here and print out tensor indexed. You would find that, or let's get it shaped directly. You would find that its shape is 4 by 2 by 3. So here we have 4 blocks of 2D tensors. There's a first, there's a second, there's a third, and this is the fourth. So here we have this 4 different blocks. Now 9 belongs to the fourth block, and so if we want to obtain 9, all we need to do is, let's take this one off. All we need to do is come right here and specify that we want this foot block. So this is 0, 1, 2, 3. So here we have 3. And then once we pick out this block, that's this foot block, which is 3, because we start counting from 0, we are then going to select a specific row. So this is the 0th row, this is the first row, or we could say first row, second row, knowing that we're counting from index 0 onwards. So this is 0 and this is 1. Now 9 here belongs to this row 0. So here again we'll say 0. And then for the columns, this is the 0th column, or this is the first column, index 0, second column, index 1, and third column, index 2. So 0, 1, 2. So 9 belongs to 2. So let's have 2 right there and then see what we get. So you see here we have 9, which makes sense because we've actually picked the exact position where 9 is located. Now let's say we want to have 219. If we want to have this 219, then it would suffice to maintain this 3 because 219 belongs to this block with index 3. And then we would say we want to pick for the rows, we want to pick the 0th row, but for the columns, because we want all the columns, because it goes from 0, 1, 2, or from 0 to 2, we are going to say we could go from 0 to 2 plus 1. Could run that. We should have 219, or we could just simply say we want to have all those values. We run that, and that should be fine. See, we have 219. Now that we have this 219, we could decide to pick out let's say 2 1 4 minus 3. In that case, again, we're gonna have all the rows, because 2 1 4 minus 3 contains all the rows are taken into consideration when picking these values. And then we're gonna go from the zeroth column right up to the second to the last column. So we go 0 1 2, because obviously this is going to be 2 minus 1. So let's run that, and then we see we have 2 1 4 minus 3, which makes sense. Or we could just simply say minus 1. So if we do that, we should have 2 1 4 minus 3. Now let's suppose that for each and every block we have right here, that's for all these 4 blocks, we want to get the elements which lie on the second column. In that case, what we'll do is we're gonna pick out all the different blocks, and then we'll pick out all the rows, and then we'll say we want to get the elements in the second column. So let's run that. We get an error. Here we have multiple ellipses in slide spec not allowed. So we are not allowed to have multiple ellipses as we've just done. We could just have this like this, run that, and there we go. You see that we're going to pick now all the columns, or all the columns of index 2. So here we have, see, 0 minus 1. Here we have 0 2. You can see that here. Here we have 0 0. You can see that here. Here we have 9 32. You could see that right here. You could also just have only semicolon and run that, and you should have the exact same output. So that's it for this section on indexing. We are going to move to the next section where we'll work with math operations. For the section on math operations, we shall head over to the documentation, and then just right here to the left, we shall look for TensorFlow Math. So let's scroll down and get this. Here we go. We have TensorFlow Math. You could check out this very first method we have here out of all these different methods. So here are different math functions which you could make use of very easily. And anytime you have any doubt with how a specific method is being used, you could head over to the documentation, select one like this is absolute function. You select that, and then to the right you would have that function definition. You would have some example, and then you will also have a more detailed explanation of what the different arguments the function takes in mean, and also what the function returns. That said, the absolute function takes an x. So we could get back to the code right here. So let's say we have TensorFlow absolute function which takes in x. In this case, let's say let's define x. So here we have x, which is simply a constant, and this constant is, say, 0.2. Now if we have 0.2 and we pass this into the absolute value function, then what we get as output is the same, or the exact same, 0.2. Now let's change this to negative 0.2 and see what we get. You see here we have still 0.2. Now what this tells us is the absolute value. What the absolute value function does is it takes in an input x, and if x is less than 0, what happens is this x becomes negative x. You see, and then if x is greater than 0, then that x remains the same. So you simply say remains the same. So that's exactly what the absolute value function does. Now you could also take in a 1D array. So let's say this is 1D. We have 2 minus 1, 3, 0.1, and 0. Let's run that and see what we obtain. You see, we have 2, 1. So the negative 1 has turned to 1. The 3 remains the same, 0.1 remains the same, and 0 remains the same. Now let's say we want to have your minus 0.1. Run that again. So we have the exact same number, but with the difference that whenever we have a negative value, that negative sign is taken off. Now getting back to the documentation, you would see that we apart from real numbers, we could also take in complex numbers. So you see, you see very simple examples here. You could take in a complex number, and essentially what this does is, like, when it gets a complex number a plus bj, the absolute value of that complex number a plus bj is a squared plus b squared, all of that square root. So you see this simple example here. Now let's just go ahead and test this out. So let's say we have x, or let's just copy this, copy that, and then paste it out here. So let's say we have x equal 2 plus 3j. There we go. So we have x equal 2 plus 3j, and want to get the absolute value of that x. You see we have 3.6. Now to verify that this matches with our formula, let's do 2, or let's say TensorFlow square root. So this is another TensorFlow method, TensorFlow square root of 2 to the power of 2, that's 2 square, plus 2 square plus 3 square, that's 3. Here we have 3 square, or to the power of 2, that's fine. So we have 2 square plus 3 square, and then we get a square root. So let's run that and see what we get. We get an error. We told here that the value for the attribute t of int32 is not in the list of allowed values. So let's take this to 2.0, 3.0, run that again, and see what we get. There we go. So as you could see, we have 3.6055512, and it's the exact same as this. So that's it. You see that this, when we get a complex number, it suffices to do a squared plus b squared and square root, and that's fine. Now we'll move on to the next method. We'll look at very simple methods. So let's say we have the addition method. So obviously you should know how this addition method works, because it's just simple addition. So it returns x plus y, and it's element wise addition. So obviously we would expect x and y to be of the same shape. So yeah, let's get back, and then let's take an example. Let's say we have x, which is equal TensorFlow constant, and then we say 2, 3, 5, and 7, and then we have y, TensorFlow constant, and then we have 7, 7 to 1, 7, 7 to 1. There we go. Okay, so here we would have TensorFlow add x, y. So we should, let's print that out. There we go. Let's print this out. We have TensorFlow add x, y. Now you see that we have 2 plus 7, that's 9, 3 plus 7, that's 10, 5 plus 2, that's 7, 7 plus 1, that's 8. And then as we said, these two are expected to be of the same shape, because obviously it's an element wise addition. Now what if instead of having this, we say we want to have 1. Let's say, what if we do 1? We run that and see what we get. You see, it still works, although we don't have exact same shape. And the reason why this works is because just before adding up this 2, 3, 5, 7 with this 1 is stretched out to match the shape of this 2, 3, 5, 7. So this 1 now becomes 1, 1, 1, 1, and 1. So that's it. So if you run this again, you see you would have 3, 4, 6, 8. You see, here we have 3, 4, 6, 8. That's it. So we get back to 1, run that again. We still have the exact same output. So although we said they should have the same shape, in some cases where we could broadcast the tensor with a smaller shape, then we could have the addition operation carried out without any errors. So that's it for our TensorFlow math. So this TensorFlow math add. We could also do the same with subtraction. So if you check below, you should have subtraction, multiplication. Remember, it's element wise multiplication and element wise subtraction. So let's go to M. Here we have multiply. S, we have subtract. Let's scroll down. We should have subtract, and then we also have divide. So let's get back to D. We have divide. So that's it. And you notice here that you have this divide and divide no none. So let's check out what this divide no none does. Let's get back to the code. Well, let's just check this out. You see, compute a safe divide which returns 0 if the denominator is 0. So let's get back here. Let's say we have 2, 3, 5, 7, and then we have 0. And then we decide to have divide instead of add. You see here we have infinity, 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 infinity because we're dividing by 0. And so what we could do is, if we say divide no none, run that. Well, this is, let's get the exact name. So here we have divide no none. That's TensorFlow math. Well, so far we had been using this divide from TensorFlow itself, but we need to specify we're using it from TensorFlow math, and TensorFlow math has divide no none. So let's run that, and you see we now have zeros because whenever we have an infinite output, we turn this into zeros. Let's change this and say we have 0, 2, 4, and 5. Run that again and see what we get. You see, this is 0, 1.5, 1.25, and 1.4. If we take the divide off, run that again, you see we have infinity, 1.5, 1.25, and 1.4. So that's it for this basic math operations. Before we move on to other math methods, let's consider the following example. So supposing we have this tensor which we want to multiply by this other tensor. This is obviously a 1/4 tensor, and here we have a 2/1 tensor. In that case, we would still apply the broadcasting similar with what we had seen already. So before we had 2/3, or rather 2, 3. So this was a tensor, 2, 3, 4, and then 5. And then when we multiply this by 1, this one here became 1, 1, 1, and then 1. Such that when we multiply this 2, 3, 4, 5 by 1, we're actually multiplying 2, 3, 4, 5 by 1, 1, 1, 1. Now that said, for this example here, we would still carry out this broadcasting. So we would repeat this 2, 3, 4, 5 twice, because here we have 2 rows. So here we have only 1 row. We're just going to repeat this such that we have 2, 3, 4, 5. There we go. So we now have 2, 3, 4, 5 repeated twice. That's row wise. And then this 1, 3 is also going to be repeated, but column wise. So let's take all this off. Let's take this ones off. There we go. We take this off. We take this off. And then we now repeat this 1, 3 4 times. So we have 1, 3, 1, 3, and then 1, 3. So you see now that we could multiply this 2 element wise. And after multiplying this 2, obviously this should give us something like this is 2. So all of this on the top remains the same. So we have 2, 3, 4, 5, and then what we have down is 2 times 3, that's 6. 3 times 3, that's 9. 4 times 3, that's 12. 5 times 3, that's 15. So this is now our output. Now let's get back to the code and see if this is the output we're gonna have. So we'll get back here and we have x. Let's take that off. X equal our constant. Well, let's say we have, let's get back here. We have 2, 3, 4, 5, and then 1, 3. So we have 2, 3, 4, 5, and then 1, 3. 2, 3, 4, 5. And then we have y, which is another TensorFlow tensor. And then here is instead 1, 3. So because we're going row wise, we will have 1. So this is actually 2D. So we have 1, and then we'll have 3. Whereas here, this 2D is column wise. So we have 1, 2, or we have 2, 3, 4, 5. So that's it. Now let's get back and do TensorFlow. Let's print that out. TensorFlow multiply, and then we specify x and y. So let's run that and see what we get. Increase the cells. There we go. You see we have 2, 3, 4, 5, 6, 9, 12, 15, exactly as we had gotten already from this board. Let's continue with other methods. We have, for example, maximum. So let's click on maximum. You will find that with maximum, it's simple. We're going to compare two values. It's again element wise. We compare two values. If x is greater than y, then the output is going to be x. And if x is less than y, the output will be y. We're just comparing and seeing the one which is maximum is the one which takes that position. So let's take an example. Like here we have 0, 0, 0, 0, and then -2, 0, 2, 5. At this zeroth position, the maximum here is 0, so it's normal that the output is 0. At this position, the maximum is 0. Obviously it's the same, so 0. Here the maximum is 2, so we have 2. Last position we have 0 and 5. The max is 5, so here we have 5. It also supports the broadcast semantics. So saying you want to compare -5, 0, 0, 0 with -3 is the same as comparing -5, 0, 0, 0 with -3, -3, -3, and -3. So obviously the maximum, the value, the highest value here will be -3, but for the rest will be zeros because 0 is greater than -3. So that's it. And that's it for the maximum. We also have the minimum. So minimum obviously is going to be just the opposite of maximum. So here instead we want to get the value with the smaller value. So when comparing element wise, we just want to get the smaller value. That's it. Getting back to the code, you try this with our previous example. You find that we have 2, 3, 4, 5, 3, 3, 4, 5. Now let's get back to our board and try to justify this answer. So after broadcasting, we have this output for x and we have this output for y. Now if it's a maximum, then at this position we have 2, because comparing 2 and 1, the max is 2. Then the next is 3. Well, it's going to be 2, 3, 4, 5 obviously, because all these are greater than 1, which is what we have right here. And then for the next we have 2 and 3. The max there is 3. 3 and 3 we have 3. Next we have 4, and then finally we have 5. So this makes sense that this is the output we get in. We are now going to move to the next method, which is the argmax method. So this argmax method is similar to the max method, but with the difference that here we aren't tracking the value which has the maximum value. We're instead tracking the position of that maximum value. So let's take a simple example. You have this here, this A. Let's copy this. And paste out here, so we could get the argmax. There we go. We have TensorFlow argmax or math argmax. We have A, and then we run that. You see from here that the value or the output is 2. Now the reason why we have in 2 is because the value or the max value we have here is found at position 2. Remember, let's get back here. If we want to specify each and every index, we will have 0, we have 1. Let's get back here. We have 2, we have 3, and then we have 4. Now the maximum value is 30, and it turns out that it's found at position 2. So that's why we have that. If we just if we have mean, then because the smallest value we have is 2, then we should have an output of 0. So let's take this off, run that again, and you see we have an output of 0. So essentially the argmax, argmean help you trace the position or the index on which we have the max or the minimum value. Now if instead we have a 2D tensor, then doing math argmax and then passing in our tensor, then specifying the axis to be 0, we would get an output of 32030. Now let's explain why we have this output. Because we've set the axis to 0, it simply means that we are going to be carrying out the comparisons across the rows. So that will be across the rows. Now if the axis is set to 1, then it's going to be across the columns. That said, for each and every row, that's for this row, remember we have the 0th, 1st, 2nd, and 3rd row, or we have this 4 different rows. We are going to compare values at each and every position. So for this position right here, for this 0th position, we're going to compare this value with this value, with this value, and with this value. So this is essentially comparing 2 with 0, with 0, and with 7. And we're comparing across these rows because we specified axis to be 0. And so that said, the max value we have here is 7. But 7, that's the 7 here. But 7 is found at the position 3. That's why we have 3. And then for the next, we have 1, 1, 5, and 3. The max is 5, which is found at position 2. And then for the next, we have 9, 7, 1, 0. Max is 9 at position 0. And then we have 6, 3, 2, 9. Max is 9, position 3. And finally, we have 5, 2, 0, 0. Max is 5 at position 0. So that's it. That's how we obtain 3, 2, 0, 3, 0 as we got here. Now, you could pause at this level, change the axis to 1, and try to figure out what the output would be and compare with the solution we're going to have. So let's run this. Okay, we have 2, 2, 1, 3. So let's figure out how we have 2, 2, 1, 3. The axis has been set to 1, so we carry out comparison across the different columns. So we have this here, we have this, and we have this, and we have this. So we said compare here, compare here, compare across the different columns, compare across the different columns. So 2, 1, 9, 6, 5. The max is 9, and it's found at position 2. Then we have 0, 1, 7, 3, 2. Max is 7, found at position 2. Then again, we have 0, 5, 1, 2, 0. Max is 5, found at position 1. Finally, we have 7, 3, 0, 9, 0. Max is 9, found at position 3. So that's exactly how we have 2, 2, 1, 3. Now, obviously, you could change this to mean, and you would have something similar. So that's how we make use of this argmax function. Well, this should be argmean, and then here we should have argmean. There we go. You have 1042, so that's fine. The next method we'll look at will be this equal method. Essentially, what this operation does is it compares each and every element based on its position, and then returns true or false. So looking at this example here, you see that when we compare 2, 4, that's this 1D tensor with this tensor 2, we first of all start by broadcasting. So we would have 2, 4 compared with 2, 2. And then since 2 is the same as 2, like let's get back to our drawing board. Since we're comparing 2, 4 with 2, 2, and since 2 is the same as 2, we would have true. But since 4 is different from 2, we would have false. So we would have an output which is true, and then rather here, which is true and then false. Now when they are exactly the same, we have true, true. The next will be the power method. Let's check out power. It should be this here. Now feel free to check out the others. We're just going through so you have an idea of the important methods. What this power does is it computes the power of one value to another. So it's again element wise. So if you have this example, you see here you have 2. Let's copy this, and let's take this from here. There we go. Let's get back here. Paste out that. We have x, y, and then let's reduce this so that it could be much clearer. So that's fine. Okay. So now we have 2 to the power of 0. Let's run this. We would have 2 to the power of 0, which is 1, 2 to the power of 1, which is 2, 3 to the power of 2, which is 9, 3 to the power of 3, which is 27. So you see, that's it. So that's essentially what this power method does. Now the next will be the reduce methods. So here we have reduce all, reduce any, right up to reduce variance. Now let's just pick out this reduce max, which is one of the most commonly used among these reduce methods. Here what we have is it computes the maximum of elements across dimensions of a tensor. So let's just copy this and then go ahead and test that out. So here we have an example like this one, 5124. So let's first of all paste out the code we copied, and then we have as input tensor input tensor, our TensorFlow constant, and then we have 5, 1, 2, 4. Okay, so what this does essentially is it simply sums up all the, or rather it simply looks for the max of all these elements. Now the max here is 5, so we have 5. Now if we change this to sum, you will find that it's going to reduce all this into their sum. So 5 plus 1 is 6, 6 plus 2, 8, 8 plus 4, 12. Let's run that. You see we have the value of 12. Now let's specify, like here, the axis is set to none and keep dims is set to false. I could take out name. Now let's say we set this keep dims to true. Well, let's print this out separately. So let's print this out, and then let's print, well, let's just copy that, paste out here. We have keep dims set to false. So run that. There we go. You'll notice that we have two different outputs. Here we have still this tensor with value 12, and here we have the value 12, but with the difference that this is a 1D array, whereas here we have a 0D array. Now this or a simple scalar. Now the reason why we're having this for the first output is because we've decided to keep the dimensions. So we are going to carry out the reduced sum. That's, we're going to sum up all these elements, but we are going to maintain the original dimensions, which here in this case was 1D. So that's why we have this 1D array, this 1D tensor. And then here we don't necessarily, or we don't keep these dimensions, and so that's why we have this output scalar. Now if we have 2D, so let's change this to 2D. Let's just copy out an output we had already previously. So let's take this one. There we go, we have that, and then take this off. So let's say input tensor, paste that out, get back, take this off. That's fine. So let's run this again and see what we get. Now you see let's first of all comment this part. Let's comment that, run that again. We have this output of 65. Now if you had to sum up all this, or let's just take out the max since it's easy to see the output clearly. So you see the max here, the max value we have of all these different values is 9. So that's it. And then if we were to take the sum, let's get back to sum, and you have to add all this up, 3 plus 1 plus 9 plus 6 plus 5, all this up is going to give us 65. Now if we set this keep dims to true, let's just take all this off. If we set the keep dims to true, you'll see that because we have a 2D input, we're still gonna have a 2D output, so the dimensions are maintained. And let's get back to false. And then now for the axis, which is set to none, so we don't specify any axis. But if we had to specify this axis and set it to 0, for example, then similar to what we have seen in previous examples, like the max, mean, here again, we are going to simply go through each and every row at every position and then sum up the values. So we have 3 plus 0 plus 1 plus 7, that's 11. So that's it right here. 1 plus 1, that's 2, 7, 10. So that's it, and so on and so forth. So that's how we have all these different values. Now if we specify 1, then we'll sum all these values for the different columns. So let's run that. And you see we have 3 plus 1, that's 4, plus 9, that's 13, plus 11, that's 24, and so on and so forth. Now clearly if you just add all this up, you should see that this is 65. Here we have 20, that's 18 plus 24 plus 13, that gives us 65. So here we see already that with a reduced sum we could reduce across specific axes. Now let's set this to true and see what we get. There we go. You see, because we want to maintain, or we want to keep the dimensions, we still have we have the same outputs, but now with a different shape. Again, as we've said, we have different methods, or different reduced methods. We have reduce mean, reduce prod, reduce STD, reduce variance, reduce log sum exponential, reduce Euclidean norm, reduce any, reduce all. So you could feel free to check this out. The next method we'll be looking at will be the top K. So let's click here on top K. With the top K, if we have an input, let's say we have a 1D input, like here, you see we have this 1D input. Let's just copy this. If we have this 1D input, you would find that it's going to produce the top K values, just as the method name goes. So let's print out from here. Let's print out results. The top K already clearly, you see them, you have 90, 98, 99, or rather the top three, the top three. We have 98, 99, 96, so that makes sense. Now, if you scroll here, you'll find that apart from the top values, we also have their positions. So 99 is found on at the fit index. So we have 0, 1, 2, 3, 4, 5. So that's it. That's why we have 5. So we don't only output the top 3 values, we also output the top the positions of the top 3 values. If it changes to top 5, you see we would have more values now. Yeah, here we have 99, 98, 96, 4, 3. If we change it to top 1, that's essentially just the max value, we will have 99, and obviously we'll have its position. So that's essentially what or how we could make use of the top K method. The last method we'll be looking at in this section will be the sigmoid function. So let's check out sigmoid. There we go, we have sigmoid. So essentially this is a very common method, and which we could make use of, or which you could call very easily. You could actually write this by yourself, but TensorFlow already has this, so you could you don't need to always write that. So essentially what the sigmoid does is it takes in an input, and then that input is negated. So we have minus x, we take the exponential of that value, we add +1, and then we take 1 divided by whatever output we have. So the sigmoid takes values from negative infinity to positive infinity, and then keeps them or maintains them in the range 0, 1. So let's get back here and let's take this off. So let's pull this up this way, get back, then plot out what the sigmoid function does exactly. So with the sigmoid function, as we're saying, we have this function which takes values of x between negative infinity and positive infinity, and then maintains them between the range 0 and 1. So it will never cross 1, as well as it will never cross it will never go below 0. So x goes from negative infinity to positive infinity, but the output or the result always falls in the range 0, negative 1. And we have 1 divided by 1 plus e to the negative x. Now again, we could call on this method with a 1D array. So like this, for example, you find that when you take 0, obviously the output should be 0.5. When if you look carefully at the plot, you find that 0, our output here is 0.5. So this makes sense that at the level of the plot, or rather at the level of this code, we have output 0.5. When we take 1, we have 0.73, 50 is 1, 100 is 1. Now you notice that as the numbers become very large, we converge towards 1. So that's it. And obviously as the numbers become very small, we're going to also converge towards 0. So if let's just copy this out here. I'll get back to the code, scroll up, there we go, let's run that. You see we have 0.5, 0.73, 1, 1. Now let's take very small numbers, so obviously very small negative numbers. So we have negative 50, run that. You see we have this number is now converging towards 0, so we have very small numbers. Now if we take negative 5, let's increase that, or 5e, let's say e 100, run that. Out of range for double precision float. Let's make that smaller, so we just take 1 0 off, run that again, and you could see that we have now 0. So basically as we go towards very small or very large negative numbers, we converge towards 0, and when we go towards very large positive numbers, we converge towards 1, exactly as we've seen in the plot. You see we get into 0, or we are approaching 0, and for this we are approaching 1, which is right here. Welcome to the section in which we will look at linear algebra operations. So just right here we have TensorFlow linear alg, and the very first operation we'll be looking at will be that of the matrix multiplication. So right here we have matmul. Essentially what this matrix multiplication does is it takes in two matrices and then computes the matrix multiplication of those two matrices. So here we have TensorFlow Linux, matmul, and let's just copy this part. There we go. And then we have this examples which we have right here. So let's go ahead and test this out. We have AB, take this off, and then let's set A. Let's get back up here and try to copy this. There we go. We have, let's say this is A. So this is our A. Here we have A, and then we have well, that's A, and then we have B, which is going to be the same as A. So let's copy this, paste out here. We have A and B, which are exact same. So that's it. Now let's now let's go ahead and print this output out. We have print out the matrix multiplication of A and B. So let's run that and see what we get. You see we have this error. So we have matrix size incompatible. Now the reason why we're having this is simple. Let's first of all print out A shape, and then we print out B shape. See here we have 4 5 4 5. Now if you are new to this matrix multiplication and linear algebra in general, you should take note of the fact that when multiplying two matrices, the number of columns of the first matrix would or should always match the number of rows of the second matrix. So when you have a matrix like when you have two matrices like A and B where there is no match, that's why you have this kind of error. So let's try to solve this problem. Let's say we change this from 5 columns to 4 columns, or we could change this from 4 rows to 5 rows. So B here, let's copy this, increase number of rows, take this off, increase number of rows, and that's it. Okay, so now you'll see it's going to work because we have 4 by 5 and 5 by 5, and this is our output. Now it should be noted that if instead of the matmul of A and B, we try to print out A times B like this, you would find that we'll get an error. So the matmul produces no error, but A times B produces an error. Again, here we have incompatible shapes. Now the reason why we're having this is because with this A times B, it's an element-wise multiplication. That is, we're going element by element. That's 3, and this corresponding here we multiply this 1, and this corresponding here we multiply this 9, which is corresponding we multiply, and so on and so forth. And so if we have these two matrices which do not have the exact same shape, or where we cannot even broadcast one to a given shape, then we would have an error. So you could see clearly why we're getting an error, because if we're trying to compare this 7 here, or we're trying to multiply this 7 which is corresponding in A, we are not going to have that corresponding value, and so that's why we get in this error. And so in that case, this will work. Let's get back here. This will work if we take this off. So if we take this off and run that, you would find that we have no error. So obviously we have 3 times 3, like taking this 3 times 3 is 9, so that's why we have 9 here, right here. Then if we take some random position, this 2 times 2, we have 4. That's why we have 4 right here. So that's it. Now let's take this, let's comment this, get back to our linear matmul. We get an error. That's obviously because the number of columns for the first doesn't match with number of rows for the second. So again, we're going to copy this and paste out here, run that again, and now everything should be fine. Now let's make this simpler so we could explain our matrix multiplication in simple terms. Let's take this off, take 3 by 3. So we'll have 3 by 3 here, and here we want to have 2 by 3. So let's just 2 by 3, that's 2 rows. Take that off, and then by 3, that's fine. So let's run that again and see what we get. So you see that works. 2 by 3, 3 by 3, it produces 2 by 3. Now let's take this example and show you how we get the output. So right here we have this input, which is 2 by 3. We have A, which is 2 by 3, and we have B, which is 3 by 3. And then the way we get the outputs is simple. We take 1 times 3 plus 5, that's it here, this 1 times 3 plus 5 times 0 plus 1 times 1. See that? And then we get we put the output here. So now we have 1 times 3, which is 3, plus 5 times 0, which is 0. So we have 3 plus 0. So we have 3 plus 0. And then we have 1 times 1, which is 1, plus 1. So that's how we get this first position. Then for the next position, let's bundle this up. So that's it for the first position. For the next position, we have again 1 times 1 plus 5 times 1 plus 1 times 5. So 1 times 1 is 1. 5 times 1 is 5. So we have 1 plus 5 plus 1 times 5, which is 5. So plus 5 again. And that's how we obtain all these different values. So we could bundle this other one up. 1 times 9 is 9. 5 times 7 is 35. 35 plus 9 is 44. Well, let's just put that out. So we have 9 plus 35 and then plus 1. So 9 plus 35 plus 1. That's fine. Now for the next, we have 7 times 3, 21 plus 0. So we have 21 plus 0 plus 0. So we have essentially here we have 21. And then for the next, we have 7 times 1, which is 7 plus 3 plus 0. So 7 times 1, 7 plus 3 plus 0, that's 10. And then for the next, we have 7 times 9. So here we have 7 times 9, which is 63 plus 21. 63 plus 21, that's 84. So here we have 84 plus 0. So here we have 84. So finally, we will have this output, which is 3. From here, we would have 11. We would have 30 or 45. We would have 21, 10, and then 84. So that's it. And then 84. Getting back to the code, you could verify that. You see here we have 4, 11, 45, 21, 10, and 84. This is actually 4. 3 plus 1 is 4. So that was an error. So here we have 4. That's it. We now understand how we get this output, which is quite simple. And also we could get the shape before the calculations. Now notice how, because these two are the same, see, these two are the same, the output is this outer dimensions. So the number of rows here will be the number of rows of the output, and the number of columns here will be the number of columns of the output. So here we have 2 by 3, 2 by 3 output, because here we have 2 rows and here we have 3 columns, and these two obviously must match. Also notice how, if we didn't have this, say let's suppose we did not have because this is 3 by 3, so let's suppose we did not have this last row. So we only had this output, which was, that is 2 by 3, and here we had 2 by 3. Then it means that when we take 1 by 3 plus 5 by 0, then when we want to have this 1 by its corresponding here, it wouldn't match. And so this makes sense that the number of rows here, the number of rows should match with the number of columns here, because that's exactly how matrix multiplication is computed. Now getting back, we could obviously calculate the matrix multiplication by simply doing A at B. So if you do A at B, you see you still have the exact same output. Our next operation will be the transpose. So let's suppose we have again A. Let's copy this A we had from here. Or let's just copy this B. If we take this, well, with a B, the transpose will not be very clear. With the A is much clearer, since it's not a square matrix. So let's print that out. We have A 151730. Let's get back to the board. 151730. Let's copy this. There we go. We simply copy that, paste it out, and then there we go. Let's scroll down. So that's it. So now we have this matrix right here. Let's take this off. We have this matrix, and what the transpose does is simple. So here, if we have a matrix like this one, if we have a matrix like this one where we have 1 5 1 7 3 0, then to obtain the transpose, all we need to do is make sure that all the rows now become columns. So all the rows become columns, and all the columns obviously will become rows. So this row here will become, or the second row becomes our second column. So we have this next one right here. So now we would have 1 5 1. So we go from 1 5 1 as rows now to 1 5 1 as column. Then 7 3 0, we have 7 3 0 as column. Notice how the columns, this 1 7 1, have now become the rows. So 1 7 1 is now a row. 5 3, which was a column, is now a row. 1 0 is now a row. So this is what we call the transpose operation. And using TensorFlow, again, it's quite easy to make use of this operation. So let's get back here, and let's say we do let's print out transpose A. So let's run that and see what we get. So we have A 1 5 1 7 3 0. Now we have 1 7 5 3 and 1 0, exactly as we expect. That's it for the transpose. It's a simple operation. We could take this off and see how we could change this. So we're going from an output or an input, which is, that's A. We go from an input which is 1 by 3 to an output which is 3 by 1. Also, what happens with the transpose is the number of rows changes to become number of columns, and number of columns changes to become number of rows. So we go from 1 3 now to 3 1. Also note that when you're carrying out this matrix multiplication, if you get back to the documentation, you might have noticed that we had this transpose A, transpose B. So let's get back here to the code and say we want to compute this matrix multiplication. So let's say we want to have let's print that out, linoc matmul, and then we have A and B. And let's suppose that we wanted to multiply A with the transpose of B. Well, in this case, our A is 1 3, and so if we're to have, that's B. Okay, B is 3 3, so that should be fine. So let's say we have A at B. 1 3 by 3 3 should give us an output which is 1 3. So that's it. That makes sense. Now, so A is 1 3, B is 3 3, and we have that output which is 3, or rather 1 3. Now, if we compute the transpose of this 33 matrix, it's still going to be 3 3 because it's going to be the same because number of rows equal number of columns, so it's not going to change anything. So let's suppose we want to multiply A, that's get the matrix multiplication of A and B transpose. In that case, we would have A at TensorFlow transpose and then B. So we run that, and you see we get 17 12 27. Now if we were to do it in another way, we could do TensorFlow linoc matrix multiplication, and then here we specify A, we specify B, and then just as in the documentation where we had transpose B set to false initially, we could now set that to true. So we have transpose B set to true. So essentially what we're saying here is we multiply A and B, with the difference that B is transpose instead. So we're getting A times B transpose. So we run that, and you see we have the exact same output. So this shows you two different ways of carrying out this exact same computation. Again, transposing B didn't stop or didn't bring an error because the number of rows equal number of columns. So if we had B, let's say we had changed B, let's take this off. So now let's say B is 3 by 2. We'll run that, and then we get back here. We should get an error because 2 by 3, or rather this A which is 1 by 3 doesn't match 2 by 3. Let's make that much clearer. Let's run A and B side by side and print out the shape. You see here that this computation could actually work, but when you do the transpose, of B, that's when you do the transpose of B, and then you get a shape. You find that 1 3 cannot match with 2 3 because number of columns here is different from number of rows we have here. That's why we get this error. And so if we just had B, obviously we should have no error. So far we had been using the TensorFlow transpose method. We could simply change this by doing, if you want to use the linear method, here we have matrix transpose. That's fine. So let's run that again, and normally everything should work as expected. From this point, we'll look at how to carry out matrix multiplication for tensors which are greater than 2D. So let's suppose we have a 3D tensor. Let's take some example of a 3D tensor which we had done previously. Let's get back up. We have this 3D tensor right here. Let's get back from here. We paste that out just below. So let's paste it out here. We have this tensor. Well, let's just call this A. So let's suppose we have this tensor A right here. We have this tensor A. There we go. We have our tensor A, and then we want to multiply this tensor A by another tensor B. So let's say, let's copy this again and paste out here. We have tensor A, we have tensor B, which for now are exactly the same tensors. That's fine. We'll just run this and then print out A shape. We'll print out B shape, and then we try to multiply this two. So, well, let's just print out the shapes first, and then we do A, or TensorFlow linear mat mul A comma B. So you see again we have this error, but the reason why we're having this error is because when you're doing matrix multiplication over batches of data, we consider each and every batch and try to carry out the matrix multiplication for that batch. But then for each and every batch we have here, if you look at this, let's reduce it so you can see the two at once. If you look at this right here, you'll notice that this is 2 by 3. So this is here 2 by 3. Here we have 2 by 3. And then here we also have 2 by 3. And obviously, because the number of columns in this case, which is 3, doesn't match number of rows in this case, which is 2, we get that error. So if we convert this into, because here we have, looking at the shape, we have 4. See here, we have 4 2 by 3 matrices. Here we have 4 2 by 3 matrices. So 2 by 3, if we change this from 2 by 3 to 2 by 2, so let's make sure that each and every one of this now is 2 by 2. Let's get back. We have 2 by 2, 2 by 2. There we go, 2 by 2. And then finally we have 2 by 2 for this last element. So we run that again. We get a shape, do matrix multiplication, and we have an output. So because this is 2 by 2, this 2 matches with this 2, and that's fine. So again, as we're saying, the matrix multiplication where we have a 3D tensor like this one is carried out in such a way that each and every block of 2D, there's some sort of block-wise matrix multiplication. So this block is multiplied with this block multiplied with this block, then this block multiply with this block, then this last block multiply with this last block. Now to test this out, you could simply say, what if we do A0? So let's get A0. If we do A0, let's print out A0, and then we print out B0. So we get the first block, or the first two blocks. Here we have 1 2 3 5, and here we have 1 2 0 3 5 negative 1. 1 2 3 5 3 1 2 0 3 5 negative 1, which is what we expect. Now let's do A0 times A0 times B0. We run that. We expect the output to be exactly what we had for the first block here. So we have 7 12 minus 2 18 31 negative 5, which is exactly what we expect here. Now if we change this to, let's say 2, run that again, we expect to have this exact output. See that? So this tells us that when we're multiplying two 3D tensors, we are simply carrying out a block-wise matrix multiplication. For our next method, we check out the band part method. Let's get to band part. So here we have band part. Scroll to the top. What it does is it copies a tensor, setting everything outside a central band in each innermost matrix to 0. Now, you have this explanation and maybe this definition here, which looks a bit complicated, and so we're gonna break this up. So here we have also this. You see this definition. We told that the band of this matrix is in band mn times the input matrix, and then the in band is defined, or the indicator function is defined as such. So this function, essentially what it does is it's capable of maintaining all the values of a given input while turning some of the values all to zeros, just as it was defined here. So let's go ahead and copy out this input, this simple example, and then see how we could obtain the output. So let's get back here. Or we could just take what we had already from here. So let's just copy an example we had. Let's take a 3x3 matrix. Well, let's just copy this, and then we'll just turn this into a 3x3 matrix. So getting back here, we have space this out. Then we copy this out and paste out. That's fine. 0. Well, let's not set this to 0. Let's put 1, and then let's say 3. Okay. So 5, or let's say 9. Okay. So that's it. So this is our input matrix A, and what we want to get is linear band part of A, while specifying the lower number to be 0 and the upper number to be 0. So we'll come and copy the definition and see how we could produce or generate the output. We'll go step by step and see how this output here is generated. So we have these conditions right here. Let's take this off so we could see only the conditions. See, we have these conditions, and now because our num lower is 0, here this condition is never going to be verified. So this is false. And then if we continue here, our num upper is 0, so this condition is never going to be verified too. So here already we have this condition which is never going to be verified, and this condition which is never going to be verified. Now for the other conditions, it will depend on the position of that element. So if we take this position here, we have m. So if we take this position here, we have m. Let's put this down. Here we have m equals 0, and then n equals 0, because this is the zeroed row and the zeroed column. So because m equals 0 and n equals 0, m minus n, we have m minus n, which is equal 0. We have n minus m, which is equal 0, and then m minus n, which is 0. So we have is 0 less than or equal 0. Yes, that's true. So now we would have here true. Here we have true. That's true. Is 0 less than or equal 0? That's true. So it means that because this is an R, remember with the R, any of them need to be true for us to have true. So the R is only false when we have this condition false and this condition false. So because one of this is true, our final output here is true. So let's break this up again. We have at the center, now we have true, and then on this other side, because one is true, we also have true. See, we have true. Now for our overall condition to be true, because we have the AND, because here we have true, here to the left we have true, and to the right we have true, this two must be true, and that's the case. So overall we have true. So finally we have true. And because we have true, this value of 1, if you look here, is maintained. If it were false, then the value would not be maintained. Now let's take a different example. Let's say when m is equal 0 and n equal 1. If m equals 0 and n equal 1, that's we have this zeroed row and we add column 1. So we fall in this value 5. M minus n is -1, and n minus m is 1. So that's it. Let's take this here. M minus n -1, n minus m 1. Now again we have this false. because our num lower is 0. So we have false, we have false. And then for m minus n is -1, is less than 0. So this is true. So that's fine. Here we have n minus m, which is 1. It is not less than 0. It's not less than or equal to 0. So this tends to be false. So here we have false. And so this is false, true. This is R, so this is true. Here we have false, false, and it's R, so it's false. See, now here we have true, false. Because we have AND, the two must be true for us to have true, so we end up with a false. And because we end up with a false, the 5 is changed to 0. So that's how we get this position here. Now you'll note that for the rest we will have something similar, where generally it's only when m is equal n, it's only going to be where m is equal n, that we are going to have true in the output. And so we have an output where all the values which are not on the diagonal are always zeros. So that's this band part method when we set num lower to 0 and num upper to 0. If we get back here, you'll see that we have some special cases. So these are some useful special cases. Let's take back this. You see that running this now, we have for this first, the upper, we have the upper triangular part, which is non-zero. So first of all, if you look at A, this is A, the upper triangular part remains intact, whereas the lower triangular part is all turned to zeros. Now, essentially, what this means is if you have an input like this one, let's say we have 3, 5, 6, 1, 0, 2, 1, 1, 3, and then here we have 2. This is 1. When we say we want to have the upper triangular part, let's reduce this. When here we say we have the upper triangular part, that is all these parts here being non-zeros, whereas all the lower triangular part is set to 0. Then what that simply means is you break up your matrix into two parts, so into two triangles. So you have this triangle, and you also have this triangle. Well, let's get back, because this is the upper triangle actually. So this is the upper triangular part, this is the lower triangular part. So we have these two triangles, and then we have this diagonal. So as we have seen already, when we have 0, 0, the lower triangle and this upper triangle is 0. Whereas when we have let's take this other condition, when we have -1, 0, we have here the lower triangle, which is set to 0, whereas this remains intact, and the diagonal also remains intact. And then when we have 0, -1, well, this is 0, -1. When we have -1, 0, we instead have the upper part, which is set to 0, as you could see here. So when we have 0, -1, or rather -1, 0, when we have -1, 0 is this upper part, which is set to 0. Now there are some special cases, or in practice you may want to have an output which is having let's say this upper part, this upper triangular part set to 0, or maybe the lower triangular part set to 0. And in that case, the band part method comes very handy. Another method which we have is the determinant, which helps us compute the determinant of a square matrix. So it's important to know that this is a square matrix, that is m should be equal n. So the number of rows should be equal to number of columns. That's a very simple method, which you could use depending on what problem you're trying to solve. Then we also have the inverse. So let's get to I. We have the inverse. There we go. Now note that the inverse of a matrix is one which is defined such that the inverse of a matrix is one which is defined such that A inverse times A. So the inverse of A is such that A inverse times A gives you the identity matrix. So if we have A to be a 2 by 2 matrix, which is like say x, 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 whatever value we have in here, multiplying this with this inverse will give you the identity matrix, which is 1, 0, 0 and 1. And so if you have a matrix like this one and you want to find that matrix such that when you multiply with this matrix, it gives you the identity matrix, then you could make use of this TensorFlow inverse method. So that's it. So you could compute the inverse of one or more square invertible matrices or their adjoints. So that's it. The next method we'll be looking at is the INSUM. The INSUM operator offers a clever way of carrying out matrix computations by taking into consideration just the shapes of the different matrices or of the different tensors. To better understand how the INSUM operator works, we shall take several examples. So let's start with the matrix multiplication. Right here we have A, B, and then we carry out matrix multiplication of A and B, and then we obtain C. Obviously, because the number of columns of A equal number of rows of B, this matrix multiplication is valid, and we have this output which is of shape 3 by 5. So here's the output we get. Now, if we were to use the INSUM operator to get the value of C, what we would make use of will be the shapes of our different matrices. So this, for example, is 3 by 4, and then B is 4 by 5. Obviously, the output C is 3 by 5. And so if here we have I, J, so if we take this to be IJ, we put a comma, and then here we have J, K, then our output is going to be I, K. Notice how this J is the same as this J. So because we these two must be the same, we maintain the J. But we have here I and then K as output. So here we have I, K. And so if we want to translate that into code, we would have TensorFlow INSUM, and then we would have the string which takes IJ, comma, JK. So this we want to multiply A, which has a shape, and then by B, and then the output is going to be IK, which is now C. So we pass in A and B, and it understands that this is A and this is for B. So let's run this and then get this output IK. So you see here we have the exact same output as with the matrix multiplication. Now another example we could take is the dot product. So let's suppose that we have two vectors. So let's set A and B again. Let's just copy this. So we have two vectors, A, just 1D. So here we have, or we take this off. Well, let's just take all this off. Take this, put this here, and then we create our 1D tensor. So we have this 1D tensor, which is our vector, and then we want to do A dot B. So dot product, want to get dot product of A and B. Here we have, say 0, let's say 1, let's say 3, and then let's say 9. Okay, so well, let's just put this a small number. So if we had to calculate this manually, we would have 2 times 0 plus, which is 0. So we would have 0 plus 6 times 1, which is 6, plus 5 times 3, which is 15, plus 2 times 2, which is 4. So in that case, we are going to be having 21 plus 4, that's 25. Okay, so if you want to compute the dot product, what we'll do here is we would make use of the INSUM. So we have INSUM, and then because we have A here, which has a shape I, because it's not 2D, it's 1D, so we just have I, and then we have B, which is shape J, you see. So it's like before, here we had this comma separating the two. So let's put that comma, you see, this is A, this is B, and then the output is going to have no shape because it's going to have it's going to be a scalar. So because it's going to be a scalar, we put nothing in front of the arrow, and then we just simply put in A and B. We run that, and there we go, we have 90. We are expecting to get 25, but we instead got 90. Now we have A here, which has shape 4, and then we have B, which has shape 4, and then when we define this, we act as if A and B, although 1D, have different shapes. So we act as if we could have 6 here, or we could have 9, or we could have whatever number, and which is not the case, because for us to carry out the dot product, this two, that's A and B, must have exactly the same shape. So if we have shape 4, then here we should have shape of 4, and so that's why we have to change this J into I, because this two must be the same. This is similar to what we had with the matrix multiplication, where this J and this J, or essentially we make sure the column here is J and the row number is J. So to let the AND-SUM operator understand that this is this condition must be verified, and if this condition is verified, then we have matrix multiplication. So getting back here, you see if we have I, and then we output nothing, meaning that we just sum up, or we'll just multiply and then sum up all the values, since we'll get a scalar. Then if you run this again, you find that we have the output 25. Now talking about, let's get back here. I'll take this off and paste that out. Let's say we had J. So let's say we had J. If we had J here, then we'll be instead computing the outer product. Now with the outer product is different, because we could have something of different length. We could have 1, and that will still work. So if you run that, you'll still have an output, because I and J could be different. But if you get here and you have 1 and you run this, you should get an error. You see, that's an error, which makes sense because these i's are the same. So let's get back, run that again, and get back here. So that's it. So you see, that's what we have. Now if after this, that's after this I, we do, let's say we want to have an output I, we run that. You see, we have the output that we have here is still another 1D tensor, and when you look carefully, you will notice that what we have here is simply gotten by multiplying each and every element here. So if we take this zeroth element, multiply by 0, that's 2 times 0, we have 0, 6 times 1, we have 6, 5 times 3, we have 15, 2 times 2, we have 4. And then when you sum all this up, we have now 25. So essentially, when you specify that the output should be I, like this, all what you're saying is just do the element-wise multiplication and give me whatever output we get. But when you take this off, what you're saying is generate this, because after multiplying, you generate this. And then because there is no output, I want a scalar. And since I want a scalar, I'm going to sum all this up to produce that scalar. So when you run this now, you see we have the 25. Then if we say ij, we run this, you see output subscript contains a label j not present in the inputs. Well, this makes sense because obviously you cannot have you cannot introduce j when it's not present in the input. So let's have ii. Run that again. Output subscripts contain a label appearing more than once. So here we told that we have this label I, which is appearing more than once. Anyway, that's it. Let's take this off. We have our dot product, and then now we get back to our outer product. For the outer product, here we have 2652 and then 0132. Let's take this off for now. So 2652 0132. To compute the outer product of these two, we'll rearrange this way. So let's say we have this matrix, or we have this tensor, and then we have this other one. Let's turn this like this. Let's get this transpose. From here now we do 0 times 2. 0 times 2 we have 0. 0 times 6 we have 0. Well, we have all zeros here. And then 1 times 2 we have 2. We just maintain this. 2 6 5 2 6 18 18. 3 times 5 is 15. 3 times 2 is 6. 2 times 2 is 4. 2 times 6 is 12. 2 times 5 is 10. 2 times 2 is 4. So this is now our outer product, and this is how it's computed very easily. Getting back to the code, if we have this as A and this as B, then if we say we want to have ij, so we want to generate this 2D matrix, which takes into consideration, or which takes as input A and B, and then computes outer product, and we run this, you see we have this matrix which is similar to what we just generated, with the difference that this is the transpose of what we got. Well, getting back, you see this is, note that this is let's just copy all this so we could compare on this on the board. Take this slightly up. As you can see, it's exactly the same as the transpose of what we just computed. So what this tells us is when we have this two like this, the A acts as the column matrix and the B acts as the row matrix if we have ij. So this A here, this A is a column matrix and B is a row matrix. So instead of 2652, we're supposed to put it out like this. So it's supposed to be 2652 and then 0132, so that when you multiply now, you have all the answers you have exact same response as expected. If you want to have the original, or what we had when we computed this originally, you could instead have, well, no, this is AB, and then here you could do JI. So you run that again and you see we have exactly what we got initially. So this, if it's meant to be in order, that's ij, then this is going to be our column matrix, and then this is going to be our row matrix. So let's say now that we have C. So this is our C. Let's go ahead and compute the sum of all elements in C. If we want to compute this, we'll simply make use of the reduce sum method. So reduce sum, let's print that out, run that again, and then we see that we have 90. Now let's print out C. So we have C printed out and we have the sum of 90. Now what this tells us is that initially right here, when we had computed this and then we had put out or when we had ij, you see, remember when we had ij, we ran this and then we had 90. It was simply because we had computed the outer product instead of the dot product, and then we had summed up all the elements in this outer product. Because now if you get back here, let's take this off, print it out, and then instead of coming up with this 2D tensor, if we come up with a scalar by saying we don't want, or by simply not putting anything in the output, and you print this out, then you see now that you get the exact same 90 which was expected. So when you sum all this and then when you just do this directly, you get that same 90. So that's why initially we had made an error here. So instead of 25 we got 90 because of that error we made. That's we're computing the outer product instead of the dot product. For the next one is going to be the transpose. So let's suppose that we have this matrix C. Let's say we have this matrix C, or well, let's just go and copy out A again. Let's try to get the transpose of this B. We'll copy A or B, doesn't matter. So let's say we get, this is our B, so that's our B, and then we want to get the transpose of B using the in-sum operator. Then you could pause at this level and try to figure that out. So what we'll do is we'll say, okay, B is ij. Remember, B is ij, but there is no comma here because we are dealing with only one matrix or only one tensor. So the output is going to be ji. That's all. So, and then you pass in A. So you run that. We get this error, expect input to have rank 2 but got 1. While looking at this, you see we put A instead of B. So when you replace and put B, you find that now it works. So this here has been transposed. Notice how we have 29030 and here we have 29030. 368 negative 22, 368 negative 22. So that's it. We've simply gotten the transpose of our input matrix. For the next, we'll look at the element-wise multiplication. So let's come and copy A and B again. Here we have A and B. We copy that. We get down and then simply paste that out. Remember, since it's element-wise multiplication, this two must have the exact same shape. So let's take this off, take this off, take this off, and that's fine. So now we have 2 3x4 matrices. If we do the usual element-wise multiplication, A times B, then you should have obviously for each and every position the product of the two elements. So if you take this -2 times 6, we should have -12. So that's it. Now for the with the AND sum operator, we could do AND sum. Now we have for A is ij, and then B must be ij because we said they should have the exact same shape, and then the output should also be ij. So let's run that and see what we get. We have ij expecting 2. Okay, so we forgot to put A and B here. Run that again, and our output, as you could see from here, is exactly the same output we got from here. So we have 4, 54, 06, and so on and so forth. So we see we have exact same output, and that's how we obtain this element-wise multiplication. Let's now see what happens when we have, say, 3D tensors. So let's get back again here. We just duplicate all this. Well, let's just duplicate all this, copy paste, and send this just up right here. We have now this 3D tensor. So here we have 2. We add the batch dimension. We have 2 by 3 by 4. So we have 2 3 by 4 tensors. So this is the first one, and then this is the second one. So this is A now. Here we have A, and then multiplied by, yes, multiplied by the B, which is 2 4 by 5 tensors. So this are the 2 4 by 5 tensors, and this obviously is going to give us 2 3 by 5 tensors. Now, just as we had seen already with the usual matrix multiplication, we had ij, jk, which gave us ik. Here we're gonna have b, ij, b, jk, and which is gonna give us b, ik. So the only thing we're gonna add here is simply just this b. Let's get back and try to repeat that. Let's get back here. We had this a and b. Hope it's the exact same. No, that's not the same. Let's get back to where we computed the matrix multiplication. There we go. We had this here. Let's just copy all this. So that's it. And instead of this here, we're gonna put this out. Okay. So now we have A. We have A, which is gonna be made of this two of this. So let's get back. There we go. Get from here, and that's fine. So that's it. So here we have this, and then we'll repeat this. So let's just repeat this, paste that out, and that's fine. So now we open this up here, and then we close this at the end. Close this right here. So now that we have this our 3D tensor, we repeat the same for B. There we go. We have A and then B, and we print out their shapes. So let's now do AND sum, and then we have we have B, I, J, and then we have B, J, K, B, J, K, and then we now have B, I, K. So let's run that and see what we get. So here we have A, B. You see we have this output. It's obviously supposed to be the same output because they're the same matrices or same tensors which we've repeated. Here we have 33, 69, 77, -6, exactly as we expect. A practical case of where we could apply or make use of the AND sum operator is with the transformer model. So right here we have the softmax of QLK transpose divided by square root of dk times v. Anyway, you don't need to understand what's going on. Just take note of the fact that we have QLK transpose and that we want to multiply Q by K transpose using the AND sum operator. So it's the same as just saying we want to multiply A by B transpose. So let's say we have A, which is this 3D tensor. Let's copy that and paste out here. We have A, which is this 3D tensor, and then we want to do A times A transpose. So we want to have A times A transpose. So now we're multiplying A with A, and then we have transpose B set to true. So what we're saying here is we want this to be transposed before we multiply with A. Let's print out this and see what we obtain. There we go. You see we have our expected output. Now let's suppose that we wanted to use let's use the AND sum operator. So right here we would have print AND sum, and then we simply specify that here we're gonna have, because let's print out a shape. Let's print this out here. Let's print out a shape. So as we're saying here, we're gonna have 2 by 3 by 4. So it's bij. There we have bij, and then for the next one is gonna be b, but ji, or rather b jk, because this could be 2 different matrices or 2 different tensors. Now before putting out the string, let's just repeat, or let's just put out the shapes here so it's clearer. So here we could have 2, 3, 4, and then we could multiply this. We could multiply this by 2, or the transpose of 2, 3, 4. Now what's interesting to note is the fact that because this column is already fixed, it means that year 2 it has to be fixed, because when you transpose this, we're gonna have 2, 4, 3. We're considering that the batch remains fixed. So when this is transposed, so this is gonna be now, or let's just put this out as the transpose. Let's say the transpose multiplied by the transpose of this. So after transposing, let's copy this, paste it out here. After transposing, we expect to get 2, 4, 3. Let's take that off, get back here. Okay, so we have 2, 3, 4 by 2, 4, 3. So we have to ensure that this number of columns matches with this number of columns for the first matrix. Whereas this 3 here doesn't need to match with the other. So we could have 2, 3, 4, and then 2, 34, and here after transposing is going to be like 2, 4, 30. Anyways, this 4 and this 4 match, so that's fine. So that said, what we're seeing is, because this 3 could be any value, it could be 1, it could be whatever value, we have to be careful with the way we note that, because in this case we took 2, 3, 4, 2, 3, 4, maybe tempted to use the exact same letters for those two. So getting back here, we have I, J, K. This is I, this is J, and then this is K, and then the transpose of that's multiplied by the transpose of 2, 5, 4. So now we have I again. That's the same I, or let's say batch ij, and then here we also have batch. There we go. And then now we have K. So we're calling this K because this 5 could be whatever. It must not be exactly this 3. So it must not be I. So we have K. And then for the 4, we have J, because it must match. Remember, after we transpose, let's print this out again. This is what happens after we transpose. After we transpose, we'll be having JK, and this J now we match with this J. So it's important that we take note of that. Let's take that off, and then now we have A and A. So that's it. Let's run this and see what we get. You see, we have 138, 16104, and so on and so forth. Well, actually, this is the reduced sum. So let's go ahead and put the arrow, and then say we want to have B. Now, this is very important, because you have to be careful with the way this is going to be, or the output is going to be generated. Here we have B, we have I, and then we have K, because this J and this J is going to be eliminated. So we have Bij, Bkj, and now Bik, slightly different from the usual matrix multiplication, because here the second matrix or second tensor is going to be transposed. So that's it. So run that, see what we get. You see, we have exact same output as what we had before here. So 69, 852, 821, 0. That's it. Exactly what we expect. So that's it for the end sum operator. Hope this section was clear, and see you in the next section, where we shall look at other common methods in TensorFlow. In this section, we shall be focusing on common TensorFlow methods, like the expand-dims method, like the squeeze, reshape, concatenate, stack, gather, and gather ND methods. So we will start with the expand-dim method. So here we have expand-dims. Let's first of all suppose that we have some input. So let's say we have A, which is this TensorFlow 1D, or this 1D tensor. Let's say we have 1, 3, 4, 5, 6, 7. 6 and 7. Okay. So let's suppose that we have this tensor A, and we have a method which takes in only 2D values. So what we could do here is we could add an extra dimension. That's the role of our expandims method. So here we have expandims returns a tensor with a length 1 axis inserted at index axis. So you see it takes an input and a specific axis. So essentially here, because we do not want to change the values we have in our input, like in this case A, we are just going to add an extra axis of length 1. So if we want to have, let's just do TensorFlow expand dims, we have A, and then let's say we add this, the zeroth axis. So we have that. Well, for now, let's print out the shape of A. So print out a shape, and then we have this TensorFlow expand dims A axis specified to be 0. There we go, and then we run that. You would find that we have this output, which is 1, 3, 4, 5, 6, 7, similar or the same as what we have here, but with the difference now that we have this extra dimension. See this, of size 1, and so now we'll be able to pass this into that method which needs a 2D input. Another example or another modification could be that we may want to add this axis instead of position 1. So if we have an input like this and want to add this at position 1, let's have this 0. Let's just copy this and place out here. So now we have position 1, axis 1. You see now that we have this still a 2D tensor, but now that extra axis was added at this position 1. So now we have a 6x1 tensor instead of a 1x6 tensor. Again, it's still the same values, 1, 3, 4, 5, 6 up to 7. Obviously, if we have something 2D, that's if you have a 2D tensor or even a 3D tensor, you could convert this into a 4D tensor. So let's just paste this out here. We have A, and then let's run that. TensorFlow expand dimensions. Well, let's print out the shape of A. Print out the shape of A. We have TensorFlow expand dimensions, and then we specify A, and then we give the axis. So let's suppose that we do not put any axis. Let's just run that and see what we get. You see, missing required positional arguments. So let's have axis equals 0. We run that, and you see now we have a 1x2x3x4 tensor. So this is a 4D tensor we have now from this 3D tensor. So that's it. If we say we want to have 1, you see, notice how it's 1x2x3. If we say we want to have 1, it's now 2x1x3x4. It's still the same tensor, still same values. You see, 2, 6, 5, 2, and so on and so forth. So it's still the same values, but now it's 2x1x3x4. So we've added this extra dimension right here. Here in the documentation, we have some uses of this operation. So you see, when we want to add an outer batch dimension to a single element. So let's suppose that you've trained a model, and then you have some inputs. So let's say the input was this here, or let's take this input. So let's suppose that we have this input, which is 2x3x4. Now the models are generally trained in batches, and so it wouldn't take this 2x3x4. It will want to take an input of shape batch by 2x3x4. But even though we have this input which is 2x3x4, we could convert it to that form batch by 2x3x4 by simply adding that dimension, and that's done by this expand dims. Another case where we could make use of the expand dims method is to align axes for broadcasting. So we could add that extra dimension and then carry out broadcasting. Then we have to add an inner vector length axis to a tensor of scalars. It should be noted that if we have, or if we set the axis to -1, then that's simply the last axis. So here, if we say -1, you will find that this will fall at the last position. So here we have 2x3x4 by 1. This operation is related to TensorFlow squeeze, reshape, and sparse expand dimensions methods. Well, let's look at this TensorFlow squeeze. Here, instead, we have that it removes dimensions of size 1 from the shape of a tensor. So it's kind of like the opposite of what we did with the expand dimensions. So here, let's suppose that we have this output. So let's say we have C, which is this. Let's print out the shape of C. Now, if we do TensorFlow squeeze, and then we have C, and that will specify that the axis we want to take off is the last axis, then you get a new output. So here we have, let's get back, here we have the C, which has a shape, but after squeezing out that dimension, we now have 2 by 3 by 4, which is what we had originally. So that's how we could play around with these two methods depending on your specific use case. Moving on to the reshape method, we have this tool which permits us reshape our input tensors without changing the order in which they were initially. So let's get back here. Suppose we have a constant, and here we say 1, 2, 3, 4, 5, 6, 7, 8, and then 9. So let's say we want to reshape this. We could do TensorFlow reshape, and then we'll pass an A, and then we give it a new shape. So for now, we have this 1D tensor, which has 9 elements. And so we could convert this into a 2D tensor where we would have 3 by 3. So let's run this and see what we get. Let's run that. Let's print this out. There we go. You see we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice how the ordering is maintained. Now you could have 3 by 3 by 1. Run that again. See, ordering still maintained. Now let's get back and say we want to have 3 by 2. You see we have an error, and this makes sense because you cannot have as input 9 values and then want to reshape in such a way that you would have expected to have 6 values, because this output matrix here, which is 3 by 2, has actually 6 values, or takes 6 values, because obviously it's 3 by 2. So that's 3 rows, 2 columns. That's 6 values. And so given that our input is above that, this reshaping cannot work. So you have to be careful to make sure that the shape you pass in actually matches with the input you're sending in here. And so sometimes when you're not sure, you could say, for example, -1. So if we put -1 right here, you'll see that it's going to, TensorFlow is going to figure out what is the right value for this position. Now, if you put 4, obviously if there's no number that when you multiply by 4 is going to give 9, so it's not going to work. But let's say we put let's try -1 here. We try -1, we still have an error. So reshape only one input size, maybe -1, not both. So because we have both here, it doesn't work. So let's say we have that 3, -1, and then let's say 1. Run that again, and we should have this 3, 3, 1. So that's it. That's how we carry out the reshaping. Now we could have 2D inputs like you have here in the documentation. Scroll down, you could pick out some examples. So let's say that we have this T1. Let's take this T1, and then we paste it out here. There we go. We have T1. Let's print out the shape of T1. Has an attribute shape. Well, this is TensorFlow constant. That's fine. Put this way, and then we close that. So we have T1 shape now, and we could reshape this into a 1D tensor. So you could do TensorFlow reshape of T1 of shape 6. So we'll run that, and you see that works. So we now reshape this into a 1D tensor. Again, notice how the order is maintained. So if we had 4 here, and then here we had, let's say, 2, you run that and run this, we should have 1, 4, 3, 2, 6, 5, 6. So the order is respected. We now move to the next method, which is going to be the concat method. Let's get back to C, Here we have C concat. There we go. We have this concat method, and what this concat method does is it concatenates two tensors along a given dimension. And so that's why here you have to specify the values. That's the two tensors, or the different tensors, and then you also specify the axis. Let's copy this example and show how the concatenate method works. So here we have T1, T2. There we go. Then let's run this, and then let's do concatenate. That's concat, and then we'll specify T1 and T2. Then we have the axis, which is set to 0. Now let's first of all start by printing out the shapes of T1 and that of T2. As you could see, they're both 2x3 tensors. And so what the concatenate method does is, when you specify the axis, it's going to concatenate the two tensors along this specified axis. So 2, 3 together with 2, 3 is going to produce 4, 3, because you specify that the axis is 0. So along this 0th axis, we carry out the concatenation, and then we're now left with an output which is 4x3, and that's exactly what we see right here. Now notice how this 1, 2, 3, 4, 5, 6 is this first T1, and then 7, 8, 9, 10, 11, 12 is the next T2. So what if we modify this axis? So let's take this to be axis 1. If you have axis 1, then we would go from 2, 3, 2, 3 to 2, 6. You see, we now concatenating along this axis 1. So now we have 2, 6. So let's run this and see what we get. You see, now we have this 2x6. So again, we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. There we go. For this first part, see this first part, and then we have 7, 8, 9, 10, 11, 12. So depending on whether you want to concatenate along the rows or along the columns, you just need to specify that we're at the level of this axis. Now let's take some other example from the documentation. Scroll down and let's copy this example. Here we could start by printing out the shapes. So we have T1 and T2 shape. There we go. We have 2, 2, 2 and 2, 2, 2. And so if we concatenate along the last axis, as the example was given in the documentation, then we would have, let's add this code cell and show that. So let's just copy this. We have 2, 2, 2 concatenated with 2, 2, 2 along the last axis. That's because we specify -1. Then our output should be 2, 2, and then 4. So we'll still have our 3D tensor as output, but the 2D tensors, or the matrices we have in this 3D blocks or in this 3D tensor, but this 2D blocks will be concatenated such that we now have 2x4 shapes. So instead of this 2x2, we'll take this, concatenate with this, and then form 2x4. Then we'll take this, concatenate with this, and we form 2x4. So let's go ahead and run that and see what we get. You see, we have 1, 2, or 1, 2, 2, 3. Let's get back here, scroll back up. We have 1, 2, 2, 3. See that block? Here is it, right here. 1, 2, 2, 3. And then we have 7, 4, 8, 4. This block. See this block right here? Well, it's actually this with this. And then for the next one, we have 4, 4, 5, 3, which is this block. 4, 4, 5, 3. And then we have 2, 10, 15, 11. Now, if this was along the 0th axis, as if we had 0 here, then we should have 4, 2, 2. See? So now we're going to have, instead of having blocks of 2, we're going to have blocks of 4. So let's run that and see what we obtain. There we go. You see, now instead of having a block like here where we had just 2, like here we just have 2 blocks of 2x2 matrices. Now we have 4 blocks of 2x2 matrices. And obviously we have 1, 2, 2, 3, 1 2 2 3 4 4 5 3, and then we have 7 4 8 4 2 10 15 11. So that's it. Now another common and similar method is the stack method. What the stack does is it stacks a list of rank R tensors into one of rank R plus 1. So getting back is similar with the concat. So we take in the values and then we specify the axis. So let's get back and see what we get when we carry out stacking for this first example. So here we have T1 and T2. Now let's take this off. Let's do TensorFlow stack. TensorFlow stack, we have T1, T2, and then we specify the axis. Let's take axis 0. We run that and see what we get. Well, let's take back this. Let's run this again because we had created a new T1, T2. So one thing you'll notice is that with a concat, let's take the axis to, let's set the axis to 0. With a concat, there is no extra dimension created. So if our inputs are 4x3 or if our inputs are 2D, then our output will be 2D. Whereas with a concat, if our inputs are 2D, then our output will be 3D. And if our inputs are 3D, our output will be 4D. So here we have this 2, 1, 2, 3, 4, 5, 6. There we go. And then we have 7, 8, 9, 10, 11, 12. You see, they have been stacked in such a way that they now form a 3D tensor where we have this extra dimension created. So if you look carefully at the stack method, it's similar to carrying out expand dems. So making use of the expand dems. Let's have the axis set to 0. So we add an extra dimension to T1, and we also add another extra dimension to T2. So there we have this extra dimension added to both T1 and T2. Let's reduce this, and then we run that. So, well, this is concat actually. So let's get back. Let's just have this. Copy that, and then let's run it just above here. So here is concat, and let's take this back to the original stack. So when we stacked T1, T2, okay, so that's for stack. Run this again to be sure. So this is for stack 2 by 2 by 3. Now what the relationship between concat and stat is, for the concat, you can get the stack from concat by adding this extra dimension. Remember we said we're gonna add an extra dimension, and here we just simply add that extra dimension for T1 and add it for T2, and then carry out a concat normally. So you will notice that now we have exact same output with a stack and with a concat. So you see clearly the difference between the two. With a concat, no extra dimension added. With a stack, we have that extra dimension added. Now if we change this axis to the last one, -1, we're gonna have 2 by 3 because our inputs are 2 by 3. So our inputs are 2 by 3, and now by 2. So the stacking is done on the last axis. So here we have 1 7, or well, we have 1 2 3 4 5 6. You see, notice this here, this arrangement, 1 2 3 4 5 6, and then here we have 7 8 9 10 11 12. So the arrangement now is different from what we had before when the axis was set to 0. Again, you just need to specify -1 here. Run that. We're getting something different, but we just needed to have this expand, this extra dimension added at the end. So let's run that again, and you see now that we have exact same output with a stack. Our next method is the pad method, and essentially it pads a tensor with given values. So here we have TensorFlow pad, takes in a tensor, the paddings, the mode, and the constant values which we will pad with. So let's take this example and illustrate or show exactly how it works. Let's get back to our notebook. We paste this out here. You see we have this T. So that's our T. Then we have the paddings. We're going to explain exactly how this works. Then let's print this out. So let's print this out and see what we get. You see we have 1 2 3 4 5 6, and then all this is padded with these zeros. Now, to understand how this is, how we get this kind of output, you should note that this value for these values we have here for the paddings permit us to know how many values at the top we're going to add, how many values at the bottom we're going to add, how many values to the left we're going to add, and how many values to the right we're going to add. So if you notice, here we have 1, 2, 3, and then we have 4, 5, 6. At the top, it's padded with zeros, just one. And at the bottom, it's padded with zeros, just one layer. So we have just one layer up and one layer down. But to the left, we have 2 layers. Notice how we have 2 layers, and to the right, we have 2 layers. Let's say to the right, we want to add 2 other layers. So let's just change this to 4. We run that again. You see now that to the right, we have those 4 layers. If we want to the top to be 4, we change that, run that again. You see now that to the top, we have 4 layers. To the right, we have 4 layers. To the left, we still have 2 layers. And then to the bottom, we have 1 layer. That's the role of this patterns we have here. We also have different, this come in different formats. So we could change this, like you see in these examples. We have here, well, this is stack. Let's get back to pattern. Okay, so if it's constant, and then we specify the constant values, so we could change this here. Constant values. So let's say we have constant values, and we set that to, let's say 20, or let's just say 9, value that's not found in the original tensor. So here we have 9. You see, all padded by 9s. Getting back, apart from padding with constant values, we could decide to reflect or use symmetry. And what this means is that the patterns or the padded values we have surrounding our main tensor, like here, are going to be gotten from the tensor itself. And the way these patterns are gotten will be depending on whether it's a reflection or whether we're making use of symmetry. The next method we'll look at is the gather method. So what this gather does is it gathers slices from the tensor axis according to the indices. So remember, when we're working with indexing, we had, for example, we could say A is this constant, and here we had, say, 0, 1, well, let's just say 4, 5, 6, 7. So if we had this input and then we wanted to have the elements 5 and 6, in that case we will do A 1, 2. No, A1, 3 actually, because it's 3 minus 1. So there we have 5 and 6. So we go 1, and then this is 0, this is 0, this is 1, this is 2, and that's exactly why we have this 5, 6. Now, what if we wanted to have 4, 7, and then 5? So what if we do not want this to be in a specific order? That's where the gather method comes in. So if we want to have this 4, 7, 5, then we'll say gather, we'll specify A, we'll specify that 4, which is 0, 7 is the last, that's 0, 1, 2, 3, so 3, and then 5 is 1. So when you specify it this way and set the axis to 0, you see now that we have 4, 7, 5. So it's capable of gathering all those elements based on this order we had set. Let's suppose we have this B. TensorFlow gather, and we specify B. And let's suppose we want to have this right here. We want to have this, and then we want to have this. But we want to have this first before having this. So in that case, we will have B. We'll specify that we want to have the last, because this is row wise, this is 0, this is 1, this is 2, and this is 3. So we want to have 3 and then 0. And the axis we specify that's the row, the rows. So it's row wise. So when we run this now, you see we have 3, 30205, 30205, and then 0, which is 29030. So it permits us to gather elements from our tensor very easily. Now imagine we wanted to do this same process but column wise. We'll specify the axis to be 1, but here we have let's say we want to have this column that's 9630 and wanted to have 3, -2, 0, 0. In that case, we will do 1, because this is 0, this is 1, this is 2, and this is 3. So we would have 1 and 3, and then the axis is set to 1. So we'll run that again. You see we have 9630, and then we have 3, negative 2, 0, 0. Now what happens when this indices is 2D? So let's simply copy this again and paste this out here. So let's suppose that instead of 1, 3, we have 1, 3, and then let's say 1, 0, or let's say 0, 2. Well, let's change the order to 0. So we have 1, 3, and 2, 0. Close that, and that's fine. Okay, so instead of 1, 3, we have 1, 3, 2, 0. So let's see what we have here. Let's change the axis to 0, run that, and axis 0. So you would see that it's going to be similar to what we've seen already. So here we have 1, 3. So and because we specified the axis to be 0, we're going to pick along the rows. So here, because we've selected the axis to be 0, we would have 1, because this is 0, this is 1, we have this 1, we have 2, then we have 3. So you see that we have this here 1, and then we have 3, which is gotten from our input. Now when we have 1, 3, 2, 0, you see that is similar. We have the 1, we have the 3, and then 2. You see this is 2, because this is 0, 1, 2. This is 2, 1, 3, 5. So here we have 1, 3, 5, 0, 1, and then 0 is 2, 9, 0, 3, 0. So 2, 9, 0, 3, 0, exactly as we would expect. And that's how the gather method works. Now another method which is similar to the gather method is the gather ND method. And the main difference here is that the gather can do this across multiple, or rather the gather ND gathers across multiple axes. So it can gather elements of a matrix instead of a row or a column. So let's take a simple example to illustrate how the gather ND works. Here we have TensorFlow gather ND. Well, let's just copy this. One thing you should note is the fact that it doesn't have an axis. You don't need to put an axis. So because as has been described here, it gathers across multiple axes, so you don't need to specify a given axis. So now we have 1, 3, 2, 0. You see that. Well, let's run this. Let's have here gather ND, run that. Let's see what we get. You see we have negative 2, 1. Now the reason why we have negative 2, 1 here is simple. What this gather does is it gets, like here we have, well, let's put this up so it's closer to our B. Okay, so here we have, let's rearrange this. Here we have 1, 3. So unlike the gather, which is going to say, for example, we gathering along the rows, then it means that we could pick the first, and then we pick the third. Here we are going to pick the elements directly. So when you specify 1, 3, it's going to go 0, 1, and then 0, 1, 2, 3. That's how we have negative 2. And then when you specify 2, 0, it's going to go 0, 1, 2, and then 0, which is 1. So that's how we get this output. Now if you want to get something similar to this 1, 3 we had here, what you will need to do is take this off. So now it's 1. It's going to pick all the row, and then you will take, or you take here 3, put here 3. So you're also going to pick the third row. We run that, and you see we get exactly what we got with this gather while specifying here 1, 3. So you see that while the two methods are used in gathering some elements from the inputs, they have different ways of functioning. In this new section, we shall be working with ragged tensors. And so we shall understand the reason why we need ragged tensors and also how to create them very easily. So let's get back. Let's suppose we have an A TensorFlow constant, and then here we have another array. So we have 1, 2, 3. Well, let's just end like that. And then here we have 4, 5, 6. Let's close this. We have 4, 5, 6. And then we have 7, 8, 9. Okay. So here's our input. We could print out A, and then print out, well, let's just print out A. Now once we print out A, here's the output we get. we could suppose that we modify this. So let's change that and change this. Okay, so now our row has 2 columns, and the second row has 3 columns, while the last row has only a single column. Let's run this again. You see that obviously we get an error, can't convert a non-rectangular Python sequence to a tensor. So the number of columns has to be constant across the rows, and the number of rows have to be constant across the different columns, so that such that we have a rectangular array or a rectangular tensor. Nonetheless, in some cases, you would need this kind of data. That is, you would need data where some rows will contain shorter columns as compared to the others. And so the way we deal with this is we convert this to racked tensors, or we just simply create a racked tensor. So here we have racked instead of the TensorFlow constant. Now we have TensorFlow racked constant. So we run that again, and you will see that we have a racked tensor. Now these racked tensors have different functions. Like we've just looked at a constant, which constructs a constant racked tensor from a nested Python list. We could also have the Boolean mask. So let's just check out the Boolean mask, and you would feel free to check out the others later on. So for the Boolean mask, let's take out this example from here. We have the data, and then we have the mask. There we go. Let's copy this. Let's copy this other one, because here we have this non-rectangular list. So let's copy that, and then we could simply paste this out here. Okay, so now here we have this racked tensor right here. We have these 2 racked tensors. Let's see, this is the input racked tensor, but this is the mask. So what this mask does is simple. We are going to keep all the values. So let's run this so you see the output. F is not defined. Well, F is false and T is true. So let's get back, and then let's say here we have false, false, true, false, true, and then true. Okay, run that again. There we go. So you see that for every position where we have false, it's taken off. So here we have 1, it's no longer there. 2 is no longer there because we have false. 3 remains because we have true. So you see, we're left with this 3. And then for the next, this 4, false, so it's taken off. We have this empty list, and then we have the next true. So 5, 6 are maintained. So that's it for this Boolean mask method, which we have seen from the documentation. You could check out other methods like this cross-hashed, range, and so on and so forth. So we could check out those different methods. The simple way we could check this out is by going through these different examples. So right here we have our values. You see 3, 1, 4, 1, 5, 9, 2, 6. So when you have this rack tensors from row splits method, and you specify the row splits, the way this is done is simple. We start from 0 and then we go to 4. So you see, when we have row splits, start from 0, you go to 4. So we have 0, 1, 2, 3. See, we have 3, 1, 4, 1. See that? And then let's copy this and run the code here. When we specify the row splits and we go from 0 to 4, this simply means, just like with a range, we're gonna have 0. So we'll take 0, then we'll take 1, then we'll take 2, then we'll take 3. So we go from 0 to 4 minus 1, and that's why we have 3, 1, 4, 1, which we have here. And then for the next, we're gonna have from 4 to 4 minus 1. Is basically telling us that we are not going to have any elements at this position, and that's why you see we have an empty list. Then we go from 4 to 7. 4 to 7, we would have 4, 5, 4, 5, and then 6, because we're going from 4 to 7 minus 1. So here we have 5, 9, 2, 5, 9, 2. Then we have 7 to 8. So we go from 7 to 8 minus 1. So we add 7, and that's 6. That's a year. Then finally we have 8 to 8. So 8 to 8 minus 1 is empty. So that's why we have this empty list. So that's it. That's how we read this row splits. Now for the row lengths, we'll take this off. For the row lengths, we simply look at this 4 and say, okay, we're going 1, 2, 3, 4. That's it, the length. And then the next is 0, so we have an empty list. The next is 3, so we take the next 3. That's it. The next is 1, we take this 1. And finally, we have 0, empty list. So we see that whether row splits or row lengths, we're able to generate the same output. Well, let's just let this be. That's fine. Then we go to value row IDs. So for value row IDs, we're going to say this 1, this 3 we have right here is going to be part of the 0th row. So that's where this row ID comes from. This 3 is going to be part of the 0th row. So that's why we have 3. 1 is going to be part of the 0th row. That's why we have 1 in the 0th row. 4 is going to be part, and 1 is going to be part. So that's how we have this 3, 1, 4. And then if you notice, we skip 1. What this means is we have no element belonging to the row 1. And that's why we have an empty list. And then we now look at 2. This next 3 elements belong to row 2. And then we have 3, meaning that this next element belongs to row 3. And then we have no 4. So there is no elements in the row 4. Now specifying number of rows here is important, because if we just take this off, or let's just say if we have, considering that we have 4 rows, then you see that there we do not have this last empty list. But when you say we have 5 rows and that you don't see the 4, and then you don't see this 4, it means that that's an empty list. So that's it. For the from row stats, it shows us where the row starts from. So this row starts from position 0, and then the next row starts from position 4. So this is it here, starts from position 4. The other row starts again from position 4. So because these two start from the same position, it means that there's a row which is empty, and that's how we have this 592, because the next starts from position 7. So this 6, and then the other one starts from position 8. So here we have 0, 1, 2, 3, 4, 5, 6, 7, but there's no position 8, so we have an empty list. Now we also have this row limits. Here instead we're looking at where the row ends. So the first row is going to end at position 4. It's going to end here, 0, 1, 2, 3. Well, when we say position 4, it's actually 4 minus 1, so it's 0, 1, 2, 3 ends right here. And then the next one is going to end at that same position 4. And because it ends at that position 4, we are going to make it an empty list. So that's why we have the empty list, since it ends at the same position where the previous one ended. So that's why we have the empty list. Now for the next one, we have 7. So 0, 1, 2, 3, 4, 5, 6, 7. Obviously 7 minus 1. Remember, when we generally have start to end minus 1 actually. So when you say start end, it's actually start end minus 1. That's why when you dealing with this limits, that's with the ends, we take instead of minus 1. So we get right up to this position, because it's 0, 1, 2, 3, 4, 5, 6, right up to position 6. We stop there and we have this 592. Then we have 8. So we go 0, 1, 2, 3, 4, 5, 6, 7. 8 minus 1, obviously we have 6. And then the finally we have this empty list, because these two match. So that's it. The next we have this uniform row length. So if we want to have a uniform row length, then it simply means that all this would have the exact same length. So we have 3, 1, 4, 1, 5, 9, and 2, 6. Well, this is 2, 4, 6, 8. So let's say we had 7 here. See well, let's take the start end from here. Run that again. We're having this error because the row splits here doesn't make sense without taking into consideration the fact that we have added an extra element. Run that again. For that was fine, but we still have some errors here. Anyway, we don't want to check that out for now. We just wanted to test out this last one. So let's comment all this. Let's just cut it out, run that, and we're getting an error. Oh, the uniform row length has to be specified. So if you specify that, you see now that we have the output as expected. So let's get back and take this off, run that again, and that should be fine. So that's it for this section on ROC tensors. See you in the next section where we will deal with the string tensors and variables. Many times in machine learning, we have to work with tensors which contain so many zeros. And so in these cases, TensorFlow defines a sparse tensor, which helps to represent in a more efficient manner these tensors which are sparse, which contain so many zeros or way more zeros compared to the other non-zero values. So here we could have our sparse tensor, TensorFlow sparse tensor. And then you will notice how we specify this indices. Right here we have this indices, and then we have values, and then we have the den shape. So what this simply means is we're going to generate an output. I could change this to, let's say, 5 by 6. There we go. So we have an output which is going to be of shape 5 by 6, and then at the position 0 0 we would have the value 1. Then at the position 1 2 we would have the value 2. So we could change this value to say 9. That's fine. Let's say 5 2, and then we run that. So let's have sparse tensor. Yeah, we're getting an error 5 6. The den shape should be 5 by 6. So let's run that, and we have sparse tensor. So you could see here that we have this sparse tensor already as we've defined. We have the indices, we have the values, and then we have the den shape. You could also do TensorFlow sparse to dens, and then pass in the sparse tensor. So you get the actual tensor which we created. So let's get the error. We have 5 6. 5 2 is out of bounds. When you have this, well, that makes sense. When you have a shape of 5 by 6, you wouldn't expect to have this position 5 2. So let's run that again. Then we get our sparse tensor. So as you could see, at the position 0 0 we have the value 1. See that? Value 1. Now let's change this value to 5. Run that again. You see now that at the position 0 0 we have the value 5. At the position 2 5, that's 0 1 2, and then 0 1 2 3 4 5, we have the value 9. See? So this tensor, which originally which has many zeros and very few non-zero values, can now be represented as a sparse tensor, and hence permits us carry out computation much more efficiently. In this section, we'll look at how TensorFlow deals with strings. So TensorFlow has this TF strings module, and which contains these different methods, which you could see right here. And the way a TensorFlow string can be created is very easy. So all we have is just the same syntax. Let's say here we have TensorFlow tensor string, TensorFlow constant. So it's the same syntax. And then in here, if we have a 1D tensor of strings, you just have to say I am and then string. So there we go. We have I am a string. We have tensor string, and you see now that we have this tensor which is of type string, and it's a 1D tensor. So we have a shape 3. Then here we have the actual values in our string. So we have I am and then string. Then we have different methods which we could use. So let's take for example join. It performs element-wise concatenation of a list of string tensors. So we just need to specify the separator, and that's fine. So we have tensor string, and then we have this list, and you see how it generates the output, which is now concatenated. So let's test this out. Let's say we have let's get back and check out the signal or the syntax again. So TensorFlow strings join, it's fine. We have TensorFlow strings join. We have tensor string, and then we have the separator, which we could put set to plus. So let's run that and see what we get. See, I am a string now separated with a plus. Now let's say we have tensor string 1 and tensor string 2. So let's just copy this and repeat that and say I am let's say not a string. So that's 2. Here we have 1 and then we have 2, and then here we put this in this list. So we have tensor string 1 and tensor string 2. There we go. So run that and you see how we have this I am concatenated with I am. So you have I am concatenated with I am, and then we have a concatenated with not a plus not a, and then we have string concatenated with string, still the same output shape. We have many other methods. You have the length, obviously that gives you the length of the string. You have string, byte split, format, and so on and so forth. So you could feel free to check all this out. Nonetheless, in this course, wherever we'll need to use any of these methods, we shall explain them so that you understand exactly what we're doing. You could see here, for example, that this string can convert your input, which initially was an int, into a string type. So feel free to check out all other methods. We're going to move on now to TensorFlow variables. A variable maintains shared persistent state manipulated by a program. So the variable constructor requires an initial value for the variable, which is in this case a tensor, which can be a tensor of any type and shape. Then this initial value defines the type and shape of the variable. So after construction, the type and shape of the variable is fixed. The value can be changed using one of the assign methods. Now that said, if we consider our model to be, let's say, this block, and we have some input data, and let's say input data and some output data, and then in our model we update, or we have our weights. We have our weights which we want to update based on this inputs and this outputs. These weights can be represented as TensorFlow variables. Let's see how we could create one very easily, and also how to update or modify its values. So here we have x, TensorFlow, that's a tensor. We have x 1 2 3 4 5, and then we create xvar. So this is our TensorFlow variable now. TensorFlow variable, and initialized or is initialized with the value x. So we run that too, and then we have xvar assign. Oh, let's first of all print out xvar, or let's print out x and then xvar. You see how we have x, which is our tensor, and then we have xvar, which is a variable. See, notice how it takes the exact same shape of the tensor which was used to initialize it, and also the values are the same. So that's it. Now let's do xvar. Let's modify the value. So we have xvar assign add. So also note that all these different methods like assign add, assign sub, I found the documentation, and you could feel free to check them out. So we have assign add. Let's say assign add 5. Let's run that, and we are given a variable with shape 5 using the tensor with shape with an empty shape must be equal. So let's get back. We have that. Let's add 5. Still doesn't work using tensor with shape 1. So this shows us that it doesn't take into consideration broadcasting. So we'll have to manually write this out. 5, 5 and 5. Run that again, and then you see we have this our new variable where we have added up all those different values. Could change this to sub. Run that again, and there we go. Well, we did sub of xvar. Okay, since we had xvar already added, now when you do sub, it gets back to its original value. If we run this sub again, you see we have now negative values. You could also just directly assign values using the assign method. So let's say we have xvar assign, and then we do let's say 5 5 5 5. Run that again, and you see now that the values are directly assigned. So that's it for this section on tensors and variables. See you in the next section where we shall dive into linear regression. Hi there, and welcome to this new section in which we shall be building a linear regression model for predicting the price of second-hand cars. In this section, we shall make use of different features like the number of years the car has spent on the road, number of kilometers covered, the car rating, the car's condition, the current state of the economy, the top speed, the horsepower, and the torque in order to predict the current price of that car. At the end of the section, we shall build our model such that we are able to obtain the model's predicted prices to be very close to the actual prices. Like you could see in this plot, we have the predicted prices in orange and the actual prices in blue. That said, in this section and in other machine learning projects we shall be working on, we will make use of this machine learning development life cycle. So we'll start by defining the task. Once the task is defined, we will try to understand and prepare the data. Then once this is prepared, we will dive into building our model. After building the model, we shall come up with a way of measuring the error the model is going to make. And then from here, we'll dive into training our model and optimizing it. Once the model is trained, we shall measure the model's performance. Based on the model's performance, we shall then carry out corrective measures in order to better that model. So now if we consider a simplified version of our task, here we have only a single feature. We have just this one feature right here, and then we have our price in K dollars. Then we would train our model with this known input output pairs, which we have right here. Now our input in this case is just the horsepower, but as we had seen already in the notebook, we actually have many more inputs. So we have years, kilometers, radians, up to the torque. So just for simplicity purposes, we've decided to select only one input feature. So here we have our inputs, that's it. And then we have our output, which is the current price. So getting back to our board, what we're saying is we are going to train our model on this input output pairs. That's the horsepower and its corresponding price, horsepower corresponding price. And then once we're done with the training, we shall then be able to predict the price of a car when given only the horsepower. So when given a value of 80, we should be able to predict that the price is let's say for example X K dollars. Now we could represent this table right here by a plot like this one to the right, where we would have on the x-axis the horsepower and on the y-axis the price in K dollars. And the idea now will be to come up with a mathematical function like say a straight line, y equal mx plus c, where the values of m and c are going to be chosen after we've trained the model on the different input output pairs xy. So after training on xy, the model will learn to choose the best m and c which suits this data set, such that if we have a new point, let's say if we have some new points around here, we shall be able to estimate the price based on the horsepower. And so now if we come up with this function with the values of m and c gotten after training the model, we get a new input like this one. We shall make use of this to obtain the price of the car. Hi there, and welcome to this new section. Previously we saw that we could train a model such that it takes in input output pairs, that's this input output pairs, and then later on when given new data, is able to tell us what the price of the car is based on this new data. And what this tells us is our model relies a lot on the data for performance. And so in this section, we shall be focusing on how to prepare our data so that the model makes use of it for training. So we're going to head over to kaggle.com, and more specifically on Mayank Patel's Kaggle dataset entitled Second-Hand Cars Dataset. Now this dataset is what we'll be using in this section. So here we have the different features. You go from the ID to on-road old, on-road now, years, kilometers, ratings, and so on and so forth. You'll note that we are not going to make use of the on-road old and on-road now, as those two features aren't very clear. Generally in machine learning, we want to have an idea, or better still, know in detail what the features we're working with are. So that's it. You could open your detail. You have the details of the different features. So for the ID 1, we have the on-road old 535,651. On road now, we have number of years. So this tells us that this car with ID 1 has spent 3 years. The kilometers, the number of kilometers covered is 78,945. The rating is 1, the condition is 2, and so on and so forth. So we have all this information right up to the horsepower. Then if we click on column here, you have this sort of summary. So for every feature, let's take the number of years, for example, you have the number of valid samples we have in our data set. We have 1,000 valid samples. The number of mismatches, 0. Number of missing samples, 0. The mean is 4.56, and the standard deviation is 1.72. Check out another feature like the number of kilometers covered. You have a mean of 100,000, while standard deviation is 29.1 thousand. So what this simply means is that most of the values we have will lie in the range 1,000 minus 29.1 and 1,000 plus 29.1. Our normal distribution curve will look like this, where we have the mean at 100,000 and standard deviation, which is 29.1, meaning that the values falling within the range 100, because here we have 100 minus 29. Obviously, this is in thousands since we have K. So 100 minus 29, and here we have 100 plus 29. That's essentially about 81. It's about, not actually 81, 71. So we're going from 71 to 129. So what this means is most values fall within this range, or the fact that a value is in this range means that it has a higher probability of appearing in our data set. At this point, you could go ahead and click right here and download this data set. So it's just 25 kilobytes. You have your train.csv file downloaded. Then when you download and extract that file, you could simply just drag this into your Colab notebook. So notice how here you have this drop files to upload them to session storage. You drag and drop in here. You should also note that once you disconnect from the session, you're going to lose this file. So it's only in the session that we have access to this file. And so with the file copied in here, we could start with importing. So let's import TensorFlow as TF. This is for working with models, so modeling or deep learning modeling. Then we have import pandas as PD. This will be used for reading and processing data. And then we have import Seaborn as SNS. This will be used for visualizations. Now we could run this and then click open our train.csv file. You see, we have this train.csv file right here. Could show 100 samples. You see that? we have 1 to 100 of 1000 entries. So we have 1000 different input output pairs. Is exactly the same as we had seen on Kaggle. So here we have the ID, we have on-road old, on-road now, years, kilometers, and so on and so forth. Up to torque, that's for the inputs, and then now we have the output, which is the current price. So with that, we close that, and then now let's copy this path. So we copy that path, and then we do data, pandas, read CSV. We specify that path. So let's just create a file path here. File path. There we go. We have our file path. Now we specify our file path, and then we also specify the separator. So here we have the CSV, which stands for comma separated values. And here, given this separator, a comma simply tells us that each and every value is separated by a comma. So that is that simple. So let's run this, and then we have data head, and we see what we get. Open this train.csv file with your text editor, and one thing you will notice is the fact that you could see how all the elements in a given row are separated with a comma. So we have the ID here 1, we have on-road old 535,651, which is this. Let's get back. We have the on-road now 798,000, that's it here, and so on and so forth. So you have 3, you have the kilometers. You could scroll so you get to the current price. We have the current price 351,318, and this comma tool separates the header rows different columns, like the VID, on-road old, on-road now, up to the current price. If you happen to work with CSVs which are separated by something other than the comma, like say for example a semicolon, then you would want to change the separator and have the semicolon. Now with that said, let's get back to our CSV file. This is just an extract of 21 samples. Here you could see already that this CSV file contains our data set. Looking at this, we could break up our data set into the two main parts. That's the inputs and the outputs. So we have, let's just take all this. We have here the inputs right up to this point. We have the inputs, see, and then we have to the right we have the outputs. So if we have 21 samples, like in this case, then it means we have 21 rows. So we have a 2D tensor, which is 21 by number of columns. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 columns. While on the side of the output, we still again have 21 rows, but this time around we have only a single column. Now we could generalize this, so we could go from 21 to n. So depending on the number of samples we have, we could have n, and then we have 11, and then here we have n by 1. So we have this 2D tensor, which is n by 11, and this other 2D tensor, which is n by 1. After load the data, you could still check out this shape. Now note that this shape contains both the inputs and the outputs. So the n is maintained all through because we have 1000 samples, but now we have a combination of the inputs and the outputs. So we have 11 plus 1, which is 12. From this point, we'll make use of Seaborn to carry out some visualizations. So we'll make use of this pair plot method from Seaborn and compare the different features. So we have number of years, kilometers, rating, condition, up to torque for the inputs, and then for the output we have the current price. Anyway, in this pair plot we are comparing each and every feature with the others. So we'll compare years with all those other features, and for example economy with all the other features. So let's run this and see what we get. Here's the overall pair plot we get in, and if we copy this on our board, you see that for each and every feature we have a plot which shows how that feature is related to the others. So this plot here, for example, shows how years are related with the feature years with itself, and then this plot shows how years is related with this other one, kilometers. So let's just look at this. Let's zoom in and take a closer look at this. Here we have years, and here we have kilometers. So the way kilometers is related with the number of years tells us that whether a car has been used for maybe say 2 years or 6 years, depending on the driver, we may have a higher value for the number of kilometers covered or lower value. So if we have a car which is new or brand new, and that is used maybe to go for work and get back home, then we could fall around this range here. You see, fewer kilometers covered. But if you just bought a brand new car to be used as a taxi, then you would fall in this range, as you're basically using the car for the whole day. Also, you may have bought a second car or a third car, so you have maybe 3 cars, and you rarely use a third car. So even after 7 years, the car hasn't run so many kilometers. On the other hand, even with normal usage, after 7 years, we expect that the car has run many kilometers. So actually, this shows us that the number of kilometers covered depends on the usage of the car. And so whether the car is 1 year old or 7 years old, the usage or the number of kilometers covered may be different. One other feature which we would like to visualize is this one, comparing the current price and the number of kilometers covered. You'll notice that as there's an increase in number of kilometers covered, the price tends to drop. And unlike these other features where we don't have a direct or inverse correlation with the current price, if you increase the number of kilometers, or if the car has run through so many kilometers, then the car's price tends to drop, regardless of the usage of the car, regardless of the type of car, or any other factor. So this particular feature is really important. With that said, you could feel free to check out the Seaborn documentation to learn more on how to visualize data so that you could take much better and quicker decisions. Let's go ahead and add this header right here. So we would have data preparation. There we go. We have that header. Before we go on to extract the data and create the separate inputs X and output Y, we are going to shuffle this data. Now the reason why we're shuffling this data is because we want to avoid the model being biased based on the order in which the data was collected. So we shall simply create a random shuffle data. So here we have shuffled data, TensorFlow random, shuffle, and then you pass in the data. So that's it. Now if we do shuffled data head, now if we get the first 5 elements of the shuffled data, first 5 elements, and then we compare with the data first 5, you'll find that the ordering is going to be different. So here, unlike the data which is 1, 2, 3, 4, 5, the shuffle data is 288, 201, 882, 557, and 313. So this shows us that our data has been shuffled. Then, since we want to get X and Y, we'll simply have our X. Now this X is going to contain the, if you look at data, let's just print out data head here. So we have data head. There we go. Our X is going to contain just some parts of our data, of our shuffled data. First of all, it's going to contain all the rows. You remember we had seen this already in the section on tensors and variables. So we get all the rows, and then once we get all these different rows, the next thing we'll do is to collect or select the specific columns. So here we want this column, this is a zeroed column, 0, 1, 2, and this is 3. Because we don't want on road now, we don't want on road old, and we don't want the ID. We want years up to the torque. So we want 3 right up to the end. And then for Y, we want the shuffle data. And here we want everything again and just the end. So let's run that, print out X, and then we print out Y. We have your X, which is of shape 1000 by 8, and we have Y, which is of shape 1000. This is a 1D tensor. Let's just print out the shapes so you could see that. We have Y shape and X shape. Now we want our inputs, that's X and Y, to be 2D. So we're gonna go from this 1000 shape to 1000 by 1. So that's what we want to do, and we're gonna make use of the expand names method. So let's get back here and we do TensorFlow expand dimensions, and since we want to add this to the end, we're just gonna have -1. So we run that again, and then let's take this off, and then we print out the X shape and Y shape. In general, before passing our input data into our model, what we want to do is to normalize this data to speed up the training process. And so we are given this input data, let's call that X. We shall subtract each and every one of those values by a mean value and divide by a standard deviation. And so what the model is going to get is actually an X prime, which is equals the normalized or which is the normalized version of our X. Now the way we could get the mean and standard deviation is by simply going through all those different values, getting the mean and that standard deviation. Now you should take note that we also don't want to include data which the model will not see during training. So we only want to get this mean and the standard deviation from data the model is going to be trained on. Practically, the way we could normalize our data is by making use of TensorFlow normalization layer. So you see here we have the simple definition, we have this arguments which are well explained, and so you could always feel free to check this out, and then you will have some examples. Now let's get back here, and then we're going to import TensorFlow Keras layers, or rather from TensorFlow Keras layers, we're going to import the normalization. There we go. So we import that. Let's go down and then show how we could make use of that normalization layer to normalize some random data. So here we have our 1D tensor, let's say 3, 4, 5, 6, 7. There we go. So we have this 1D tensor, and then we shall define a normalizer. We have our normalizer, our normalization. There we go. And then what we do is we say normalizer takes an A. So let's print it out and see what we get. Let's print it out. You can see that when we don't specify any value here, we get returned the exact same input. Now let's modify this and say we have 5 and 4. Or let's be more specific. The mean is 5 and the variance is 4. Note that the standard deviation is the square root of the variance. And so if you are doing x minus the mean divided by the standard deviation, is really just x minus the mean divided by the square root of the variance. So let's put these brackets here so that clearly x minus mean divided by square root of the variance. And so given that we'll specify the variance and the mean now, let's run this again, see what we get. You see we have -1, -0.5, 0, 0.5, and 1. Now if we try to test this out, let's get back. Let's say we have let's take 3. So here we have 3. 3 minus the mean is 5, then divided by the square root of the variance, which is 2. So that gives us -1, and that's how you have this -1 right here. So when you specify this mean and the variance, when you specify the mean and the variance for each and every value, we're going to run this computation, and the values are now going to be normalized. So that's it. We could also test this out for 2D tensor. Let's get back here. We have this 2D. Let's say we have 6, 7, 8. Well, let's just say 4, 5, 6, 7, and 8. Close that. Run that again. See, we have as we had this previously, but now for this other ones we have -0.5, 0, 0.5, 1, and 1.5. You could test out for 8, for example. If you have 8 minus 5 is 3, divided by the square root of the variance, which is 2. 3 divided by 2 is 1.5. That's how we have this 1.5 right here. Now when working with data, we generally don't know the mean and the variance up front, and so because we don't know the mean and the variance up front, we want to be able to calculate this automatically. And so what we could do is we could allow our normalizer to adapt its mean and variance based on the data. So let's get back here and say normalizer adapt to A. So we want our normalizer now to adapt to A, and so now we don't need to have this 5 and 4 again. So let's run this. You see we have these values, -1s and then 1s. Now let's explain why we have these values. First of all, getting back to the documentation, you would find that we have this axis set to -1 by default. So if we set the axis, if we change the axis value, if we say axis is 0, you would find that we'll have completely different values. So having the axis or not putting any value is the same as having the axis to be -1. Now when for a 2D tensor like A, you specify that the axis is -1, it means that you are going to compute the mean and the variance along the columns. Remember, we have A has shape 2, because we have 2 rows and then 5 columns. It has shape 2 by 5. And so when you specify axis to be -1, that's you specifying the columns. What you're saying is you want to compute the mean along those different columns. So for this first column, 3 and 4, our mean is 3.5, which is logical, because if you do, let's get back here, if you do 3 plus 4 divided by 2, you have 3.5, and then the variance is going to be 0.5. So what we're saying is, if we have these two values, that's 3 and 4, then our mean here would be 3.5. Now to the left, the value we have is 3, and to the right the value we have is 4. Now what separates 3 and 3.5 is 0.5, and what separates 3.5 and 4 is also 0.5, and this happens to be our standard deviation. So in this case, our standard deviation is equals 0.5, while the mean here is 3.5. And so now if we do 3, let's take this off. If we do 3 minus 3.5 divided by minus 3.5, then all of that divided by 0.5, what we're gonna have is negative 0.5 divided by 0.5, which is -1. And then if you do, let's just copy this. If we do 4 minus 3.5 divided by 0.5, you would have 1. So that's how we obtain these values, -1 and 1. Now for the rest is a similar situation, because we have 4, 5, the mean there is 4.5, and then we have 4, and then the standard deviation is 0.5, because the gap between 4 and 5 is 1, and then when you take 1/2, you have a standard deviation of 0.5. Now if you replace this by 5, see again, and 4.5 here, we have -1, 1. So that's how we obtain all this. And now let's add another, let's get back and then add another row. So let's say 9, 1, 2, 4, and then 0. Run that again. we're getting this error. Well, let's take this off, run that again. You see now that we have our inputs, which is this, which have now been normalized. And so now we could go ahead and normalize our x. So we're going to create x normalized. We could just have this. We have take that off. We take a off, and then we have normalizer. We adapt our x, and then we'll have this to be x normalized. X normalized is simply normalizer, and we pass in the x. So that's it. So take that off, and then let's print out x normalized. X normalized. There we go. We now have the values of x which have been normalized. We still have our 1000 by 8 shaped tensor. So that's it for this section on data preparation. We are now going to move on to modeling. In this section, we shall be looking at modeling and how to build simple machine learning models with TensorFlow. Now, in our specific case, our model turns out to be this function y equal mx plus c. So here's our model. This is actually what's in this model block we have here. And what we want to do is put in or pass in this data into the model such that the model learns the right values for m and c which best represent our data. So let's suppose that we have we randomly pick m to be 0. Let's randomly initialize m to be 0, and then we'll also randomly initialize c to be 0. In that case, if here we have 0, then we shall take off this line. Let's take off this line, and now we'll have a new line which will instead be something like this. Well, actually this is 0. This is the line y equals 0 because m is 0, c is 0, so y equals 0. So what we'll be saying is this line should represent our data. But looking clearly at our data, this line actually doesn't represent our data properly. Now let's change this again. Let's say m is for example 1. So let's get back and set m to be 1. So here we have m now, which is 1. If m is 1, then y is equal 1 times x plus 0. So y equal x. The line y equal x actually looks something like this. We'll have a line like this one, which now does a much better job as compared to this other line when it comes to modeling the data we have at hand. Now, this doesn't mean this is the best possibility, as we could have other possibilities. We could have a line like this, we could have a line like this, we could even have lines like this, and so on and so forth. So the idea here is that we want to get those values of m and c which best represent our data. Now it turns out that the m and c we're talking about here are what we'll call the weights and the biases of the model. So in this case, our m is the weight, and then c is the model's bias. And so if you get that a model has, for example, 7 billion parameters, then it means that we have 7 billions of these kinds of weights and biases which are being tuned such that the model represents the data properly. That said, let's get back to the code and create a simple model. So here we have our model, TensorFlow Keras, sequential, and then we have this list. So the first thing we'll put in this list is the normalizer. We have our normalizer because whatever value of x or whatever inputs we're passing in, we want them to be normalized first. Remember, the normalizer was a layer. So you could remember, you could check this from here. We imported normalization from our layers, and then we adapted our normalizer to our data. Remember, we had done this here, and then we had adapted our normalizer to our inputs. And so when we get back here, you see we have this normalizer which is already adapted to our inputs. And then now from here we have a dense layer. It turns out that this dense layer is simply the y equal, or is simply the mx plus c which we spoke of. So you don't need to write mx plus c or some complicated math formula. All you need to do is specify, is just have this dense, and that's fine. Now dense is a layer, so here you also include dense on that, and that should be fine. So let's get back. We have our sequential API. This is sequential API, takes in normalizer and dense, and then we could run model summary. So we check out our model summary. You see we have our inputs, we have our dense layer, we have some parameter numbers or number of parameters here, we have total parameters, we have non-trainable parameters, and then the trainable parameters. We also have the amount of memory space this occupies. So this is just in bytes. Now it should be noted that using the sequential API is not the only way in which we could create models or machine learning models with TensorFlow. You have the sequential API. You also have the functional API, and then you have you could go through model subclassing. So subclassing. Now getting back to documentation, you could head over to TensorFlow and then Keras. Then you click here on sequential. And basically what this sequential API takes in is some layers, that's it, and its name. So you could get back here and then give this a name. Let's call this, yeah, as I said, we're taking the layers and the name. So we could call this first sequential API. Run that. And you notice how this name here changes. So let's get back to documentation. We have the layers, takes in the layers and name. And then you'll also notice that here the way it's defined is a bit different from what we just saw. So this is another way in which we could define or build up a sequential model based on the sequential API. So let's create a new code cell down. And then here we have our model, which is a sequential based model. Then we have our normalizer. So add normalizer, let's take this off. Then we have the dense layer, and then number of outputs of the dense layer is 1. Actually, the reason why we have this number of outputs to be 1 is simple. Remember we have this inputs, and then we have a single output. So here we have 8 inputs. Let's say 1, well, we have 1 up to 8 inputs. So we go from 1 to 8 inputs, but the output or number of output here is just 1. So because it's just 1, when you create in the dense layer, you just need to specify the number of outputs your model is expected to produce. And so getting back here, we'll just after adding all this up, we'll do model summary, and we get that model summary. So that's fine. You see we have the exact same model using the add method. So instead of putting all these layers in this list, you could make use of the add method. So if you're wondering why we choose the sequential API instead of maybe the functional API or the model subclassing, the answer is simple. We have a model which is made from stacking up different layers. So here we could consider this to be our normalizer layer. Let's enlarge this, it takes up more space. So our model is made of stacking up our normalizer layer. Let's copy this and paste it out. Well, let's take back that. So we have our normalizer layer, and then we also have our dense layer. So because our model is made of or is composed of these 2 layers stacked, we could make use of the sequential API, as this API suits this kinds of model configuration. So if we have, let's say, n layers, let's reduce this now. So we could have so many layers actually stacked. So far as they're stacked sequentially, then you could make use of the sequential API. For more complex configurations, you may want to work with a functional or model subclassing, but we're going to look at those in some subsequent sections. So we have this up to, let's say, n layers. See, we have all those different layers which could be stacked, and now we could make use of sequential API. Now, if you look at this model summary, you'll notice that we have, for the dense layer, 9 parameters. The reason why we have this 9 parameters is simple. We have an input. here which has with 8 different features. Our input was 1000 by 8, and so here we have 8 features. Now with those 8 features getting into our model, we have this actually x. We'll look at it as x. We're gonna ignore the batch dimension here. We ignore this dimension. We focus more on this one where we have 8 features. And then now when we taking this x, you would find that we would have a weight for each and every x here. Remember, this is x. This x we have here could be rewritten as x1, x2 up to x8. See that? You could put this in a vector where we have x1 up to x8. And so when we have this input, we could simply do m1 x1 plus m2 x2. This is the x1, this is the x2, which is from our inputs. So m2 x2, then right up to m8 x8, m8 x8. So all this here represents our mx, and then the plus c here is the bias. So we would have plus c, and now for our output we have our y, where y is simply equal m1 x1 plus up to m8 x8 plus c. So one thing you could notice already is the fact that we have 1, 2 up to 8 weights plus this bias, giving us 9 parameters. And that's why when you got back here, you see we have, or when you get back here, we have 9 parameters. For the normalization layer, since it's already been adapted with the data set, you have non-trainable parameters. So this represents the non-trainable parameters, as we don't need to update this as we train, because those parameters, that's the mean and the standard deviation or the variance, have already been adapted on the data set. That's why they are non-trainable, while these are trainable, meaning that we want to update them as we train our data. Another nice utility function which we could use is the TensorFlow plot model. So we could do TensorFlow Keras plot model, or it's actually Keras utils plot model. We specify the model. Then once we specify the model, we also specify the output shape. So here we have to file my first model png, and then we set the show shapes to true. So we have to file equals that, take that off, and there we go. So let's run that again and see what we get. You see we have this output now, which is this nice looking figure, which is the summary of our model. We could now we have this image right here which we could download. So that's it. We have seen how to create these kinds of summaries. We understand what each and every statement we have here means, and then we've seen how to make these beautiful plots. Now in the case where we didn't have a normalizer which already understands the data, given that it has been adapted on it, we could we'll need to specify our input layer. So here we have the input layer, and then we'll specify its shape. So here we give it 8. Notice how we ignore the batch dimension. See, we're ignoring this because this could take any value, as we could have or we could work with data in batches of 8. We could work in data of way more larger batches, and so on and so forth. And so because this actually varies or changes depending on whatever situation we're having to work with, we focus on the other dimensions. In this case we have 8. So there we have our input layer. Let's go ahead and import that. Input layer, run that again, and then let's run this and then see what we get. So we have here input layer, we put that comma, we separate the different layers because that's a list. We get an error, unrecognized keyword argument shape. Well, this is actually input shape, so let's change this to input shape, and that's fine. So you see that works fine. Now let's change this to 9, run that again, And you see we have an error because the normalization layer expects our input shape to be 8. Run that again, and we see our plot. Now notice how this plot has changed. Now we have 8 instead of known as before. So let's take off the input layer, run that. You see before we had known, but now we have known shape when we add this input layer. So this utils function understands that now we have input which are of shape known by 8 or batch by 8. So that's it for this section on modeling. We shall now move on to our next section, which is that of error measurement. Welcome to the section on error sanctioning. In the previous section, we saw how to build a simple linear regression model. In this section, we'll see how to calculate the model's error in order to permit it make update its parameters such that it makes such that this error is reduced. So let's get back here. We had this y equal mx plus c, and then we had this line, but again, this line could be just any other line depending on how we initialize m and c. So we could have this line, it could be this line, it could be this line, it could be this line, or it could be maybe say even this line. Now supposing that it is this line right here, then for each and every point, the way we are going to sanction the error or the model's error is by first of all measuring it. So we'll let's start with this point. For example, if we have this point here, what the model predicts is that the price, if you use the model's prediction and then you link this point up with the model's prediction, that's a straight line, then you would find that what the model predicts is actually this value. So the model predicts let's say a value of well, this prices go from 8 to 10. So let's suppose that this is a value of about 5, whereas it's supposed to predict 10, because here we have the true value. Let's take this, let's copy this and just drag it right here. So as we're saying, here we have the true value from this point. The true value is actually this 10, but what the model predicts is 5. And so now this difference of 5 is actually what we'll call the error. So there's this difference, that's the error. But it happens that this error is not always this large for all other values. If you, let's zoom in, you'll find that for this value, for example, for this specific value we have here, what the model predicts and its actual value is the same. Let's get back, copy this and paste out. So we have that here. So let's say the model here predicts 5.5 or 5.2. So here we have 5.2. Well, this is 5 here. Let's drag this down. So here we have this 5, and then just right beside it we have 5.2. So this is 5.2, and then this is 5. So what as we're saying, for this point, what the model predicts, that's when you link the point with the line with this function y equals mx plus c, you'll find that what it predicts is 5.2, and the actual value itself is 5.2. So what this tells us now is that our error is equal 0. So that's it. We have an error of 0, while just above here at this at the level of this point we have an error which is quite large, of about 5. Let's say there we have an error of about 5. Okay, so that's it. We see that depending on the point, we could have different error values. Now generally what we want to do is we want to get an average of all these values, and then that will be our overall error. So our overall error here will be for each and every point we have here, we will get their errors. So let's say we will take this point. You see when you link this up with a line, you find that what the model predicts here is this value, whereas the actual value is right here. And so the error is going to be this for this point, and you could repeat the same process for all other points. But what's important to note is the fact that the error of the model is going to be the mean or the sum total averaged of all these different points. Let's suppose that we had this line, something like this. So let's suppose that this line was like this. In that case, the error for all these values, you see that the error for all these values, when you compare, well, let's get back, you will find that when you compare this model here with this other model, the error here will be much larger than the error for A. So let's call this model A and let's call this model B. Our error for model B will be much larger, or let's say greater than, the error for model A. And this makes sense because for most of the points we have here, there are individual errors when we're using this method B is going to be much larger than the individual errors when we're using model A. Diving into some code, we get to the documentation. You have TensorFlow losses. Let's reduce this. We have TensorFlow losses, keras, and then we have losses here. We have this mean squared error. Let's click on this mean squared error, and it's going to be defined here. Compute the mean of squares of errors between labels and predictions. So that's it, simple definition. And then you have some examples. So just right here we have y true, and so what that means is, if you considering this example here, if you consider this example, its y true is 10, whereas what the model predicts is 5. See, so here is y true, it's going to be 10, while the y pred by the model is going to be 5. And then with this mean squared error loss, we'll be able to compute the loss very easily. So let's copy this, get back to our notebook, space that out, and you see here we have y true 0 1. Let's rearrange this, 0 1 and 0 0, and 1 1 and 1 0. So let's run this and then see what we get. Well, let's print this out. So let's have print that out and see what we get. So you see we have 0.5, and the way we could get this is simple. You have for each and every position, you compare the values 0 and 1. That gives you 0 minus 1, and the mean square error, as the name goes, is squared. So we have 0 minus 1, all of that squared. So we have that squared, plus is a mean, so it's an average. So we have plus 1 here and 1. So let's just copy this and paste out here, take that off. We have 1 and 1, or 1 minus 1, all that squared, plus for the next 0 minus 1, that's 0 minus 1, all that squared, and then here we have 0 minus 0, all that squared. So 0 minus 0, all that squared. Take that off, and we have 0. So all this is going to give us 1. This is 1 square. 1 plus 0 plus 1 plus 0, that's 2. And if you divide this by the total number of elements, we have 4. So this gives us 0.5. Now let's modify this slightly and say we will have 1. So if we have 1, then we would have 1 divided by 4, which should give us 0.25. Here, 1 divided by 4 should give us 0.25. Let's change this from 0 to 1. Now we have 0 minus 1. So here's 0 minus 1. And then this should be 1. This is 1 plus 0 plus 1 plus 1. So that's 3 divided by 4. Now we should have 0.75. So let's comment that and see what we get. There we go. You see we have 0.75. So essentially we have this error, which is for each and every point here, what the model predicts, which in this case is 5 actually, because when you make use of the line, you see it's 5. What the model predicts, that's 5, minus what the model predicts, minus what is actual, like minus the actual value. So that's y actual, and you take all this and you square. Then what you do is you repeat this for all the different points, and then you look for the average. So it's simply the sum of all this y minus y ace, all of that square. So you sum all those up, and then you divide by the total number of points or total number of samples n. In this case is say 1,000. Now the next problem we have with this mean square error is that it doesn't do well when it comes to dealing with outliers. A simple outlier we could detect by looking at this plot is this one right here. Why is this an outlier? The answer is simple. We have high horsepower, but we have low price. We would expect that the higher the horsepower, like most others here, we should have a higher price, just like as we've seen with all these others. So with these outliers, given that they deviate a lot from the usual pattern of the whole data set of different samples, using y minus y, that's y minus y, let's say y prime square, using all this kind of formula where we have y minus y prime square isn't the best. Here the error is much larger as compared to all the others. So here we would have an error. If we take this and paste it out here, let's try to link this up with our plot. So let's keep dragging this. See, we link this up, and then we drag this to up. There we go. You see that this error is much larger as compared to all the other errors. So compared to this, is much larger than this, much larger than maybe the error would have here, much larger than this error, and much larger than this error. And so because of that, the model will pay more attention to this outlier as compared to all these other points. And this is for the simple reason that the loss is going to be much higher, especially as it's going to be squared. So remember, if you have a square, you would have something like this, a plot like this. So if you have say an error of 3, well, you would have a square of 9. But if you have an error of 10, you have a square of about 100. So the gap you have here will be much larger as compared to the gap you have here. So this kind of outliers tend to trick the model into updating its parameters m and c based on its own particular loss when it's actually an outlier. So what we use in this kind of cases is we make use of the mean absolute error. So instead of squaring, we just simply say y minus y prime, and then we take the absolute value. So instead of this kind of plot, we would have a plot like this instead. And the difference now is that although we still have that error margin, so although the error the difference between the y predicted and the y actual is going to still be large, we don't have to square it, so it doesn't aggravate the situation. So that's it. We have this mean absolute error. Again, with TensorFlow, you could use that without writing any extra line of code. Now, if you want the best of both worlds, that's if you want to use the mean square error and the mean absolute error, then you could go in for the Uber loss. Now, with the Uber loss, with the Uber loss, it's actually a mixture of the two. So what we have here is, if we have if the error is too large, then we'll use the mean absolute error. So we just compare. If we have error, if our error is too large, so if error is large, then we use mean absolute error. And then if you have an error that is small or that is usual, like in the case of all these other points, if you have usual errors, then usual error margins, then you would go in for the mean square error. So in that case, if your error is small, then you will go in for the mean square error. Diving back to documentation, you have the mean absolute error just right here. This is the mean square error, square of y minus y prime square. or rather the square of y minus y prime. And then for the mean absolute error, compute the mean of absolute difference between the labels and the predictions. Now remember that the absolute value actually is x. Let's write that out in case you don't know. When you talk about absolute function, the absolute value is simply x if x is greater than 0. So if x is already positive, then it remains the same. But if x is negative, then you add a negative there so that it turns into a positive value. So in that case, the absolute value of minus 7 is 7, and the absolute value of 7 is 7. So that's it. We get back here. That's it for the mean absolute error. So let's get here. We have U-bar. There we go. We have this U-bar loss. Let's scroll up. Compute the U-bar loss between y true and y pred. So we have this parameter delta, and the role of this parameter delta is simple. The way we know that the error is large is by comparing it with that parameter delta. So if the error is greater than the parameter delta, then we consider that it's large and we use the mean absolute error. If the error is less than the parameter delta, we consider that the error is small and we use the mean square error. So getting back here, we have that. We should have an example showing that. Okay, this is it. You see we have x squared, that's y minus y prime square, if x is less than that parameter delta. Yeah, the note it as d. And if it's not, then we're going to use the absolute value. Well, looking at this here, this definition, it turns out that we made an error on the board, and it's actually not just the absolute value. So we have with the U-bar, if it's less than the delta, that is if the error is small, then we use the mean square error, y minus y prime square. But for the U-bar, it's still the absolute value, but now we subtract half of the sigma and then multiply by sigma, so delta. So this delta comes in again in the formula. So it's not just y minus y prime and then 1 times 1 over n. Anyways, the good thing with TensorFlow is you don't really need to dive into all these details before making use of the U-bar loss in practice. So here you see how to make use of it, usage with the compile API. So after you've created a model, you now compile that model, you specify the loss, and you see you specify the optimizer, which we shall look at in the next section. So let's just copy this and then get back to the code. Take this off. We have now model compile. We have the optimizer, SGD, and the loss, which is the U-bar loss. We've just looked at error sanctioning, and that has permitted us to see how this model A with parameters M and C, different from this other model B with its own parameters M and C. Let's say, for example, given that we have this line Y, so M is, say, for example, 0 and C 3, and then this other M could be 2, and then C could be, let's say, 4, with the model B having a higher loss or having a higher error as compared to the model A. Now, the whole idea of training optimization is simple. What we want to do is take a model which has been initialized, that's take a model whose parameters have been initialized to some random values, like for example 0, 3, or even 0, 0, or whatever random values, and then update those parameters such that we get a better performing model like this one here with parameters 2, 4. So let's suppose that we randomly initialize our model to have M equals 0 and C equal 3. Then we want to update this such that 0 turns to something close to 2 and 3 turns to something close to 4. Now, to carry out this transformation, we shall make use of an algorithm known as the stochastic gradient descent. This algorithm is quite simple. Suppose we have a weight. This weight could be M or C. That's, we have a parameter. Let's call this parameter, or let's say this initial value. We are going to subtract, we're going to take this weight minus learning rate times the partial derivative of the loss. This loss is the same as the error we had computed with respect to that particular weight. So let's have this. This is minus all this here. And when you have, this is I, so this initial weight, or the initial weight value is here. So we have wi minus learning rate times the partial derivative of L, the loss, with respect to I. And then this now gives us WF, that's its final value. So we could go from, if we pick out some, let's pick out some values. Let's suppose that our W initially is 0 minus, let's say a learning rate of 0.1 times a partial derivative of, let's say, minus 20, will now give us a WF, which is 2. And that's how we could move from this initial W to this 2. But it should be noted that in practice, we don't generally just move from a very poorly performing model to one that is very well performing in a single step. So we are going to go through this same algorithm in many steps. So we could start with, let's get back, we could start with this partial derivative of let's say even 5. So here we have 0.1 times 10 is, times 1 times 10 is actually 1 divided by 2, that's 0.5. So we could go from 0 to 0.5. You see, we go from 0 to 0.5, and then in our next step, because now our W has turned to 0.5, that's from 0, we went from 0 to 0.5, we will replace this 0 here with 0.5. So instead of having 0, we would have now 0.5. The learning rate is still the same, although it could change as we keep training. And then this partial derivative, we could say, for example, that is 10. So let's, this is 0.5. Let's take this off here and then replace this with negative 10. So here we have negative 10. Now you see we have 1. So we have 0.5 minus, or rather 0.5 plus 1. So 0.5 plus 1 gives us 1.5. So let's take this off again. So instead of 0.5 now, we have 1.5. Take this off and we have now 1.5. So you see how we go from 0, we go from 0 to 0.5 and then to 1.5. And the reason why I would expect to have better values of W, better in this case is values of W such that the straight line would be close enough to these points as compared to this other poorly performing model. And so as we're saying, the reason why we are sure that we are going to keep getting towards this better performing values of W is because we are including the loss in this algorithm. So when we calculate our loss, we look for this partial derivative with respect to the weights. And it's this partial derivative that permits us adjust the weights. Now this learning rate helps us adjust by how much we are going to modify the weights. So if we had a large learning rate here, or let's say if we had a larger learning rate, not large because learning rates are relative. So if we had a larger learning rate of instead of 0.1, if we had 1, so let's take this off. If we had 1, you'd find that right from the first step we would have 5. So we would just jump from 0 to 5. So this controls how much we improve our model. Now if you have no background in calculus, you shouldn't bother. As with TensorFlow, all we need to do to make use of this algorithm is by just specifying that our optimizer is SGD. So you just need to put in the string and you're good to go. You don't really need to write all this code. So getting back here again, we have, let's plot the loss against the weights. So we have a plot of loss against weights. Now our loss here is actually something like y minus y prime, all of that square. It's true we have a sum, but we're going to ignore that. So it's going to look something like this. You see this quadratic function. And even if you have no background in calculus, you should just understand that when we talk about a partial derivative or derivative in general, and we have a curve, that has to do with the slope of that curve. So if you have at this point, if at this point you have W and you have the loss, at this point the slope, you have a slope which looks like this. If you draw a tangent and you calculate a slope, you try to calculate the slope, you find that here the slope is going to be higher than if we draw a tangent at this point. If you look at this point here and you draw this tangent. Well, let's get back and try to draw a tangent. And we have a slope. The slope is smaller as compared to this. So if this is, let's call this slope A, and let's call this slope B. So slope A is greater than slope B. And so what this means is the partial derivative of the loss with respect to the weight at this point is greater than the partial derivative of the loss with respect to the weight at this other point. Now let's see how this plays when it comes to updating the weights. Remember that the ideal situation is that our loss should be 0. So what we want to do here is minimize the loss. So if we get to a point like this, then that's fine, because we've gotten to the smallest possible value of our loss. And what this means is you may even have 2 and 4 and as weight as M and C, that's as the parameters, but the loss will be maybe somewhere about around here. And so there may still be room for improvement. And so what happens is we are going to take this weight. You see, we have the weight, subtract the learning rate times this slope actually. So when we say partial derivative of the loss with respect to the weight, what we're actually doing here is we're subtracting that slope. And so if we are having this weight, imagine we have this weight here, and that this weight leads us to this point here. There we go. We have this point here where our loss is quite high, which is not what we desire. Then you would find that the slope is much larger, just like with this slope here. The slope is much larger as compared to if we have a weight value around here where we have a smaller slope. And because the slope is much larger, you would find that multiplying this larger slope by the learning rate will lead to a larger change in the weight. So this larger change in the weight will tend to make the weight or this weight value move to the left, because now we're taking the weight minus a large value, and so we'll tend to move now to the left. Now if we're in this other direction, if we come in this other direction, that's if we have a weight value in this other direction, then taking W minus this learning rate times the slope, because the slope is now negative, we have a negative slope, we'll have W minus a negative, that's W plus the learning rate times the absolute value of the slope. And so now we'll be moving towards the right. And so you see how graphically the stochastic gradient descent algorithm permits us move the weight towards values which will permit us have a smaller loss. Another interesting point to note is the fact that as our weight approaches these values where the corresponding loss is very small, the slope also becomes very small, and so the change in weight isn't that large. So if we get to a point like this here, if we get to this point, let's say we get to this point here, which is very close to the optimal weight value where we're going to have the smallest possible loss, then this slope here is going to be very small. And so when you do W minus learning rate times that very small slope, you'll find that the value of W will change just a little bit. And so what this tells us is when we are far away from that optimal weight value, the slope is large, and then when we approach that optimal weight value, the slope is small. And so what happens generally during training is as we start training, the loss value drops much faster, and as we keep getting much better weight values, this loss value continues dropping but much more slowly, and this is what we call model convergence. Now the choice of this learning rate is very important, because if our learning rate is too big, then multiplying it by a large slope will take this weights to this other side, which is not what we want. And if it's too small, then even if we have a large slope, the change in the weight is going to be also too small, and so the learning process is going to be too slow. So we want to choose an adequate value for the learning rate so that our training goes fast and smooth. Diving back to the code, you see all we need to do is just specify SGD, and we're going to have the W minus learning rate times this partial derivative with respect to the weights, which is going to be calculated under the hood. So that's it. Let's get back and print out the shape. That's y and x and y, and then we could start with the training. So here we just need to do model.fit, and then we specify x, we specify y, we give number of epochs. Remember, we said we are not going to start updating these parameters and then dive, or after one step just get straight to the optimal values. Generally we go through several steps, and each one of the steps is called an epoch. So we'll specify a number of epochs to say 10, and then we'll variables, we say 1. So let's run that and see what we get. Has no, this should be epochs. Run that, and as you could see, the model has trained for 10 epochs. Now you'll notice how this loss value keeps dropping. See, we go from 308,519, we drop to 308,516. If you increase the number of epochs, you would find that this value is going to drop even much more as compared to what we've seen already. So you see it keeps dropping. Now we get to 308, 485. Now, although we specify this optimizer to be SGD, that's stochastic gradient descent, we could also have other optimizers, so you could check out here, but most of these are just flavors of the SGD, like the Adam and Adam W, which are one of the most popular optimizers we have today. So click on this Adam. You see we have Adam optimizer, which, as we said, is a flavor of the SGD, and it has now many more parameters. You could feel free to check out all this in the documentation. So let's just copy this out, or let's just get back to the code and import Adam. So we have, get back to the top, we have from TensorFlow Keras optimizers, we're gonna import Adam. So that's it. You could import Adam, you can import Adam W, or any other optimizer available in TensorFlow. So that's it. Once you import that, you could now replace this SGD we had right here. So instead of this, now we just have Adam, and then you could specify its learning rate. So we have learning rate. By default, it was given to be 0.001. Yeah, that was it. Take that off. Okay, so by default we have this. We also have the values for beta 1, beta 2, and so on and so forth. Well, let's just focus on the learning rate. So by default we have this. We could change this to say 1e negative 5 or some other value. So let's just maintain the 1e negative 3, and then just as before, we compile the model, and then we go ahead and train. Now, while training, we did not keep the history of all these losses. So let's say history. There we go. So we're still going to have the same output, but now after the training is done, you could do history, and you'd see that you get all these different loss values. So you get all these different loss values. See, we have this dictionary, we have loss, and we have all these values right up to the end. So let's now do history, and then we get the loss. See, we have directly all these different loss values from the epoch 0 right up to the last epoch. We can now plot out this loss values using matplotlib. So let's simply do, let's first of all import matplotlib. We have from here import matplotlib pyplot as plt. Run that. Well, take off this O, and that should be fine. So we run that again. That's fine. We get back, and then we try to plot all this, or try to plot out this loss. So we see that graphically. There we go. We have our matplotlib plot history loss. There we go. We also want to have a title. So here we have model loss. Then we want to have a y label. Y label is simply the loss, and then we have the x label. The x label is the epoch, and then we have legend. We have train. Well, let's say train. Okay, let's put it on the list, and we have train. That's fine. And now we do plot show. There we go. You can see our loss, and you see that it's actually dropping. And if we compare this plot to what we had already in the board, we see that we're still very far from the model converging. So we could still do better with this model, or we could still get much smaller loss values. In the previous session, we looked at training optimization. In this section, we shall be diving into performance measurement. In this section, we shall define a metric which will permit us evaluate how well the model is performing. This kind of information is especially important when you have, for example, several models, or let's say you have two models, A and B. So if you have model A, then with a given metric, you could evaluate and see how well model A performs with the metric. And then for model B, you could also evaluate how well it performs with that model. And then now compare the two models, that's model A and model B. In our case, we shall be making use of the root mean square error. And again, with TensorFlow, it's very easy. You just need to have, import the root mean square error. So you have keras metrics, and then you import root mean squared error. So that's fine. So once you have this imported, you get to model compilation, which is just below here, and then you include that metrics, and then you have your metrics. You have root mean squared error. So once you include this root mean square error in your model compilation, and then you restart the training, you'll notice that apart from the loss, you also have the root mean square error. So now we have the loss and the root mean square error values which have been printed out. Then you could go ahead and plot the root mean square error out. So let's copy this and just paste it out here. We have, apart from loss, we have the root mean squared and error. There we go. Here we have models, model performance, root mean square error. Close that, and that's it. So here we have RMSE, then epoch and train. So let's run this and then see what we get. We have in this error, root mean square error. Let's add this R, run that again, and that's fine. So you see the root mean square error 2 is dropping. And then another special method which is used in TensorFlow to evaluate a model is actually the evaluate method. So you do model evaluate, and then you pass in X and you pass in Y. So run that again, and you see evaluates the model and gives you the root mean squared error. So here we have the loss value, and then you have the root mean squared error. So this is the loss, this is the root mean squared error. And note that this is at the end of the training. So it tells you how well the model is performing at the end of training. You could check this out here, 332, 869, and 308, 096. That's exactly what we have here. That's it for this section on performance measurement. We shall now dive into validation and testing. Let's consider this example or this sample SAT prep exam. So let's suppose that you get into the exam hall and you realize that out of this 8 questions which have been asked, 4 were already treated in class. What this means is that this exam paper is not very great or will not do a great job at evaluating your performance, as you've already had to treat this 4 questions in class. Actually, your performance should be evaluated on these 4 other questions, since you've not yet come across them in class, or you've not yet come across them before. And so after the exams, you would have all the students getting a score of greater than greater than 4 on 8, or we could say greater than 50%. So everybody in class is going to have a score greater than 50%, because the questions have already been treated and everyone has revised these. And so at the end of the evaluation, the instructor might think that all the students have grasped the different calculus concepts, whereas that's not true. they've just reproduced what they were already trained on. That's what they already revised in class. And so to avoid this kind of scenario with our model training, where we actually evaluate our model on what is already seen, like in this case, well, we say, for example, we train on this data, and then we evaluate on the same data, and we have, say, a root mean square error of 10, then that would not be a correct way of evaluating the model, because it's already seen this data. So generally what we want to do is split our data up into the train set and then a validation set, or let's say a train set and a test set. Let's keep this one aside for now. So we have our train. So let's say we have this part here, this first 5, we use this for training, and then this other 3, we use this for testing. So this is training, and then here we have testing. So what happens now is the model, after being trained on this, is now going to be evaluated on data it has not seen. Now the whole point of doing this is we want to be sure that the model is able to predict the right price when given the input. And so if we go ahead or if we go around testing or evaluating on the data it has already been trained on, then we may overestimate our model's performance. And so breaking this up like this makes sense, because now we are testing on data the model has never seen. Now, apart from breaking this up into these 2 parts, we also might decide to break it up actually into 3 parts. That's the train, validation, and testing. So now we could say this first 4 will be for training. So this first 4 for training, the next 2 for our validation, and then the last 2 for testing. The reason we shall do this is because we want that during the training process we have an idea of how the model performs on data it has not seen. As if we know how the model is performing on data it is yet to see, then we could make modifications at the level of the model, or even at the level of the optimizers, to see how we could ameliorate our model's performance before we go ahead and test our model on the test data set. Now in our case that we have 1,000 samples, say we have 1,000 samples, then we want to break this up such that we have a considerable number of validation samples, because the number of samples we have too matters. As if we have a very small number of validation samples, then we may not be able to properly evaluate how our model performs on data it's yet to see. So in this kind of scenario, we could say we could take 60% for training, we could take 20 for validation, and then we could take 20 for testing. We could also say we take here 70, we could decide to take 70, we could take 20, and then here we could take 10. But the point is we want to have a pretty accurate idea of how the model performs on data it's not yet seen. Now if we change this, and now instead of 1,000 we have, say, 10 million samples. So instead of 1,000 we have 10 million samples. Then in that case we could decide to say, okay, we want to have 90% for training, 10% for validation, and then another 10% for testing. And the simple reason here is because we have so many samples, this 10% of those 10 million samples is enough for us to evaluate how well the model performs on data it's not yet seen. Because the idea is to ensure that our model is evaluated on data is not yet seen, operations like the normalization shouldn't involve the validation and testing, as that will be data leakage. So if, for example, you want to normalize your data and then you take x minus mean divided by the standard deviation, and then this mean is the average of all the data, that's even including the validation and test, then you would have leaked some information from the validation and testing into the training data set. And so to avoid this, operations like normalization are carried out only here in our train set, such that we do not have anything to do with the validation and testing. So these are completely separate. And then from here we train our model, we obtain our train model, and then now we evaluate on the validation and test set. Now that said, we get back to the code, we dive into data preparation. So here we have our data which we had prepared. Here we had X, which is the full data set. And then before normalizing, let's create the cell below. And we have now our train ratio. So let's say we have our train ratio, which we will set to 0.8. Take that off. We have the validation ratio, which we'll set to 0.1. And then we have the test ratio, which we'll also set to 0.1. So we have validation, training, and testing. And then we have our dataset size, which is simply the length of X, which obviously is 1,000. You could print that out and check that it's and verify that it's 1,000. So that's it. We have train ratio, validation ratio, and test ratio. We are going to dive into splitting up our data. So we have X train, X underscore train. There we go. We have X, and then we take all the values from 0 right up to 0.8 times the length of the data set. Because if we have 0.8, if we have the split 0.8, 0.1, and 0.1, then what this means is here we'll have 800, here we'll have 100, and then here we'll have 100 samples. So we go from 0 to actually 800. Now since it's 0, we could take this off, and then we have int dataset size, which is 1000 times 0.8. So that's times the train ratio. So 0.8 times 1000 is 800, and that's it. And then now we have the y. So we repeat the same for the y. We have y, and then take this off. We have y. So that's it. We have our train ratio. Well, we have y train and x train. Then now we could print out x train shape, and then y train shape. There we go. So we run that, we create a new cell below, and then we do the same for the validation. So let's copy this, and there we go. Now note that for the validation, we are not starting from 0, we're starting from this 800. We go from 800 to 900. So in this case we have this 800, and then we go, let's copy all this again. So this is 800, this is 800, but we add the val ratio. So val underscore ratio, close that. So this is now 0.8 plus 0.1, which is 0.9. So we go from 0.8 to 0.9, and then we repeat the same. So let's just copy all this and repeat that for the training, for the y. So let's copy this, take this off, and there we go. We have, take that off, and then we have that now for y. So let's print out x train shape, or rather x val shape. Let's get back here. We have x val, and then y val, and then x val shape, and y val shape. Then we do again the same for the testing. So let's copy this, and then print that out. So you notice how we have 800 here, and then here we have 100 samples. So let's go ahead and do the same for the testing. Take this off. We have test, we have test, we have test, and then now we're going from 900 to the end. So let's just take all this off. That's fine. Take all this off, and then we go right up to the end. So run that again, and you see we have 100 samples. So that's how we split this up simply. Now the normalizer is going to be adapted to on the train set. So we adapt that to the train. So the mean, our standard deviation is going to be got from the train data and not from the full data set. Here we have normalizer train. So train. There we go. So now we've set about, we have our new normalizer. You see, we get back to the model. It's going to be the same. Nothing's going to change, but When we get to our model, or rather when we want to train our model, we'll specify X train and then Y train, and then we'll say here we have validation data. So we'll specify that we have validation data, and then we'll give it X val and then Y underscore val. So that's it. Let's put this way so it's more clear, and we have this comma and we run that. You see we're training, and you could see we have loss, we have root mean square error, we have validation loss, and then we have root mean square error, or we have validation root mean square error. So while you're training, you have an idea of what's going on. You don't need to finish training before testing. While you're training, you get your data validated, and so you could even stop the training after, let's say, 5 epochs, depending on how the model is performing, and then you could go and modify some parameters or change the model overall. So that's it. That's how we carry out validation in TensorFlow very easily. Now let's get back to documentation. Come here, Keras models, and then we'll check out the fit method. We have this fit method, and you see here that apart from the validation data, apart from specifying the validation data, you could also specify the validation split. So you could have all your data set and then decide that your validation split is going to be, say, 0.2. So let's say if you took in all X here, if you're training on all X and then you have Y, you could, instead of having validation data, you could just say validation split. So you don't have to split the data up manually. So you could just do this, and that will be fine. And then obviously you specify, let's say 0.2, and that's it. So you could run that, and you see that it still works just fine. Now let's go ahead and modify the plots such that we have both the validation and training plots. So here we have this plot. We would have our second plot. Take that off. And now we'll specify that as a validation. So we have val loss, Y level, loss, and epochs. Then for the legend, we have here val loss. So we add that. And then we do the same for the root mean square. So we just add this up here, paste it out. We have val root mean square. And then we also have val, take this off, val root mean squared. So run that again, and you see from here that the model or the training performance is better than the validation performance, as we have a lower value for the train loss as compared to that of the validation loss. That's the same with the root mean square error. And then now if you want to evaluate your model, instead of putting in all X, you could say val just on the validation. So you now evaluate that model only on validation data, you see. And then you could also decide to evaluate the model only on the test data. So let's take this off, and we have test data. Run that, and there we go. So you see it performs differently in the validation and test data splits. After evaluating the model, the next step will be to make use of this model to carry out predictions. So let's say we have, for example, X test. Let's take a single sample, X test 0, and then you see we have this 8 different elements, and it's of shape 8. So we would now take our model and do model.predict. That's a predict method we shall be using, and then pass in this X test. So we have X test, and run that, and then see what we get. Let's say this is Y output. Here we have Y output. You see we have this output right here. If we print out the Y output, here we have Y output. We have something like 2,748. Actually, this has been gotten like this because I retrained again for over 1,000 epochs, so the model got much better. Anyways, that's what we have. We will now dive to the next part. In this next part, we shall be placing the model's predictions and the actual prices, or the actual expected prices, side by side. So we'll do something like this. For each and every sample, we would have we'll plot out what the model predicts and then what was expected, and then we'll repeat for all the rest. Again, here we shall be making use of matplotlib. So we'll define our figure and then specify the figure size, we have 40 by 20, and then we shall specify the width of each bar. So let's take 0.1, and then we have plot bar, and then here we have a range of values. So let's just specify, well, let's just put that in here, TensorFlow range 100 numpy, and then we have what the model predicts, or y predicted, what the model predicts. We specify the width, and we have the label. So for our label here, we have model prediction. Let's take this off, copy and paste that, and then now again we repeat the same, because this 100 is picked because we have 100 test elements. So we could just say length of test set. So that's it. We have what the model predicts, and then we also have the actual values. So we'll call this y true, or y, we could call this y actual. Anyways, here we have y true, keep that short. We have the same width, and then we have our label. Now for each and every for this range we have here, because let's copy this and paste out here, run that. As we're saying, for this range of values, we want that each time we plot out the y predicted, to the right we should plot out the actual values, or maybe to the left. But anyway, we want that shift, and so what we'll do is we will add a width. So we'll add a width to these values. So you see that if you add plus a width, you find out instead of 0 or 1, we will have 0.1 and then 1. Let's take numpy on that. That should be fine. So here we have width is not defined. Oh, okay, width is not defined. Let's say 0.1. 0.1. We run that again, and that should be fine. So while that's running, we have plot x label, and then we have actual versus the predicted price, and then we have plot y label. We have car price. Okay, so we have plot show. There we go, plot show. That's fine. So now the next thing we'll do is actually get this y pred and y true. To get the y true, that's the actual values of the prices, what we could do is we would get the y test. So y true is equal y test. But since y test is of shape 100 by 1, what we'll do is we'll just take all and the rows. We'll pick all the rows, and then pick this first column. So let's take that off. That's our y test. We print out y true, and there we go. So you see we have this value. We could take numpy, and that's fine. So we'll now have this simple list. So these are all the different values for, or the actual prices for the cars for the test set. And then we'll do the same for the models prediction. So let's copy here and then paste out. So for y test, instead of y test, now we have the model which takes in x. So we have this test, that is, we have what we know. This is what we know, and now we're trying to compare it with what the model predicts. So instead of y test, we take in x, or big X. So we have big X. The model takes in all this, outputs 100 by 1, and then we have all, and then 0. So let's print out y predicted, what the model predicts, y pred, and then here we have that shape. There we go. Let's run that and see what we get. You see we have 100. Let's print all this out, and let's see numpy, and then here we have numpy. So we could now take this off. So we now have our y true and our y pred. So this is what the model predicts, and then just below we have what the model, or what was supposed to be predicted. So now we have all this. Let's run this and then see what we get. Let's take this off, and we can now look at our bar chart. You'd notice that we have one in blue and one in orange. Now this here, just looking at the values, you see that there's one that's a y true. The actual y's seem to be much larger than the what the model predicts. So our model is clearly underperforming. So you could see that from this chart. See here in blue. Let's maybe zoom in so you could see that clearer. You see, take that up. Okay, so you see just here in blue you have what the model predicts, and then in orange you have what was expected of the model. Let's get back, and there we go. So that's it for this section. We've just evaluated and tested our model. The next section we'll look at corrective measures to make our model much more performant. In the section on corrective measures, we shall start by commenting on our loss and validation plots. So we saw already that our model was underperforming, and looking at the loss versus epoch plot, we could see clearly that our loss values were much higher than what we could potentially get. And so this kind of scenario where we have both the training and the validation, so here we have train and then here we have validation. So when we have this training and validation plots, training and validation loss values which are way higher than what we would expect, in that case we'll call this underfitting. And this is because in the worst case scenario, our model at least should be able to learn from the training data. Well, here we could interchange this. We could have the validation and the training below, but the point here is that the model underperforms in both the training and validation sets. Now, generally, when we have this kind of scenario where the model underperforms even on the training data, this means that the model is not suited for the problem, or the model may be too simple. And by simple here, we mean that this 9 parameters M1 to M8 plus C, that's 9, aren't enough to learn from our 1000 samples data set. That's actually to get all the patterns necessary to be able to get a single sample like this one and then predict a reasonable price which is close to what's expected. So when our model is underfitting and not able to learn these patterns from our data set, what we do is we build a more complex model. And now this more complex model will be made of many more layers, hence rendering our deep learning model much deeper. So let's take this here and just pull this up here. You see, we have all this inputs, we have this weights, and then we have this output. Then instead of just taking this as our output, we're going to add this other two outputs. So now we have 3 outputs. Let's pull this up here. We have this one. See, we have this one, and notice how each one, that's each input, is linked to every other output. So take this here and put out here. See again, each and every input here is linked to all 3 outputs. And so what this means is we are going from 8 weights here, that's keeping aside the bias. We're going from 8 because we had M1 to M8 now to 24. So instead of 8, we now have 24. And then on this other side, what we'll do is we'll take this again. So let's drag this here. There we go. We have this one. We have this one. There we go. And then we have this other one. Well, we also have this other one. So let's just pull this up here, and that's fine. Again, we have all this linked to one another. So you see that now we have here in this intermediate layer, we have 24 parameters. And in this one, we have 3 times 4. That's 12 parameters. Here we have 12. Here we have 24. And then for this last layer, we have 4 times 1. That's 3. So let's get back. Let's drag this up here, and there we go. So you see that now we have a much deeper model with several hidden layers. We have now hidden layers, and then we have our inputs and the output. And one great thing about TensorFlow is that if here we had dense, that's we had this dense, and then we placed we had a single output, and this was in a list. Now we're gonna have that same list with a dense, but now we have 3 outputs. So here we'll specify 3, and then for the next, because we go from 3, that's this year, this layer we have 3 outputs. For this next dense, we're gonna have 4 outputs, and then we'll end up with a dense with 1 output. So we have 4, and then we have a dense with just a single output. So here we have dense and we have 1 output. So we're going from this line of code to this other one, which doesn't change much at the level of the coding because we just have to add this. But actually our model has become much deeper. By deeper here, like increasing the number of layers as we go in this right direction, we go deeper, and our model becomes much more complex, and so it's able to learn the patterns in our data set much easily now, as compared to this very simple model which wasn't capable of learning those complex patterns in our data set. So far we've been dealing with just linear functions. So essentially all what we've been doing is mx plus c, which is a linear function. But to increase the complexity of our model, we could add some non-linearity, which we'll call big N. So if we add a non-linear function, if after getting our outputs here, that's for each and every neuron we have here, we pass this into a non-linear function, because obviously this is a linear function here. If we pass it into a non-linear function, we shall make our model overall much more complex, and hence could learn more complex patterns in our data set. Some of the commonly used activation functions or non-linear functions are the sigmoid, the tanh, and the ReLU. With a ReLU, for example, it just y equal x if x is positive, and y equal 0 if x is negative. And tanh x is ex minus e minus x divided by ex plus e minus x, going from -1 to 1. For the sigmoid, we saw this already. It's 1 on 1 plus e to the negative x, and it goes from 0 to 1. So when we compute mx plus c, this here becomes our x, and then we pass this in here. So we pass this in here, and then we now obtain the sigmoid. Same as with the tanh, we take this x, we pass it in here, we pass it in here, we pass it in here, pass it in here, and we obtain the tanh. And then if it is with the ReLU, it's going to remain the same if all of this is positive, and if all of this is negative, then it's going to be 0. Dive into the code. We're just going to change this and say 128, for example. We could have 128. We're going to stack 3 of this, and then with 1 output. So we have 128, 128, and then our output must be 1, because that's the nature of our data. So because our data expects to have some input which is of the shape, and also the output must be of this shape. So if you don't have this kind of shape, then you would get an error. So that's it. We just stack this up like this. It's very easy. You could stack as many as you want. That's all you need to do. So there we go. We have 3 of this, and then we run that, and you could see now that we have 34,304 or 305 trainable parameters. We still have our 17 non-trainable parameters from our normalizer. We could reduce this. Let's say we take 28. We could also have different values. So we could take 53, for example, and you see we have fewer parameters. Anyways, let's get back to 128, 128, and 128. And we run that. We have our summary. We check out our plot. You see now that it's going to be different from what we had previously, because we've made some changes. Then we go ahead and compile the model, and we start with the training. Let's train for about 200 epochs. After training is complete, you could now see that we have a much better performance, as our loss values have dropped substantially. We could also check out the root mean square error. You see, this is a great drop as compared to what we had previously. We evaluate, and then we check out this plots. So you see now that the actual and then what the model predicts are not too far from each other as compared to the previous model. Now let's go ahead and add the non-linearities and then retrain again. This time around just for 100 epochs, as we see that after even about 20 epochs, the model doesn't change much. So let's go ahead and train for 100 epochs with now the non-linearities added. To add the non-linearities is simply activations. So you have activation and then you specify ReLU. That's all. So here we have activation, and there we go. We have activation and we have ReLU, activation and ReLU. Now for this last one, we don't need to have the activation as our values should be all positive. So we just let that, and that's fine. Let's run again and recompile and start with the training. Let's change this to 100. There we go, and then we run all this so we could check those out after. Now we actually forgot to note the y test values for the root mean square error. As you could see, we have better results. We could go ahead and check out those charts. Let's run this again, and there we go. We have our charts indicating that our model now performs much better as compared to our initial model. We've just looked at the section on corrective measures. Now we're going to dive into TensorFlow datasets. So right here in the documentation, you could click open on TensorFlow data, click on the overview to have an idea of what TensorFlow datasets are all about, and also why they're important or why we should generally want to use them. The TensorFlow Data API, as we shall see throughout this course, will permit us build complex data processing pipelines in a very efficient manner. This API would permit us work with large amounts of data and also be able to perform complex computations on this data effortlessly. The first method which we shall explore in our TensorFlow Data API is this from slices method. So let's just copy this out. We get back to our code. Then we change this to train. So this is our train data set. And now we have our from tensor slices method, which is actually going to take our tuple, which will contain the x train and the y train. So that's going to be our train data set. Now we could do for I in train data set. Let's print out I. Well, let's break once we're done with the first sample. So that's it. You see, we have this input and then we have the output. Let's say ij, and then print out I, and then also print out j. So you see that we have the I, we have this I, and then we also have the j. That's the output. Now, getting back here, you would find that it's very easy to do stuff like shuffling, batching, and also prefetching, which we shall look at shortly. Now let's get back to documentation. We could scroll down, and here we have the shuffle method. You see that this shuffle method actually takes in a buffer size, a seed, because you want to be able to reproduce a particular setting of your data set. So you want to shuffle your data in a way that when you reshuffle it again, you have exact same shuffling order. So that's it, and then you have the reshuffle after each iteration. So you want that each time you iterate on your data, you want to maybe reshuffle again. Anyways, that's it. We have this definitions here. It randomly shuffles the elements of this data set, and the data set fills a buffer with buffer size elements. So here we told that, for instance, if your data set contains 10,000 elements, but the buffer size is set to 1,000, then the shuffle will initially select a random element from only the first 1,000 elements in the buffer. So when you set the buffer size to 1,000, what you're saying is want to shuffle from the first 1,000 elements. And once an element is selected, its space in the buffer is replaced with the next 1,001st element. So maintaining the 1,000 element buffer. So yeah, what they're saying essentially is that if you have a data set with say 10 elements and a buffer size of, let's say 3, so let's create this 10 element data set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here we have 8, 9, 10. So we have our 10 element data set, and if we have a buffer size of 3, then the shuffling will be done such that the first element will be picked from either 1, 2, or 3. Once we pick an element, let's say we randomly pick out 2. If we randomly pick out 2, then what this means is we are going to take this off, and then we will now pick between 1, 3, and 4, so that our buffer size remains 3, because now we've picked out 2, and so we're left with 1, 3, and 4. Now let's randomly pick an element. We pick 4, so this is no more in our buffer. We now move on to 5, and then we could randomly pick out whatever other element, and so on and so forth, right up to the end. So that's essentially what is being described here in the documentation. Reshuffle each iteration controls whether the shuffle order should be different for each epoch. So after every epoch, you could decide whether you want to reshuffle or not. So getting back to the code, we have our train data set. Well, we already had this, so we just say train data set equal train data set shuffle, and then we provide a buffer size. We could take buffer size of, for example, let's say 16, of a buffer size of 16, and then we have the batch. So let's specify, let's take this off. We have batch, and then we have batch size. We could also have your buffer size. Anyways, let's just put this, let's just have this buffer size, and then we could define this above. So now we have the buffer size, which is set to 16, and we have the batch size, which we could set to 64. So now we have our buffer size set and the batch size set. Another thing we could do is prefetching. Getting back to documentation, we have here that most dataset input pipelines should end with a call to prefetch. This allows later elements to be prepared while the current element is being processed. This often involves, or rather it often improves latency and throughput at the cost of using additional memory to store the prefetched elements. So here we told that this prefetching has a buffer size. So we have this buffer size argument, and it represents the maximum number of elements that will be buffered when prefetching. And if the value of TensorFlow data auto-tune is used, then the buffer size is dynamically tuned. So we would like to use this. So to understand the concept of prefetching, let's suppose that this red is for loading the data and this blue is for training. So let's say we load a batch, and then we train, and then we load again. Let's copy this. We load. Let's drag this way. We load, and then after loading, you see, after loading, we go ahead with the training. There we go. And then let's say we load again. So let's copy this. Let's say we load again, and we go ahead again and train on that loaded data. The whole point of prefetching is that while you're training the model, you could be loading the data set. So instead of having to always wait for the model training to complete before loading, you could instead do this simultaneously. So let's take this off. So you could have this here. So now you're done with loading, you start training, and you're also loading. So once you're done with this training, you see you could now pick up from here. Or well, you could pick up from here because you must complete the loading. So you could pick up from here. Let's take this off. And then once obviously while you're training again with this, you could also start loading. So we could start loading from here, and let's take this off. And then we could pick up from here. Let's take this off. We could pick up from here and start training. So you see that at the end, we've taken up for the first scenario. Let's reduce this. For the first scenario, we took a time. Let's say we took a time t. This time we took a time t to complete. But in the second scenario, we've taken a time of about 2 divided by 3t. And so that's why here we'll just do prefetch, and then we have TensorFlow data auto tune. So that's it. We run that, and there we go. We have our train data set. That's fine. We repeat the same for the validation and the testing. So take this off. We have train off. We have val, and then here we have val. Then here we also have val, and instead of train we have val. Instead of train here we have val. We do the same for the test. So let's run this and then do the same for the test data set. We have test, and take this off. We have test, and yeah, test. So that's it for the train, validation, and test data set. On this, you'll notice that the shape is now different. Let's actually print out just the shapes. So let's say I shape and then J shape. Run that and see what we get. You see now we have 64 by 8 and 64 by 1, and that's simply because our batch size was set to 64. Now we're not going to change anything at the level of the model, so we still have our model. Let's rerun that. So we reinitialize the parameters, we recompile, and then here we're going to replace all this with train dataset. So just say train dataset, and that's fine. And then for the validation, now we have val dataset. So take this off and rerun that again, and our training should be fine. So you see, we go on with the training as usual, and we could check out our plots, and now the evaluation will be on the val dataset. So let's take this off, run that again. Yeah, it's gonna be test dataset, test dataset. Take that off, run that again, and that should be fine. So you see, we've replaced our initial data pipeline with now the TensorFlow Data API pipeline. Hello everyone, and welcome to this new and exciting session. According to the World Health Organization, nearly half of the world's population is at risk of malaria. In 2022, an estimated 249 million people contracted malaria in 85 countries. That same year, the disease claimed approximately 608,000 lives across the world. Malaria is an acute febrile illness caused by the Plasmodium parasites, which is spread to people through the bite of an infected female Anopheles mosquito. Now, this disease is preventable and curable. In this section, we shall see how we could build out a model which takes in as input this blood cell and says whether this blood cell is infected by the malaria parasite or not. With that said, the data we shall be using to train our model will be composed of input images like this one and the output, which is parasitic or uninfected. So we could have parasitic, and then we could also have uninfected. So we have these two outputs, or these two possible outputs. In this section, we should start by understanding the task. Then we'll dive into preparing the data. Then we'll build a model, in this case a new model, that's a convolutional neural network. We shall check out on another error sanctioning method. Then we'll go ahead and train our model, evaluate this model, then apply necessary corrective measures to ensure that we have an even more performant model. To understand the task, we shall get back to how the blood cells are being generated, given that these blood cells make up the data set which we shall use in training our model. So as you could see here, the first thing is we select the finger to be punctured, then we puncture the ball of the finger, and lastly, we touch the next drop of blood with a clean slide. With the blood now placed on the clean slide, we could view this under a microscope, where you could see here we have thin blood film and then we have the thick blood film. What's important to note here is the fact that we could extract each and every one of the cells here. So if you could pick out just the cell, and then you have this image which you have right here, and then is this image with its corresponding label, which is that of parasitic or uninfected, that we'll use to train our model. Now, just focusing on our input, that's the image, you would find that if you zoom in, let's get in here. If you zoom in, we have these units here beyond which we cannot zoom in any further. So let me reduce this. Let's draw around the outlines of these little squares. So let's take this specific square here. Let's draw this, and there we go. So you'll notice that we have all these little squares right here, and these little squares actually represent a pixel. So let's just have this. So this here is a pixel, and all these different pixels are what make up a complete image. If you try to zoom out now, you see that pixel, that unit which we could not zoom in, or from which we could not zoom in any further. You see that when we try to zoom out, you see it becomes much smaller. So what we're saying is this each and every small square or small pixel forms part of our complete image, and understanding that pixel forms part of this complete image and the kinds of values it takes in is important when building machine learning systems. That said, when we say an image like this one is 490 by 766 pixel image, what we mean is that we have 490 images, or rather 490 pixels horizontally. Like if you scroll right here, you take note. Let's make sure you take note of what ever value we have here. So at this point here, you would have the values. So getting back to the image, you see around here we have 400. If I get to the last, I have 490. Well, I'm seeing 489. So I have 489 by 6. Let me go slightly up. Okay, so you see I have 489, well 88, 488 by 1. So what this tells us is if we reduce, you see the value is reducing. Now we have 283 by 0. As we increase, see we go right up to 490. Let's get here. We have 487, but that's actually 490. So this tells us that horizontally we have 490 pixels, and vertically we have 476 pixels. Now if we scroll right down here, right up to this, you see we have 0 now by 473. Well, if you get right below, we should get 476. So that's it. So this tells us that we have those pixels. Now if we zoom in, you have similar scenario to what we had on the previous board. See, we have this small cells which we had seen already here. So we had picked out this particular cell here, which represented a pixel. An image like this one, which contains 490 by 476 pixels, will contain totally 233,240 pixels. So these are the total number of pixels we have in this image. And then for each and every pixel we have, it takes 3 values. So when we have an RGB image like this one, or a colored image, we have that for, let's say, this pixel, let's get back. For, let's say, a pixel, this pixel, it has, or it takes in 3 values: the R value, the G value, and then the B value. And then each and every one of these values range between 0 and 255. So the R will range between 0 to 255, the G between 0 to 255, and then the B between 0 and 255. Making use of this image gotten from the MATLAB website, you find that our image is made of the R, see, the G, that's the green, and then the blue. So and then the blue component. So if you pick out a pixel, like let's say we pick out this pixel, you have its R value, you have its G value, you have its blue value. Now you may be wondering why all those values actually range between 0 and 1. The simple answer is that if we have values ranging between 0 and then 255, for them to range between 0 and 1, we could normalize them, and that's by simply dividing all the values. That's if we take all these values that we have and we divide by 1, then or rather we divide by 255, not 1. If we divide by 255, then all our values now will range between 0 and 1. And so with that said, now we could split this our image up into this 3 different channels. We'll call this our R channel, and then we would have the G channel, and then we'll also have, well, let's space that out, and then we'll also have the B channel. And so this image, which is 700 or rather 476 by 490, is actually 476. That's 476 by 490 by 3, because we have these 3 channels, R, G, and B. In the case where we have a black and white image, that's a grayscale image with only 1 channel, then we will not have this last channel. We'll just have 476 by 490 or 476 by 490 by 1. In that case, we'll only have one of these channels right here. The RGB value for an image which is completely white like this one is actually 255 by 255 by 255, meaning that the R value is 255, the G value is 255, and then the B value is 255. And then for an image which is completely black, the R value is 0, the G value is 0, and then the B value is 0. With that said, we could go ahead now and prepare our data, which is composed of these cell images and their corresponding labels. In this section, we'll dive into preparing our data. So we have this Malaria data set, which is made available on the TensorFlow platform. So here let's scroll down. Here we have its description. The Malaria dataset contains 27,558 cell images with equal instances of parasitized and uninfected cells from the thin blood smear slide images of segmented cells. We have this additional information right here, and then you can see the size, and then we have this figure which shows us some sample images. Now we are going to click on Explore in Know Your Data. So let's open this, and then we could check out different data samples we have here and overall information about our data. Selecting this cell at random from the right, you see here we have this uninfected cell. We have all the different features and their values. Has faces, false, is portrait, false, labels, number of faces. Well, this is a general know your data platform, so you would have these kinds of features actually. So although we're not working with faces in this case, would definitely have this because this is something general. So we have the aspect ratio, we have the format, that's PNG, we have the resolution, we have the mode, RGB, we have the height, and then we have the width. So you see we have this image right here, exposure quality, sharpness score, and so on and so forth. So that's it. We see we have the label, and then we have our image. So you could pick out some other one and then check that out. Anyways, yeah, you notice that we only have uninfected cells, and that's simply because we start with the uninfected. That's out of this 27,000 items. The first let's say 13,000 or 13,500 or whatever number is uninfected cells, and then the rest are parasitized cells. So if we change the order, you see now we have the parasitized cells, and clearly you could see visually the difference between the parasitized and then the uninfected. See, notice how you have this little purple patches here and there in the different images, and then when you click here, you find that the image is much clearer, or you don't have those kinds of patches we had here. Like you see these patches we have with the parasitized cells, we no longer have them with the uninfected cells. You could also decide to group by these different features. So let's say, for example, let's group by aspect ratio. See, we have those different aspect ratios and so on and so forth. So you could decide on how you want to group the images and visualize them that way. So that's it for this part. We'll now dive into loading our data set, and to load our data set, we'll make use of TensorFlow Dataset load method. So you head over to the documentation, that's TensorFlow Datasets, API docs, Python to be specific, TensorFlow Datasets, and then we have this load method right here. So with this load method, we'll be able to simply specify, like let's get back here, we'll be able to simply specify this name and then load up this data such that we'll have as output here our TensorFlow dataset with obviously its information. With that said, we'll start with the imports. So we get back to our notebook and then we simply import TensorFlow as TF. Then we import NumPy as NP. We import matplotlib for visualizations, matplotlib pyplot as PLT, and then we import TensorFlow datasets as TFDS. Run that and make sure you have the runtime set to GPU. Let's now go ahead and load the data. So we have dataset and then the dataset info. Then we have TensorFlow dataset, TensorFlow that's TFDS load, and then now all you need to specify is Malaria. So what we had seen already, that's the name which we saw in the documentation, is the exact same name we use here. So we have that Malaria, and then we have with info set to true. Let's run that and then see what we obtain. So let's have dataset, and then we have dataset info. With this downloaded, you see here we have the dataset and we have the dataset info. So we have this dataset which is a prefetched dataset. You could see the shape right here, none by 3. So we have an RGB image, and the data type is unsigned int 8. We have the label, which is an integer, so definitely we would have 0 for, let's say, parasitic, and then we would have 1 for uninfected. So that's it. So let's take this off and say we select only train, and there we go. You see we have just that data set. So let's say for I in train, and let's take a single element. So let's take just that single element and let's print out that I. That's it. You see we have the image. That's it, 103 by 103 by 3. And then we scroll down and we have the corresponding label, which is 1. And then we have dataset info, well, the name, the full name, the description, and right up to the citation. We could verify that the length of our data set is 27,558 by printing this out. And then we could now dive into splitting up our data set. So here we have the split. You see that we specify train, and train because obviously our data set initially is made of just a train data. And so now we are saying that we want to have all elements between the first 80%. So essentially what we're saying is we're going to have element 0 right up to element 0.8 times 27,558. So let's take this off. We run that, and you see what this tells us is we're going from 0 right up to 22,046. So this first 22,000 elements will be used for training. Then the next 10% of our full data set will be used for validation, and then the final 10% will be used for testing. So with that said, let's run this, and then now let's say data set. You'll find that we will have this list made of 3 different data sets. So let's say we have data set equal data set 0, and then we have the same. We repeat same for validation and testing. So yeah, we have 2, we have 1. There we go, we have 1. And then we could take this off. We have validation, and then we have testing. So let's run that, and now we could do the length, or we could get the length. We could get the length of our train data set, and we could do the same for the validation and the testing. Test and val. Run that and see what we get. So that's it. That's how we split up our data set. We can again print out those different lengths for the train, validation, and testing. So we see we have 22,046, 27,056 for both the validation and the testing. From here, we'll go ahead and shuffle our data set. If you check out documentation, you see we have shuffled files. Let's just take this way. And we have here shuffle files, and we'll set that to true. And the reason why we need, or is important for us to shuffle, is simple. Suppose that you have some data, and this first part is uninfected, and then this next part, let's take this off. This next part is parasitized. Let's take this from here. Now, if you take out the first 80%, then you end up with something like this being your train. So this will be your train data. Let's take that off. So let's say this is going to be our train data, and then this is going to be our validation and testing. But the problem now is that validation and testing is made of only parasitized cells, whereas if we had shuffled our data, then we would have a mixture of the parasitized and uninfected cells. So you would have something like this instead. Let's just take this randomly have that, and there we go. So in this case, you see that we're gonna have, or we're gonna go from, let's add this up. We have that. We're gonna have this first 80%, and then we'll break this up again, and you see now that our validation and the testing data sets have both the uninfected and the parasitized cells. So that's why it's very important for us to shuffle our files. Run that again, and there we go. So we could run this again, and then feel free to check out let's say val, and that's it. Well, this should be, let's get back, this should be val dataset instead. So here we have val dataset, and we could take that off, run that, and see what we get. You see we have our image, and we have its corresponding label. Another way in which we could carry out the splitting is actually manually. So instead of relying on this split parameter right here, we could actually manually split up our data set. And this is important. And this is useful in cases where we are not dealing with a data set provided by TensorFlow. So let's say we do not have the split. Let's take this off. Let's suppose we do not have the split. We still have the shuffling. Now we're going to define our split method. So here we have the split method, which will take in our data set, and then we'll take in our split ratios. So we'll define train ratio, train train ratio, val ratio, and then we have test ratio. So right here we will start by defining, let's return none. So what we'll do is we're going to start by defining these ratios. So let's say we have train ratio, which we'll set to 0.8, and then we have val and test ratios. So test ratio and then val ratio, and here is 0.1 and 0.1. That's it. And then now what we do is we're going to create a simple data set to illustrate how our manual splitting will work. We have the data set, or let's call this, let's just say DS, our data set, and then we have TensorFlow data set range, and then we put 10, so we get this 10 values. So let's just print out, well, let's just call this our splits method. So here we would have train ds, we will have val ds, and then we would have test ds. So that's what we expect to be returned right here. Train data set, we have val data set, and then we have test data set. That's it. And then now we'll call on our method split, which will take on the data set or ds, and then we'll pass in its the train ratio, we pass in the val ratio, and then we'll also pass in the test ratio. So that's it. Let's get back, test ratio. Let's now comment this out as we've just done, and then we print out the our data set as numpy iterator, and then we have list, and run that and see what we get. There we go. As you could see, we have values ranging from 0 to 9, which is what we expect because that's what we specified right here. Now if we want this first 80%, that's this first 8 elements, then it suffices to do to get right here and say take, or not this, let's say we have, or let's say we just define this val ds right here, and we say ds take the first 8 elements, or take the train ratio times the total, or let's say total number of elements. We set that to 10. We set it to 10. There we go, and we replace this with total. That's it. We have total, so it's gonna be 8. Well, this should be an int, so we'll just make sure we have an int right there. Run that again, and then we'll see what we get. See, we have our data set, and then we're making sure we want to get the first 8 elements. This should be, well, let's print, that's the initial data set. Let's now get the val data set. So because this is a complete data set, now we want to have the val data set. You'd see that we get the first 8 elements. You see, we have those first 8 elements. Now if you want to get the next 8 elements, all you need to do is skip the first 8, and then once you skip the first 8, you take the next. So this is 0.1. So what we'll do is we're gonna have our val data set, or well, this is actually train. So this is actually train data set. So our train data set. And then now for our val data set, let's take this off. For our val data set, we'll specify the val ratio. So here we have our val ratio, but also this is skip. So we want to skip the first 8 elements. So let's say we have train. See that? So this is the first 8 elements that we're gonna skip, and we will take all this to the end. So here is skip, and then here is take. Take simply means you have a data set and you take the first n elements. So if n is set to 8, then we'll take the first 8 elements. Now for train, for skip, you simply moving, or you're going to start from the n plus 1th element. So let's say val data set, and we skip this first 8 elements. Here we have train. So here we should have train. Let's copy this. There we go. We paste that out. So now we should have val. So let's take this off and run that. So we see how we get the val data set. Well, this for now is a combination of the validation and the test data set, because we just kept the first 8 elements. See, now we have 8, 9. So this last elements. Now we'll just change this slightly and call this val test. Val test, because the combination of the validation and the test data set. So that's it. We have val test, and then now we'll define our val data set to be simply our val test data set, and then now we take the top elements, or rather we take this first element. So we have int. Let's cancel that. We have your int, and then we have our val ratio times the total. So this is going to give us 1. So we'll just take the first element, and then we have for the test, let's take this off, paste that out. We have test, and then we have val test data set, but instead now we skip. So we skip that, and then we have 0.1 times 10, which is 1, and we get this last element. So now we could print out, let's print out our val and test data sets. So take this off, we have val, and then take this off, we have test. Run that again and see what we get. You can see that we have now 8 for the val, and then we have 9 for the test. Now let's say we had changed this to 2, 2, and 6. Run that again, and then see that we have for the train the first 6 elements, and then for the next we're gonna have the next 2 and the last 2. See, here we have our train data set, here we have our val data set, and then here we have our test data set. So our method works perfectly. That said, now let's dive into our split method and then implement what we just described right here. So we'll start by getting this total. To get total, you just need to have the dataset size. So let's say dataset size, which is simply the length of our dataset. And once you have the length of the dataset, you now do train ds. That's exactly what we had seen already here. And we specify the train ratio times total. So let's just copy all this, or let's cut that out and then paste out here. Shift this. There we go. So we have our train data set, val data set, and test data set. Now this is instead dataset size, and here we have dataset size. There we go. We have we can now run all this. Then let's get back here. Let's take all this off. And now we have our train data set, val data set, and test data set. So let's get back to 0.1 and then 0.8. We don't need this total anymore. We don't need this too. Our data set is this data set. So let's take this off. So we have data set. We run that and then see what we get. While that's running, we could simply update this here to get the length of train data set. We get a length of val data set, and then we get the length of test data set. On that too, and make sure that we have exact same lengths for both the first method and our manual splitting method. So we get in this error, dig has no attribute take, and that's because here we need to specify that this is train. So we run that again. That should be fine now, see, and then we also run this too. So we now compare the lengths, and you could see that they are almost the same. The only difference we have comes from the fact that this int rounds down, whereas with this method, making use of the load method, the load method split, we instead have a round up. So that's why we go from 2755 to 2756, whereas with the manual split we go from 2755.8 to 2755. So that's why we have this little difference. That said, that's it for the section. We're going to move on to the next section where we'll dive into visualizing our data. Welcome to the session in which we shall be focusing on data visualization. So we want to be able to generate visualizations such that we have images and their corresponding labels. Now we're going to make use of matplotlib for that. So let's go through our data set. So for I, sample in enumerate, train data set, take. Let's say we want to visualize 16 samples, the first 16 samples. We will have, we'll make use of subplots from matplotlib, subplot, and then it's going to be 4 by 4 that we increment I, and then we have plot im show to show the image, but here we have our sample, and then here we'll specify image. There we go. And then we have the title. Now the use of this title is simple. We want to be able to have the corresponding label. So we have sample, and then now we have label. So let's run that and then see what we get. We get in subplot not defined. This should be actually plot. So we're making use of matplotlib for that. Now with this next error, what we could do is simply print out our sample label, and you find that we have this integer tensor which we get. Now what we could do is we could simply do numpy, and then once we obtain the 1 from there, we would simply say get label or get label string. So this takes in an integer. So here is going to be the label, and then we're going to return the corresponding string. So if our label is equal 0, we return parasitized, and then else we return uninfected. So that's it. So if it's 0, then we have parasitized. If it is 1, then we have uninfected. Let's run that, and then now we will have get label string, and then we get that corresponding label. So now we have numpy. There we go. We close that up, and then we run this. Looking at this here, you could see the corresponding the different labels. So we could now take this off, and here we have our corresponding plot. So you see we have this image uninfected, and we have the parasitized. So that's it. So we have our different images and their corresponding labels. In the section on data processing, we shall focus on resizing and rescaling. Firstly, with resizing, we'll start by explaining why we need to resize our data. So let's suppose that we have an input image, or we have different inputs. Like we could have this one of shape. Let's put out a shape just by ear. So let's say this is 256. So this could be 256, and then we have another input, like this is 256 by 256 actually. So let's say this is 256 by 256. Let's copy this and paste out here, and then we have another input which is, let's modify this so it's smaller. There we go. We have this smaller image, and these two images make up our data set, or are part of our data set. So let's say this is 150 by 150. So now we have these two images which are part of our data set and which have two different shapes. Now the point of us resizing is simply because our model here will generally want to take in an input of the same shape. So we want to have an input of a shape, let's say for example, 224 by 224. So 224 by 224. Now note that if it's RGB, then you have 256 by 256 by 3. And here you have 224 by 224 by 3. So what we'll do is, before passing in this input into our model, let's shift this way. Let's take this way. So before passing this input into our model, we will resize it. So we'll pass this into this resizing unit, such that now we have inputs of shape 224 by 224 before getting or before passing this input into our model. After resizing and making sure that we have the same shape for all the inputs, the next step will be to normalize our data. So let's say we have an input. We'll do x minus x mean, call this x mean, divided by x max minus x mean. Now, in our case, we know that the minimum, or x mean here, is actually 0, because the pixel values go from 0 to 255. So if x mean is 0, then our x max is going to be 255. So just replacing here, you see we have this is going to be equal x, well, x minus 0 is x, divided by 255. So we normalize, or we rescale our data in this way. One point we need to take note of is the fact that we are normalizing, or we need to normalize our data before it being passed into our model, because we want to be able to restrain the range of our inputs. So we are going from a range of 0 to 55 to a range of 0 to 1. So restraining is or restraining our inputs in this way helps us now, because our weights, or those inputs, will be multiplied by the weights. And if this range is quite large, we get a less stable training process as compared to when we're multiplying weights by inputs whose range is very small. So it's very important to normalize your data before passing it into the model. Apart from this normalization, we could also have standardization. So first of all, here we have normalization. There we go. We have normalization, and then we could also have standardization. So in the case of standardization, here the formula changes slightly. So we have standardization, and as we're saying, we're gonna have x minus a mean value divided by a standard deviation. Now, this applies generally where we have this mean and standard deviation for a given data set. Like in the case of ImageNet, the ImageNet data set, which we are going to look at in subsequent sections, we have we know this mean values for each and every channel, and we know also the standard deviations. So because we know this mean values of the pixels and the standard deviations, we could standardize our data. So we could simply take x minus that mean value divided by the standard deviation. But in data sets like this current one, where we don't have this already, we could just simply normalize, that is x minus x mean, which in this case is 0, divided by x max, which is 255 minus 0. And so we have this process instead. So that's it. We replace here, and now we have standardization, or rather we have normalization. So yeah, we have normalization. That's it. So we resize, and then we normalize or rescale our data, and then we pass this into our model. Diving back to the code, we'll first of all start by defining the image size. So here we have im size, set that to 224, and then we have our method, which will be the resize rescale method, and it takes in the image and its corresponding level. So here now what we're doing is we're simply going to resize. So we take we make use of this resize method from TensorFlow image, taking the image. You could check that out in the documentation, and then you specify the new size. So here we have im size by im size. So that's it. So whatever image you're gonna have now as output an image of shape 224 by 224, and then what we want to also do is label. Well, here we have the label. Now, as we've seen already, we'll just simply take whatever x and then divide by 255. So after resizing, we'll divide by 255, and that'll be it. So let's run that again. We'll now modify our data set. So here we have train, there's a call this train data set equal train underscore ds, and then we use the map method, which is going to simply take in this resize rescale method. So here we have resize rescale, and that's it. So now we have our new data set, which is the original data set, but this time around with the resize rescale. So here we have missing one argument, label. When we scroll back here, we notice that this is actually a dictionary. So instead of taking this two separately, we should just say we have inputs, and then now we have inputs, and then we have image. So you pick that up, and then we also have input, and then here we have label. So let's have this, run that again, and this should work this time around. We're getting another error. Here we have input, well, inputs actually. So inputs, run that again. There we go. That's what we have. Now we could do for image label in train the data set. Let's take a single element, and then let's print out the image and also print out the label. You could see now that we have this inputs where we have the shape, or this image shape 224 by 224, and then we have the output 0. So that's it. So we now have our data, but we just seen all zeros here. But let's do numpy unique, and then we pass in image and see, and be sure that we actually have non-zero values in our image. You could see that we go from 0 right up to 0.771, which makes sense because our values are supposed to range between 0 and 1. And that's it for this section. In the next section, we'll dive into how the convolutional neural network works. We are now ready to build our model, and up to now, neural networks have been performing quite well. We had seen previously that if we have 3 neurons, that's 1, 2, 3 in the input, and in the output we have 3 neurons too, then there will be 9 different connections here, and hence 9 different weights plus the bias. But for this example, let's consider only the weights. So we have 9 different parameters for 3 inputs, 3 outputs. And if here we have 5, considering only the weights, we would have 3 times 5. That's 15 different parameters. Now, if we're dealing with an image like this one, so let's consider this image, which is 224 by 224 by 3 image, 3 for the 3 different red, green, and blue channels. So we have this input image now. So unlike previous examples where we would have features, or specifically in this case input features, which do not contain as many elements as this, we now have this case where if we want to count the number of features or the number of pixels, we would have 150,528 different input features to take into consideration. Hence, instead of having a total number of 3 right here, we are gonna have 150,528 different values. And if we want to do the same competition, which got us this number of parameters, we would have 150,000 times 3. That's approximately 450,000 different parameters. Now, what if we modify this number of neurons right here and take, say, 1,000 neurons in this output right here? We would see that we'll move from 150,000, or rather from 450,000 to 150 million different parameters, where each and every parameter has to be trained and optimized. This becomes clear that deep neural networks like this, or better still, dense layers or fully connected layers, aren't scalable, since when we increase the number of features, the total number of parameters also increase considerably. Hence, we need to build a type of layer, unlike this one, where each neuron isn't connected to all the previous neurons. And this layer happens to be the convolutional layer. In order to better visualize this, we'll use this demo platform from Ryerson University. So here we'll put in a figure, let's say 4, and then we'll see exactly how this ConvNets work. So we have this, and then we have this input right here. So we get this input, we have some weights, and then this output features. Note how to obtain this particular pixel right here, only a few of these inputs are used. And so here we call this the receptive field. As you could see, we have the receptive field right here. And if we take this other example, you see it's on receptive field. You see, to get this value, only these 4 values you see below. Actually, this one, this, and this. As you could see here, let's scroll back. Okay, so only those 4 values have a role to play when it comes to giving us the corresponding value we have here. And so unlike with the dense layer, where to obtain this value we needed to link this to each and every previous neuron, now only just some neurons in this neuron's receptive field play a role in getting this value. Another great tool for better understanding the convolutional layer is this CNN explainer. Actually, CNN stands for Convolutional Neural Networks. This is created by Jay Wang, Robert, Omar, Park, Das, Fred, Kang, and Polo. We are really grateful for this tool. Before getting back to the explainer, let's take this example. Right here we have a 4x4 image, so we have 16 different pixels. If we flatten out these pixels, that's if we put these pixels out like this, such that we have these inputs, and then in the output we have 4 different neurons, then here we would have 16 by 4 connections. That we'll have 64 different parameters, excluding the bias. But with a conv layer, we could leave from this 4x4 to just a 2x2. So we could leave from this 4x4 to this 2x2 with just 9 parameters. So we would have what we call a kernel right here, or a filter. So we have this filter, which is 3x3, which actually corresponds to our weights, which we've seen already. This kernel here, kernel size 3, will produce this output of 2x2, which when we flatten out can give us this output right here. And so instead of working with 64 parameters, we're working with 9 parameters. If we want to replicate that same example in the CNN explainer, here's what we get. We have this input right here, which produces this output. Now, notice how we specify that the kernel size equal 3. And because the kernel size equal 3, we are able to get this output. But how is this output gotten? You would see that at this top left corner, we are going to fit our kernel, which is of size 3x3. So we put in our kernel right here, and then we take each and every value of our kernel and multiply it with a corresponding value in the input. To obtain the first value, you see how we pass this kernel on the input. So at this top left position, we've passed the kernel. Notice how we have a 3x3 kernel, which is passed on this input, and we have the output right here. Then to get the next position, to get this next output, you see how this kernel is passed on this next part of the input. And the way we get this next part is by simply sliding through the image. You see how we left from this, we slide that through the image, and we got this next output. And since we've gotten to the end, we move to the next position, which is this. we get this next value right here, and then from here we slide again to this end and we finally get this value. So that's how we get all this outputs from the inputs and the kernel or the filter. We can now go ahead and increase this input size. Let's take, for example, 7. You see we have input size of 7 by 7 input image, and then we have this output 5 by 5. The reason why we have this 5 by 5 is because we have this kernel size of 3. If we get to increase the kernel size to 5, you see our output reduces. You see, when the kernel size gets to 6, our output reduces. Let's take this back to 3. So you take back to 3, and this input of 7 by 7 gives us an output of 5 by 5. We see how when we get to this, we have that output, move, slide, 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 move to this next here, slide, 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 and so on and so forth, right up to the end. So from here, we see how the size of the receptive field of each of these outputs equal 3, which is actually our kernel size. The next thing to notice is reducing the kernel size permits us extract more features from the inputs. You would see that since we have this input 7 by 7 with kernel size of 3, we have the output 5 by 5. So we've extracted much more features from this input as compared to when we push a kernel size of 6. Here we'll extract less features from these inputs. Now, though using a smaller kernel size permits us extract much more complex information or complex features from the inputs, working with larger kernels permit us extract larger input features. One logical question which may come to your mind is, how do I get the size of this output feature map right here? To get this, we'll use this formula where this output width is equals the input width minus the filter size plus 1. If we take this example, we have an input width of 7 minus a filter size of 3 plus 1. This gives us 5. So that's how we obtain this right here. Now, if we take say kernel size, let's take the kernel size to be 4, for example. In that case, we have 7 minus the kernel size 4, which is 3 plus 1, which gives us an output of 4. And that's how we obtain this output right here. Now, in a case where you're designing a convolutional layer and you want to get a particular feature map size, say for example in this case, if you want to get an output size of 3, then all you need to do is to specify this kernel size to be equal to 5, and you should get this output. Now, in some cases, you may want to have a particular feature map shape, but using just the kernel size, you wouldn't be able to get that. And so, to match up with the particular output shape, would include a pattern. Let's look at this pattern. You see, we're having 7 by 7, and when we take this to 1, you see that we go from 7 by 7 to now 9 by 9. Notice how it's written here. After pattern, we have 9 by 9. So we'll leave from this 7 by 7. Let's take this in this box right here, this internal box, and then the pattern leads us to 9 by 9. Notice how after doing the pattern, and if we play around with our kernel size, we go from 1 1 to 8 8. So we go from 1 1 to 8 8. But with 0 pattern and the input size of 7, you see we go 2 3 4 and 6. So we cannot go up to 8 8. We're gonna have an output of 8 8 when the pattern is 0. Whereas when we increase the pattern by 1, here we increase the pattern by 1, that's 1. You see that we could get an output of, say, let's put a kernel to 3. We could get an output of 7, of 8, you see, up to 1. So that's it. Now we understand how this pattern works. Basically, we just have our input and then we add this surrounding elements right here. We just pad our input image. Now the pattern generally we use is the 0 pattern, though there are other pattern methods, but the 0 pattern is one of the most common since it's easy to use and it's computationally less expensive to work with. So that said, here's our pattern. And then we also have another advantage of working with a pattern, which is that of ensuring that the corner pixels have an influence on our output features which are generated. Now let's take this back to 0 pattern. We have 0 pattern and we have this input image right here. If we're doing an image in which most of the information or most of the relevant information is centered, then there is actually no issue, since this filter right here will go through each and every pixel we have where we have this person in the image. Now if we modify this image such that we have a person's, let's suppose we have a person's face here just at the corner of the image, you'll see that unlike with this image where this person was centered and that our kernel was able, or our filter was able to pass through each and every part of this image, with this one we have a different scenario. We've just modified this so it looks similar to what we had here. Now what we could do is, if we monitor the number of times this filter goes through the person's head, we would see that we would have here one time because our filter passes here once. The next time after the sliding we'll have this, so second time. The next time after this other sliding will lead to this 4 times, so at least it passes through the head. And then here we have 5 times. No, we have 1, 2, 3, 4 times actually. But in this case, since we are around the borders, you'll see we have this 1 time, and that's practically all. So we see that in this example, or in this case where we are around the borders, this influences the outputs in a smaller way or exerts less influence on the values we get in this feature maps which are generated. So in an example where this, let's suppose an example where all this wasn't there and that where our information lies most is this, you'll find that it would have been better to at least pass through this head region, just as we did with this here, where we passed through the head region 4 times and we're able to extract very useful information from this image because our filter goes through this many more times. Now to remedy this situation, we have the pattern. You see that when we increase the pattern, so let's take this to 1, we've increased the pattern. Let's increase the pattern to, oh okay, yeah, let's fix to just 1. Anyway, we just increase the pattern to 1, and then we'll retake that example. Now retaking the example, we'll see that if we maintain our filter size of 2, this filter here will at least touch the head, although slightly, and then the second one does this twice. So in this case, our filter touches the head twice as compared to previously where it touches the head only once, and hence this useful information has more influence on the output features which are being generated right here, and which is very important, as practically that's what we're trying to do. We're trying to extract information from this input and pass to the output. Another hyperparameter which we could look at is a stride. Now note that for now we've looked at this one, this, and this. So here's what we call the hyperparameters. We have the stride, and we'll understand shortly how this works. For now we're dealing with a stride of 1. Why 1? Simply because you just slide in through one step before going to the next. So you just slide 1, 1, 1, and so on and so forth. Now if we move this to 2, we start from this position right here. Let me fix that. You start from this position. There's a problem. We get back to 1 and back to 2. You notice that as we go to 1, this turns blue, and then to 2 it turns red. And the reason why it turns red is because there is no valid output, or there is no whole number which with a stride of 2 can produce an output. So in fact what we're going to do is we modify this input right here. So modifying this input, this works now. So it's possible for us to leave from this input of 6 to this output, but with a stride of 2. So let's now understand how strides work. We start with this. Notice now how we're going to skip 2 steps instead of just 1 step. So as we go, you see we skip 2 steps. Notice 2, 2, and that's it. So we move to the next. And now even moving downward, you see it's not like with a stride 1 where we just had 1 step. Like with a stride 1, we just did this 1 step. But with a stride 2, we're going 2 steps below. So that's it. Now that said, increasing the size of our stride actually reduces the size of our output, and hence reduces the amount of information we extract from the inputs. And so in general, we get better results by working with smaller kernels and smaller stride values, since we're able to extract more information from our inputs. Generally, the kernel size is used as 3. The kernel size of 3 is generally used in practice, and a stride of 1. So we may decide to use padding or not. And the new formula when we include the padding and the stride is given as such. So we have the output equal the input size minus the filter size plus 2 times the padding divided by the stride plus 1. In this case, if we have an input size of 6, so here we have 6 minus filter size 3 plus 2 times the padding, what's our padding? 1, so it's plus 2, divided by the stride. Stride is 1 and plus 1. There we go. We have an answer of 3 plus 2, which is 5, and then plus 1, which is 6. So that's how we obtain this output size, right? Also note that one good thing with working with a library like TensorFlow is when you don't know the exact pattern to use, such that you have particular output size, you could specify the pattern to be valid. Once you specify the pattern to be valid, TensorFlow automatically calculates the pattern for you such that the output you want matches up. Up to this point, we've been supposing that our input image is 2-dimensional. That is, we have a height and a width. Now, what if we use the kinds of images we have in real life, that is 3D images, where we have the red channel, the green channel, and the blue channel. So if we have this RGB image right here, RGB image, we'll see how we get the output. Now the way this is done is quite straightforward. So what we have is, in this case, we include this pattern. So you see it's been 0 padded. We've included this pattern, and then we have our kernel right here. Now notice how we have this kernel, and then it goes through this first part, or this top left corner, and what we do is we multiply each value right here. We have -1 times 0 plus -1 times 0 plus -1 times 0, and so on and so forth, up to plus -1 times 0 right here. You have -1 times 4. So basically what we're doing here is kind of like a dot product. So we're taking all these elements, multiplying by their corresponding elements, and then adding all this up. Once all this added up, we should have 41. So you could take this as a simple exercise, and then you should be able to get 41. And then we have this other kernel right here, where we repeat the same process. We have this, and then we have this kernel, we have this. So here, what we do is we have we take this, we obtain this value, take this, obtain this value, this, obtain this value, and then we add all this up to get this answer 41. Now note that we also have the bias, which we've not yet included. So for now we have this 41. Now we move to the next step. So we slide through next step. Yeah, the stride is equal to 1 actually. From here we do the same process, -1 times 0, this -1 times 0, added up, and all of that. So all that added up, all this added up, all this added up, we have 12. We repeat the same process right up to the end. So that's how we obtain our output right here. So you could also check out on this other more visually appealing example in the CNN Explorer website. So here we double click on this, and then we see exactly what's going on. We have it here. You see how we're forming this output by sliding through the kernels over the inputs. So here I click on this, you see I slide through this, and you see how all these values are multiplied and then added together to form the output. So that's it. From this point, we move to this explained visually project by Setosa. Filtering is a course part of image processing, and since we're dealing with image data here, it's important for us to better understand how this works. So right here, we'll choose a kernel or a filter. Let's pick this sharpen filter right here, or this sharpen kernel. Notice how once we pick a kernel, these values change. That's the values of the filters actually change. Let's take this outline, you notice the change. Now let's keep this outline, and then we notice that every time we hover over this input image, we have the values right here. That's to the right. So for now we have this, and then let's notice that here we have this -1, that's -1 times at this position. Notice at this position we have the value 255. So 255 times -1 plus 255 times -1 plus unknown value, unknown here because we are the borders, so there is no value. And then we have 249 times -1, 255 times 8, 233 times -1, 255 times -1, and then all this sums up to give us a given value. Since we have this unknown values, here is unknown, so we have no value there. But if we change this position and then we fit around the I region, you see we have a value of -533. So we notice that no matter the image we put in here, we'll always get an output where the outlines are being highlighted. So if you check out this image which we just imported of Elon Musk, you see that the output is this image right here which highlights the edges. And so as is explained here, they highlight large differences in pixel values which generally occur at the edges. So around those regions, you see these large differences have been outlined as compared to this zone here where there's no difference. And since there's no difference, we just have this black region. So here again, you see that we have the filter. That's it. This is the exact same value we have right here. We have the filter, and then this example shows us how this output is gotten. Now the major difference between what we're doing right here and the convolutional neural networks is that with this we know this kernel values. So we know that we have this matrix -1, -1, -1, -1, 8, -1, -1, -1, -1, which is an edge detector. So we know this, and then we know the obvious output. But with the convolutional neural network, or with a convolution layer to be specific, what we do is initially we just initialize these values and we let the model during training to learn these values automatically. So these values are learned by the model during training automatically. One of the very first convolutional neural networks, or ConvNets, was built by Yann LeCun in 1989. And right here we have the structure of this ConvNet known as the LeNet. This LeNet takes in an image. Here we have a 28 by 28 by 1 image. Here we just have one channel, black and white image, and then we pass this through a convolutional layer, which we've just seen. After passing through the convolutional layer, we have the sigmoid, but also note that here we have a 5 by 5 kernel. We have +2 padding. So if it's 0 padding, we'll add zeros around our input and then add another 0 or another group of zeros around our features. Then from here we have this output 28 by 28 by 6. So shortly we'll see exactly how this output is gotten. So we've seen we have the sigmoid activation. From here we have the pooling layer. Now this is a subsampling layer, and we'll understand how it works. So we have 2 by 2 average pooling kernel and with a stride of 2. From this we have another convolutional layer with 5 by 5 kernel. Here is no padding, and we have this output activation, pooling, flattening. With flattening, all the features have been modified, so we'll leave from this 3D tensor to a 1D tensor. And then we have this dense fully connected layer, followed by sigmoid, followed by another dense fully connected layer, followed by sigmoid, and finally we have this dense layer with output 10 neurons. And the exact reason why we have this output of 10 classes or 10 neurons, since we have 10 classes, is because we were predicting whether an input is either a 1. So these inputs are images of handwritten digits. So we want to predict whether the handwritten digit is a 1 or a 2 or a 3 up to 9. And so here we have this, and then we also have a 0, so that makes 10. So 0 to 9 gives us 10 possibilities, and that's why we have 10 different classes right here. Now for the AlexNet, it was built to correctly classify whether an input image belongs to one of 1,000 classes in the ImageNet dataset. So here we have this AlexNet with a different architecture, as we could see right here. And now we'll go ahead and understand how all these outputs are gotten. And so we'll be rebuilding the LeNet architecture, but this time around considering an input 64 by 64 by 3. So right here we have the RGB channels. We have R, G, and B. If we pass this input now through this convolutional layer, we're gonna have this output. And how do we get this output? To get this output, we have to take into consideration these parameters which have been given to us for the convolutional layer. That said, the filter size is equal to 5. So we have here filter size of 5. There is no padding, stride equal 1, and then the number of filters equals 6. We'll calculate the number of parameters shortly. Anyway, these are the 4 most important parameters. So here we have this, and this is what we call our filter. We have this filter. You see that we have the dot products which are computed to get the outputs as usual. And so we take this, like these are like our R, we have this, then we follow through with this, and then we follow with this. So we take this and then compute the dot products and with the other two, and then from this we add all this up to obtain each and every value for this very first feature map right here. So to obtain this feature map, we are using this filter. Now this shows us clearly that when we specify that the number of filters equals 6, it doesn't mean we actually have just 6 of this, as you may feel like number of filters equals 6 means we have 6 filters stacked like this. Here we have 5 and then 6. So we may feel like we have just 6 stacked like this, which is not actually the case. What happens is we have 3, there's this 3 channels, and then each of our filters also have the 3 channels, as you could see. And so what we call a filter here is this 3, or rather is this 5 by 5 by 3 kernel right here. Now we've done the computation and we've had for this, we repeat the same process. So we take this for the R, we repeat this, and then we obtain this next. We do all this the same way up to this position, and then we have this right here. And that's why when we have 6 filters, we're always gonna have 6 channels. Then if you do 5 by 5 by 3 and all that times 6, so if you have 5 by 5 times 3, that's 75. 75 times 6 should give you a total of 450. And since for each of these filters we add the bias, that is, we have an extra bias for each of these filters. We have 1, 2, 3, 4, 5, 6 biases. So adding this plus 6, we have 456 parameters to be trained. So here we have 450 weights and 6 biases. That said, we've understood why we have the 6 channels. Now, how do we obtain the 60 by 60? The way we obtain the 60 by 60 is by applying this formula, which we've seen already. So here we just have the output equal 64, filter size 5, so we have -5, padding no padding, so padding is 0, stride 1, so we have 64 minus 5, and then plus 1. This gives us 64 minus 4, which is equal 60, and that's how we have this output right here. From here we move to the subsampling pooling layer. For the pooling layer, we have these 2 parameters. That's we have the number of filters, and then, or rather, we have the filter size, not the number of filters, the filter size, and then we have the number of strides. To obtain the dimension for the pooling, the formula is slightly different, obviously, because here we don't have the padding. So we have x minus f divided by s plus 1, and then we'll leave from this to this feature map right here. Notice how we still maintain the number of channels, but our input feature map has been subsampled. For the particular case of max pooling, if you want to understand how this works, let's say we are at this position. Let's take this position. Let's take a position where we have some values. Notice how as we pick this value, you see the max is 0.02. So you should look around, look at this. So we see here the max is 0.08, and so on and so forth. So basically what we're doing is we're just simply sliding through the whole image, and then for every, since our kernel size is equal to, we have a 2 by 2 kernel size here. So for every 4 values, we are going to pick out 1 to represent them, and in this case this 1 is the max. In some cases we'll instead take the average of this. That's known as average pooling. But for this max pooling, which is the most commonly used, we take the max of all these different values. That said, to obtain this, we have x, that is in this case we have x equals 60. So let's take this off. X equals 60 minus f equal 2 divided by the stride. Our stride is 2, and then plus 1. So 60 minus 2, 58 divided by 2, 29 plus 1 gives us 30. That's how we get this. We still maintain the number of channels. Here's another example showing even more clearly how this max pooling works, or pooling in general works. So if we have this input, so we're picking out just one of this. Suppose we're picking out just one of these channels, and we have this. We are going to have our kernel 2 by 2. That's it. And then what we get as output is 0, since the max of 0, 0, 0 is 0. We have a stride of 2. So notice how we've shifted by 2 positions. Stride 2, and then the max here is 2. We move again, stride 2, max now is 2. We move, you see max is 1. You move, max is 0, and then you go to the next, max 3, and so on and so forth. So that's how we obtain this new feature map right here. Notice how we have this is 5, 10, 5, 10, and then here we have 5. So we leave from 10 by 10 to 5 by 5. After this subsampling layer, we have the activation. We've already looked at activation in the previous section. We've seen the sigmoids, and we've seen the ReLU, we've seen the tanh, and we've seen the leaky ReLU. So that said, we understand that, and now we move to the next convolutional layer. Or filter size equal 5, padding no padding, stride 1, number of filters 16, number of parameters 2416. So you could take this as an exercise to be able to show that the total number of parameters we have is 2416. That said, we're gonna have this output right here. We have the ReLU added, and then we have this output. So we have this output 26 by 26 by 16. Recall, number of filters dictates the number of channels right here, and not the filter size. It's the number of filters. And then this 26 by 26 is gotten by using the same formula we've seen already. From here, we have another subsampling. We've understood that already, and then we flatten all this out. So after doing the subsampling, we have this 13 by 13 by 16, When you multiply all this, it should give you 2704. And this is what we call the flattened layer. So we pass this through a flattened layer to obtain this. Now this takes each and every value we have here in our feature map and then just simply places it in this one dimensional output right here. Then from here we have the dense layer, which we're used to working with already, and then we have 1,000 neurons in the output, and finally we have 200 neurons. In our case, we should have 2, since we're actually predicting whether it's a parasite or it's a non-parasite, so we should just have 2. Anyways, we understand all this now, and we should be ready to dive into the code. Before moving on to the code, let's get to see what the feature maps of a trained convolutional neural network looks like. As you could see right here from this example from the Stanford website, we have this car which is passed into a convolutional neural network, and then in its output we have it predicting a car. As you can notice, this first layers actually serve as filters for low-level features like the edges. So you'll notice that this input or this feature maps from the first layers produce visually interpretable outputs. Now you will notice also that as we go further or deeper, we have this outputs which are less visually interpretable, and the focus more on high-level features like the car parts, which permit us correctly classify that this image contains a car. And so the first layers are for feature extraction, and then the last layers are for classification. Both subsections actually need each other, as if you do feature extraction and you don't have layers which are able to permit us correctly classify this image, then we will not achieve our goal. And in the same sense, if we have a good classifier but we get this kinds of inputs directly where we've not extracted useful features from them yet, then our classifier is not going to perform well. You could also check this ConvNets MNIST demo by Andrzej Karpathy, where he trains a model on the MNIST dataset. Here we have our model, the input conv pool, and softmax. So here we have this on MNIST dataset, and then we're having this passed in. As you could see, notice how in this first layers the feature maps actually contain much more visual content as compared to this final layers right here. See, if you look at this final layers, you see that we have these feature maps which instead contain content which permits us say whether a particular input belongs to a particular class. If you want to build convolutional layers with TensorFlow, you could make use of this TensorFlow Keras model right here. So that said, we're just gonna come to the layers, tf the Keras, and then we pick layers, and then we'll find the conv2D layer. So here is the layer we're searching for. Double click on that, and then here we go. We have the arguments. That's what we pass in this layer. The filters right here corresponds to the number of filters. So let's take this off. Here is the number of filters. We've seen this already, NF, and then the kernel size corresponds to the filter size. From there we move to the strides, which take a tuple. Let's take this off and check this out. So here we have this tuple actually, and then what's important to note here is the fact that if you want to do striding of say 1 2, that is 1 2, then in the height dimension your striding is going to be equal 1, and then the width dimension is trying to be equal to. So if we have this feature map right here and we pass a kernel, we are going to be sliding and skipping 2 steps in this horizontal direction, while when we're going downwards, we are going to be skipping only one step. So that's what this means. Now, in the case where we are having exactly the same number of steps sliding horizontally and vertically, then the striding, like in this case, can just be given as equal 1. From there, we have the pattern. By default, the pattern is valid. Here we're told that for the pattern, if the pattern is valid, it means there's actually no pattern, so we have 0 pattern. And then when the pattern is same, the result of the pattern, or we pad it with zeros to ensure that the input dimension equal the output dimension. Also note that this is only possible when the stride is equal 1. So that said, if we have a feature map like this, let's say we have 60 by 60, and then we want to pass this through a conv layer to get an output feature map. And if we want this output feature map to be the same dimension as the input, that is 60 by 60, then all we need to do is to specify that the pattern is same. So once we have this, the output will be the same as that of the input. From here, we have the data format. Now note that there are generally two kinds of data formats. That is, we have height. So for an image, we have the height, width, and then the channel. So if we have a 224 by 224 by 3 image, then we actually making use of this data format. Now we could also use this format where we start with the channel. So we have the channel by height and by width. And so here we have 3 by 224 by 224. Note that by default we have the channel last. So by default we have this first convention last right here. But if you want to take this convention, all you need to do is to specify that you're working with the channels first. Then from here we have the dilation rate. So we'll look at this GitHub repository by Vidou Moulin, where he uses animations to explain how convolutions work. You could scroll down and you'd find the dilated convolution animation, which when we click on, we have this. So there we go. We have this example in which the dilation rate is equal to. So the way this dilation works is we have this kernel which initially had no spaces between its values. So we had something like this. We had this 3 by 3 kernel. And now what we do is we have this spaces or this holes between these different values. And so now what we get is some sort of 5 by 5 kernel right here. If we're working with a dilation rate r equals 3, then instead of a single hole here, we are gonna fit in 2 other holes. So we're gonna have this, we just have 1, 2, and then we fit this, and then we have 1, 2, and then we fit this. So that's how we build this out. We have this and then that. Now to get the shape, we have 1, 2, 3, 4, 5, 6, 7. So we have a 7 by 7 filter now. It should be noted that the dilated convolutions are used in problems where we want to keep increasing the receptive field as we keep going deeper in the network while maintaining the number of parameters. The next argument is the groups, and according to the documentation, this is a positive integer specifying the number of groups in which the input is split along the channel axis. This means that in this case, for example, we could break this up into 3 different groups. So we have 1, 2, and then 3 groups. Then each group has its own group filters. And then the output is a concatenation of all the group results across the channel axis. From here we have the activation, which we've seen already, and then we'll say whether we're going to use the bias or not. We have this kernel, that is the weight initialization, and then we have the bias initialization. We have this regularizers, which we'll see subsequently, and then we have the kernel and bias constraints. in order to create our convolutional neural network, we're just going to make use of this sequential API which we had built previously, and then we'll define the input layer. So here we have this input shape 224. We had defined this as im size actually. So we have im size, that's it, by im size by 3. We could also define number of channels, but let's just let it to be equal to 3. Then from here we have no normalizer, and then we have this conv2d layer right here. So we have this arguments which are default, so we wouldn't bother to check on this. We will take this off, and that's fine. So we'll have this. There we go. We have our conv2d, which we copy, or rather we cut that off, and then we put this after the input layer right here. So there we go. We have our input layer. We want 6 filters, and then with a kernel size of 5. So that's it. Our stride, we could take this to be equal to 1. There we go. Padding is valid, so that's what we expect. And then just here we have our activation. So we have activation, we could say sigmoid. We have the sigmoid activation since we're replicating the ReLU, or rather the LeNet architecture. So there we go. We have the sigmoid, and that's our conv2d. From the conv2d we have a max pooling layer. Let's take this off. Let's take this dense layers off. From this conv2d we have the max pooling layer. Now what we could do is we could just simply import all this. So let's go ahead and say import the conv2d, max pool 2d, and the dense layer. Coming back to our documentation, we could check out on the max pool 2d. So there we go. We have max pool 2d. We'll specify the pool size, which is equal to, and then the number of strides equal to. Padding is valid, and data format, we're not going to specify that. So we have our max pool 2d, and then this pooling size with the strides. We copy that. We actually done with a stride of 2, so we replace that. We have a stride of 2. The next step is this one right here, similar to what we had seen previously, with the difference that now we have 16 number of filters. And so we could simply copy this and then paste this out right here. We have conv2d, max pool 2d, now conv2d, max pool 2d, and then here we have 16 number of filters. The pattern is valid, activation sigmoid. Then this next max pool 2d is still the same as what we had previously. And so we move on to the flatten layer. We add this here, we have flatten. There we go, and we run that. So while that's running, we just simply come right here and then add that flatten layer. So we have this flatten layer which is in charge of flattening this or converting this into this 1D output. From this flatten, we now have a dense layer, which is what we've seen already. So we just have to put this dense layer here. Let's take this like this, and there we go. So we have our dense layer, and then the activation is sigmoid. So we're respecting the activation used in the LeNet paper. Then we have this here, we could take 1000, and then we have that. We add another dense layer, add this other dense layer. Now we'll make sure that as we create this final dense layer right here, it has an output of 2 neurons, since we are dealing with a binary classification problem. So that's fine. Take this here and then run our model. We have it that input layer is not defined, so let's simply add that here. We have the input layer. We run that and then check that out again. Here we go. We have this input layer which we run, which we add, and then we run this. Now everything is fine. So that's it. We have 45 million parameters and no non-trainable parameter. Notice how this dense layer here is responsible for a huge percentage of our parameters. So we could reduce this. Let's take this to 100 and then this to like 10. Let's run that again, and there we go. We have a smaller model this time around. A point to note is this number of parameters which we pre-calculated here. Here we have 456 and here we have 2460. And we'll see how we get exactly this number of values here. For the dense layer, it's quite obvious as we just have 100 times 10 plus the 10 biases, giving us 100 times 10 is 1000 plus 10, giving us 1010. And then here we have 10 times 2, 20, 20 plus 2 biases, giving us 22. It should also be noted that there was a slight error here, as we don't have, like with this we have 5 by 5 by 3, but here is 5 by 5 by 6, since we have the input number of channels equals 6. So this means this is 5 by 5 by 6, and here is 5 by 5 by 3. All this 5 by 5 by 3 and all this 5 by 5 by 6. And if you take 5 by 5 by 6 and multiply it 16 times, you should have 2416. It should be noted that here we're trying to replicate the LeNet architecture, and this is in no way the state-of-the-art kinds of models we use today. So in the section under corrective measures, we are going to use even better models. For now, let's just work with this. Hello everyone, and welcome to this session on error sanctioning. The error sanctioning method, or the loss function we shall be using in this section, is going to be the binary cross entropy loss. And right here we have this binary cross entropy loss formula. So here we have negative y log y, or y chapeau, minus 1 minus y chapeau log of 1 minus y chapeau. To understand this formula, we'll start by taking this log plot into consideration. So our log function is this plot we have right here, or it could be explained using this plot right here, where you see as we approach 0, as we go into a 0, the log approaches negative infinity. In this section, our values for y will fall under the range 0, 1. And so with that, we'll consider that we have a y, because here if we could consider that our y chapeau is what the model predicts. So y chapeau is the model's prediction, and then y itself is the actual or expected prediction. So here we have model's prediction. Take that off. We have model's prediction. There we go. And then right below, or just here, we have the actual prediction. So now here we have actual prediction. So this is what we expect, or expected prediction. So that's it. We have y chapeau and we have y. Now when you or let's suppose that we have or the model predicts, let's say this is what the model predicts, and then this is the actual. So here we have model, and then we have the actual prediction. So let's suppose that the model predicts 0, an output of 0, and that the actual prediction is the level 0. In that case, you would have yi. Let's even take this off. Let's take this off here and have that to be y and y chapeau. So here we have y chapeau, which is what the model predicts, and then this is what we expected to be predicted. So here we have 0 and 0. So we would have 0, but because we're multiplying this 0 by a very large negative number, all here multiplied by a very large negative number, we're gonna have output of 0. And then on this other side, we have 1 minus 0, which is 1, times the log of 1 minus 0, which is a log of 1. But when you look at this log, like you get back to this plot right here, you have the log of 1, which is 0. And so because the log of 1 is 0, we have 1 times 0. And so overall, we have 0. So you find that the error at the end, or the loss, is 0. And this makes sense because we want to have a loss function which is such that when our model predicts exact as or the same output as the actual prediction, then we should have an error of 0, or a loss of 0. Now let's suppose that we have 0 and then 1. In that case, you would have 0 or 1 right here. So this is going to be 1. This is 1 times a large negative number. Here we have log of y, or chapeau, which is log of 0. It's a large negative number, as we've seen already. So 1 times that large negative number leads to a large negative number. So we'll have negative, let's call it L. Let's call this L. Here we have negative L. And then here we have 1 minus 0, which is 1, times the log of 1 minus 1, which is a log of 0. So we have 1 times a large negative number again, which leads to us getting L. So here we have L. So overall, we're going to have negative L minus L. So we would have negative 2L. So we have a very large negative number. So we are penalizing the model for predicting the wrong outputs. Actually, when you have this negative times this negative will give a plus here. So this negative times this gives plus, and here we have minus. So we have minus here, and then here we have 1 times log of 0, which is negative L. So here we have negative L, and L minus L is 2L. So we have a large positive number. But what's important to note is the fact that we are penalizing the model for the wrong prediction. Now, if we have 1 and we have 0, we would have something similar. Then if we have 1 and we have 1, then we should have a 0. We can now try out this binary cross entropy loss method on in TensorFlow with a simple example. So let's say we have y true, and there we go. We have y true. Let's give it some values. Let's say we have 0, we have 1, we have 0, and then we have 0, and then we have y pred. Let's say we have 0, we have 1, we have 0, and then we have 0. There we go. So we have our binary cross entropy loss, which is equal this TensorFlow keras binary cross entropy. There we go. And then now we could simply call that. So let's print out BCE, which takes in the y true and then the y pred. We run that, and let's see what we obtain. Getting an error, cannot convert 0.0 to integer tensor of type int32. Well, our y pred should be a float. So let's have this point and then run that again. And there we go. You see we have an error of 0, which makes sense because the y pred is the same as the y true. Now let's suppose that we have 0.8. We have, instead of 0, we have 0.8. Instead of 1, we have 0.2. Instead of 0, we have, say, 0.9. And then instead of 0, we have, let's say, 1. We run that again. And then we'll find that the loss now must have increased as compared to when we rightly predicted all the values. Now let's go closer to the actual values. Let's reduce this. Let's increase this. And then let's reduce this. And then let's say this is 0. We run that again. And you see now that compared to the 5 we just had, now we would have a smaller value. Though not 0, but a value approaching 0. So you see we have 0.1, which makes sense because our predictions are now much closer to y true values. And so that's it. We understand the binary cross entropy loss. Now we will dive into compiling our model. So we just need to have model compile. And this compilation will consist of specifying the optimizer, which is Adam optimizer. We have learning rate equal, say, 0.01. Then we have the loss, which we've just defined. This loss right here, which we've just defined, is the binary cross entropy loss. So we have binary cross entropy. Getting back to the documentation, you would find that we have this from logits parameter right here. If the output value or values range between -infinity and +infinity, then we want to use the from, or we want to set the from logits to be true. But if it's a probability, that's if it lies between 0 and 1, then we would have from logits to be false. Now, if you get back to our model, you would find that we have the sigmoid activation, and the sigmoid activation makes or ensures that we have values ranging between 0 and 1. And so because of that, we have our from logits set to false, and which is the default value for the from logits argument. We also have the label smoothing. You could check out documentation, float in the range 0 and 1, where when we have 0, there's no smoothing. That's it. By default is 0, so there's no smoothing. And when it's greater than 0, we compute the loss between the predicted labels and a smoothed version of the true labels. So where the smoothing squeezes the label towards 0.5. So larger value of label smoothing correspond to heavier smoothing. Now, if we get back to the code, what we'll actually, or what they're trying to say here is, if you have the label smoothing set to say 0.1, then by just having 0.1 here, and here 0.9 and 0.1, and then let's say 0, and running that, you see we have a loss of 0.35. Well, this is 0.1, this is 0.9, this is 0.1. Let's say we have now 0.1. We should have a loss, an even smaller loss. And this is because instead of comparing 0, or instead of comparing the 0 we have here with 0.1, we are now comparing 0.1 with this 0.1, and that's because we'll specify the label smoothing value to be 0.1. So you could see again that having all this the exact same for y pred and y true doesn't yield zero anymore. If you go back to 0 and you run this, you should have 0. Let's get back to 0.1 and then modify this y pred. So you see when you have 0, we should have an output of 0. So what we're getting here is for this output 0. Going back to 0.1, you would find that when you increase 0, or when you move 0 to 0.1 and then 1 to 0.9 and here 0 to 0.1, that you have a smaller output for the loss. And so that's it for this section. In the next section, we'll dive into training our model. In the section on model training, we'll just simply start by calling our fit method while specifying the train data set, the validation data set, number of epochs, and set the variables to be 1. So let's run this and then see what we obtain. We get an error. Sequential or input 0 of layer sequential is incompatible with the layer expected known by 224 by 224 by 3, but the found shape was 224 by 224 by 3. So this tells us that our inputs, or what we've gotten here in our train data set, is unbatched. So let's get back and batch our data set. So here already we had carry out the splitting, and then we had our train data set, then we had this mapping. So from here we could do batch, and we specify the batch size. Yeah, we specify the batch size. There we go. So let's include batch size right here. We have batch size, and we say we want to have 32. So that's it for the train data set. Now let's repeat the same for the validation and then the testing. So well, let's carry out shuffling. We have before batching, we'll shuffle. So we shuffle, and then we specify a buffer size of 8. Reshuffle each iteration set to true. There we go. We have the batch, and then we also prefetch. So here we have prefetch, and then we have TensorFlow data, auto tune. So here we have auto tune. Okay, so that's it for the train data set. We could now repeat this for the validation. So let's have that pasted. Now we have val, take that off, and here we have test. So we have val, we have test, and there we go. So let's run that again and see what we obtain. So here we have batch size not defined. Let's run that again, and that should be fine. So you run this, and then you see that we have an output now which has been batched. So we should have the batch dimension. So that's it right there, and you see we have 32 labels now. So let's get back and continue with the training. So let's run this again. Now this should be fine. We get in this other error. Logits and labels must have the same shape. So we received this output batch by 2 instead of batch by 1. And this makes sense because the way we created our outputs, or if you look at our outputs, we had here. If you look at this output labels, we have just for each and every sample, we have just one output. So it's not shaped batch by 2. So let's get back here in our model and modify this. So instead of 2, we should have 1. So if we are parasitized is 0, uninfected is 1. So initially we're having 2 like this. We're supposing that we would have if it's parasitized, then we would have 1 and then 0, and then if it's uninfected, then we would have 0 and then 1. But we could simply just take all this off and just say if it's parasitized, we have 0, and then if it's uninfected, we have 1. So now we have an output of 1 unit instead of 2. So let's take all this off, recompile our model, and that should be fine. You can see now that our training has started. You could change the runtime. Make sure you're using a GPU. You see it's quite slow because we're using a CPU. So if we take the T4, that's it. We're going to have to restart the runtime. So let's go ahead and restart. Let's run this again. And go ahead and restart the training. So let's have that. We recompile and we restart the training. So we've restarted the training, and as you could see, we have this loss and validation loss values. The training is quite slow with respect to how the loss values are dropping, and so we could get back here and make some adjustments. Firstly, we'll use the ReLU activation instead of the sigmoid. So we'll replace all this with ReLUs. Take this off, and we have ReLU. And then also here in this final layer, we are going to leave this at sigmoid because we want our outputs to lie between 0 and 1. Then we'll modify this kernel sizes. We'll go from 5 to 3. And then we shall include batch normalization. So just after the conv layer, we have batch normalization. And then just after this, let's add the comma. Just after this, here we have batch normalization. There we go. We have batch normalization, and we'll just copy this and paste out here. So after the dense layer, we would have batch norm. Take that off. After this dense, we also have batch norm. So we include in the batch normalization such that so that we could recenter and rescale the different features we generating from our layers. So let's go ahead and stop the training and then recompile our model. So we have that, we recompile, and let's just copy this here and paste out here and run that again. Now, just by looking at the first 2 epochs, we see clearly that our model's loss now drops much faster as compared to what we had previously. So that's it. You see that the batch normalization plays a great role in stabilizing our training and hence making it much faster. So we have this. We will now add the metric. So metrics, we would have binary accuracy metric. Make sure you import this. So we have binary accuracy, and the way accuracy works is quite simple. So here we have, or let's suppose that we have 100 samples. So we have 100 samples, or let's say we have 100 samples in our test set. Then if our model predicts correctly, let's say 80 samples, and doesn't correctly predict the remaining 20, then our accuracy is going to be 0.8 or 80%. So it's just that simple and straightforward. So that's what we're going to have when we include this binary accuracy metric right here. So you can see this is dropped. The val loss starts increasing slightly. Anyway, let's just stop this and then we restart the training. So let's take this off. There we go. Let's recompile Let's recompile, and then we restart the training. With the training now complete, you could see here our model loss, which drops, and we also have this model accuracy, which goes right up to 0.95. So our model now performs much better with the batch normalization, and we have this 95% accuracy model. Hello everyone, and welcome to this section on evaluation and testing. So far we've built and trained our model, and we have reasonable performance. Let's go ahead and evaluate this model. So here we have model evaluate, and then we could pass in our test data. So test data set, we run that. The result we get now is about 93% for the test data set. So that's the accuracy for our test data set. Now let's dive into prediction. So we've trained our model, we've evaluated it. Let's suppose that we have some data drawn from our test set, and we want to be able to say whether it's parasitized or uninfected. Now before moving on, we'll define this parasite or not method. Parasite or not, and then it takes an x, and if x is less than 0.5, if x is less than 0.5, then what we want to do is return the string p, that's parasitized, and else we want to return the string u. So that's it. So it's either parasitized or uninfected. Now let's run that, and then we have model, or we could actually say Lunet model. Let's define this as Lunet model. Well, since we already had model, let's just leave it that way, but you could define it as Lunet model to separate it from all other models we'll be working with in this course. So we have this model, and the model, we make use of model predict, that's a predict method, and it takes in a test data. So we have test data set. We could take a single one, and then we get the output. Now note that here we have a batch of 32 elements. So if you output this, you would have an output of 32 elements. So after this, we could pick out a single one out of this. Well, let's just get the output first. As you could see, we have the 32 different outputs. Now we could pick out just the very first one. So we could run that, and you see we have our output. Now we want to get it as parasitized or not. So parasite or not, parasite or not, and we get that. So let's print this out, print that, and there we go. So let's run this again and see what we get. You see we have P, meaning that it's parasitized. Now the next step will be to visualize our predictions. That's to see what the model was supposed to predict and what the model actually predicted. So let's go for image label. We'll just do 9 predictions, or 9 images. So for that, in test data set, let's take a single batch. Now for I in range 9, what we're gonna do is we're gonna have this subplot. So we have our subplot, and it's 3 by 3, and then we increment I. Then from here we have plot im show. We have the image I, actually, because we have a batch, so it's image I. And then once we have that image, we are gonna have a title, which is gonna be made of what the model was supposed to predict and what the model predicted. So we have this title, which is made of well, yeah, we have parasitized or not, so we just say parasitized. Well, the function name is parasite or not. Okay, so it's parasite or not, and then it takes in the output, the label. So we have here label, send that to numpy, there we go, and then we pick I because it's that specific index. And then now we have, like, that's after getting this label. So here is a label, the next thing we want to have is what the model predicts. So we have this here, then now we have plus, then we could have this slash, well, plus, there we go, and then we have again parasite or not, which takes in the model or the output of the model. So model predict, we have model predict, and this model predict takes in the image. So here we have image I, and then and that's it. So there we go, we have, it takes in our image, and then we have, well, let's do this way instead. When this takes in the image, we have I, and then we have 0. There we go. So that should be fine. Then finally we have, let's take this way, we have plot axis and set that to off. And there we go. We could now run this and see what we obtain. You could see from here that we have most of the predictions right. Out of the 9 predictions, we only have 1 wrong. That's this one. So essentially here, the model was supposed to predict this as parasitized, but it predicts this as uninfected. Hello everyone, and welcome to this new section in which we'll look at different ways of creating models other than the sequential API which we've seen so far. In this section, we'll look at the functional API, we'll look at building callable models, we'll look at building model via subclassing, we'll also look at building our own custom layers. Previously in this course, we said that there are 3 ways in which models are built in TensorFlow. That is the sequential API, using the functional API, and then finally model subclassing. As of this point, we have been using the sequential API, as you could see right here. Now, you may ask yourself, why do we need to use a different method in creating TensorFlow models when so far we've achieved close to 99% train accuracy and around 95% test accuracy? Now, as you may have noticed, so far all the models we've been building have taken up this kind of structure where we have an input, we have the first layer, the next layer, which has been stacked in this sequential manner right up to this very last layer here, and then we have the output. So the question we could ask ourselves is, what if we have a model which takes in, say, 2 inputs and has 3 outputs? These kinds of models are very popular in deep learning, and we shall look at them subsequently. But before getting there, you could just imagine a problem where instead of classifying whether we have a non-parasitic or a parasitic cell, we want to know the exact position of that parasitic cell, or in general that cell in the image. You would find that you would have one output which classifies whether it's a parasitic or not. So we have this first output, parasitic or uninfected, and then this other output which gives us the position of the cell, or the exact position of the cell in the image. So here we see already how we could get 2 outputs from this. Let's take this third output out. So here we see we could have, let's even take this one. So here we have this 1 output, 2 outputs model, and with a sequential API we can't really do this. So that's why working with a functional API is very important. The next point is, we'll be able to create more complex models with the functional API. So there is this model known as the ResNet, which is very popular in deep learning deep learning for computer vision. Now, a ResNet like structure will look like this. We have this layer, this outputs have been passed into this next layer, and then we have the outputs of this, which are going to be concatenated with these outputs, and then after this concatenation we are going to pass this to the next layer right here. So if we want to add this layer, we could have a layer here and have that. So as we're saying, we take this output and then concatenate it with this next output before passing to this next layer. And so those kinds of structures or those kinds of models could not be built with the sequential API, and hence the need for the functional API. And then the last reason why we are going to be using the functional API is the fact that we could use shared layers. With shared layers, we could have a layer or a particular layer in our model which has already a predefined way of encoding information. So when we pass information, let's say we have this input, let's say input 1. When we pass this input 1, this layer right here or this encoder produces an output which is going to be different from when we pass in another input I2. But the way it produces its outputs is in a very thoughtful manner. So we could have I1, I2, I3, which all share this layer, and then we have other layers of the model which follow on. That said, we'll look at how to create the functional API. So here we have the sequential, and then just below we are going to create this functional API. Before starting with the creation, we are going to import some classes. So we'll start by importing the input class right here, which is a layer. We import input, and then we have from TensorFlow Keras layer, or rather models, we're gonna import model. So we import the model right here, and we import the input. We run this, that should be fine. We now have this func input, since we're using the functional API, just a way of calling that. We have the func input, and then we have input, which we just called, and this takes in the shape. So here we're going to copy this exact shape we use in the sequential API. We have the shape right here. There we go. We copy that shape, and then we reuse it here in creating this input layer. So here we have that, and then we have your shape. So we've had the shape. At this point, you could start stacking up all these different layers we had stacked up in the sequential, or with this when we were using the sequential API. We started with this here, this conv2d, right up to this dense layer. So there we go. We're just gonna make use of this. So we copy that, and then we are gonna paste this out right here. Now, first things first, we have an output. So first things, we have this layer, that's we have this conv2d, which we've defined, and then we pass in the output from this input layer. So here we have this func input, we copy that, and then we pass this into this conv layer right here. Now once we pass this into this conv layer, we have an output, and that output is this x. And then you should guess that right, we pass this x into this batch norm layer. So here we have x, as you could see, and then we have an output of x. There we go. From here we pass in the x into the max pool 2d layer. So we have this, we cut that, and then we have this x right here. So we'll just repeat this same process right up to the end, and there we go. You see that we haven't done much changes as compared with the sequential API. So that's it. We pass in this input right here. We have x, we pass it in, we have this, we pass in, and right up to this end. Now once we get to the end, we are now going to create the LeNet model from this. So we have LeNet model equal model, which we imported, and then we have the func input. Now here, let's say we have func output. So we pass this last, and then our last output is func output. So we have the input, and then we have the output. So there we go. We can now give it a name. We have name LeNet model. If you look up, we had mistakenly written this right here. So this should be the input image. Here we have our input image, and then we've created a model, LeNet model. And then from here you could simply do lunet model.summary. Now you will notice that we should have exactly the same summary as we had with the sequential API. So let's run that and see what we get. Here we have how many parameters? We have 4,668,297 parameters. There we go. You see we have exactly the same number of parameters, the same number of trainable and non-trainable parameters. So basically what we've done here is we've recreated this model we created with a sequential API. Now we've gotten this, we'll see that we'll have to change absolutely nothing from our code. So here we're just gonna compile our model without changing anything. We have the same lunet model. Now we could also change this. Let's say lunet func, so you see clearly that we are actually using this functional model right here. So we have this func, there we go, func, and that's it. We could run that, and then we recompile right here. So we are not changing any parts of this. We recompile that, and then we train the model. We are getting this error because of the way we named this model right here. So let's have this lunet model. That's fine. We recompile and then we run. So that's it. We're training our model. And here is what we get as results. Now coming back to our model, we'll see that we have this feature extraction unit right here. So this conv layers are responsible for extracting useful features from the images, and then these last layers are responsible for correctly classifying whether the image is parasitic or not. That said, we could build a model known as feature extractor, and so here we'll add this. We have our model feature extractor, which is going to be like similar in construction as what we've done so far. So we just have that copied, and then we have this, but the difference is we are not going to include this final layers right here. We'll only end at this point, and then we'll have as output this here. So this is our functional. Here we'll call this extractor. Let's just say we have this as output. So we have this output, and there we go. So here we have our functional input, and then we have this output, and then here is the feature extractor. So we have our feature extractor model right here. We could do this feature extractor, and then we summarize this. So let's run this and see what we get. So that's it. We have our input, and then we have this output right here. At this point, instead of writing all this we wrote here, we're just gonna call, or let's take from this point. So we have our feature. Let's look at the name. We gave it the name feature extractor model. So here we have feature extractor model. So here's our feature extractor model. See, we take all this off, and then in here we pass in our input. So notice how we're making this model look like a function. So TensorFlow models are callable just like the layers, and as you could see here, this feature extractor model could be seen as a layer, just like the dense layer, the batch num layer, and all other layers. So we've gotten this x from this input which has been passed in our model, and then from here you see we pass this x into this flatten, and we have the rest. So that's it. Let's now rerun this again so you could see what we get as output. And as you could see, we get exactly what we expected. We have the same number of parameters, and there is this difference here where we have this feature extractor. So unlike before where we had the ConvNets, like the conv2d, batch num, max pooling, and the same, like let's go up here, this is actually a feature extractor. So unlike before where we had this and then this, now it has been replaced with this feature extractor right here. That said, we've just built this model using the functional API, and in subsequent sections we'll build even more complex models using this functional API. Models where we're going to use shared layers, we're going to have multiple inputs, multiple outputs, and models where we're going to have even more complicated model configurations. It's important to note that you could mix up the functional API model creation style with that of the sequential API. So here, instead of creating this, so instead of having this feature extractor created like this, we are going to create it using the sequential API. Let's add that, and then we copy out this from here. Copy out this full model with a sequential API. We paste this out, and we take only the feature extraction part. Here we see we take this off, and then we're left only with this feature extraction part. Now let's call this feature extractor. So feature extractor sequential model. There we go. We paste this out right here, and we're fine. So we have our feature extractor model. We run that. That's okay. Let's take this off, and then we'll just make sure we put exactly the same here. So there we go. We paste it out, and we rerun this. You see, we should be able to get exactly the same output. See, we have exactly the same output, and here, instead of our feature extractor model, we have your sequential layer. So that's it. This shows us that we could mix up these different ways of creating models. From this point, we'll look at the model subclassing. So right here we have our model subclassing. There we go. It's important to note that model subclassing permits us to create recursively composable layers and models. Now, what does that mean? This means I could create a layer where its attributes are other layers, and this layer tracks the weights and biases of the sub layers. Before taking an example, let's make this import. So we're going to import layer from layers. We have TensorFlow.keras.layers. We're going to import layer. We run that, and then we move on to create our model using the model subclassing. Now that said, we have this feature, our feature extractor. So we have feature extractor right here, and then this inherits from layer. So it inherits from TensorFlow layer, and then we have an init method and followed by a call method. So that's it. Now let's use the right syntax. Here is a class, here is a method, init method. There we go. You could always check on our free course on Python programming in case you're not versed with all this syntax. So that's it. We have had that, and now just like the way we did when we were creating this feature extractor, let's go back to our feature extractor with a functional API. Actually, here you'll see, let's copy this out and then get back to our model subclassing. So that's it. Here, let's just put this down here, and then we have the super feature extractor. There we go. That init. So that's it. Now that we have defined this, we could now go ahead and use this layers as the attribute for this feature extractor layer. So there we go. We have this here. We have our conv, the self.conv1, which is this conv2d right here. So we take all this off and just place it here, and then from here we have the batch1, which is this batch norm layer right here. Take this and then place it right here. We have the max pool 2d, take that off. We have self.pull1. There we go. So that's it, and then we just repeat this process. So we could have the self.conv2 rather, so conv2, and then we just take up this parameters. Let's take this from here and place it right here. So here, instead of having this, we will just get this, and then the batch run and max pull to remain the same. So that's it for our init method. We now go ahead to build our call method. We have our call method here, which takes this input x, and then here what it does is it permits us call each and every layer we've defined here in this init method. So here we have x equals self. So the value of x is going to change. We're going to pass it through self.conv1, and self.conv1 is going to take in x. This looks similar to the functional API. We have x equals self.batch1. There we go. Batch1, and then we have x equals self.pull1. X equals self.conv2. X, and then self.batch2, and finally we have self.pull2. That's it. So now from here we just return x. Also note that we could pass in a parameter, an argument like the training, which can tell us whether to use a given layer or not during the training process. Nonetheless, for now, all this is going to be used during training, so we have that. Now let's take all this off. We run that. There we go. That's run correctly. Now we should be able to build our model. So here we have this Lunet model, which took the feature extractor model from here. Let's just copy this, and then, but before copying that, we have to ensure that we create this here. So we have feature subclassed. So we have our feature subclassed, which is this feature extractor we built right here. So here we have feature extractor we built. So that's it. Now you could always pass this parameters like the number of filters, the kernel size via this. So you could pass this here. You could specify filters and the kernel size. So let's just do that. So let's say filters takes kernel size, strides, and say padding and activation. So we could pass all this here, so that when we get to this point, we don't need to specify all this. So we'll simply take this off. No need to specify all this anymore. Now we have our activation and all that specified. Okay, we could also include the pool size. Let's include the pool size and this strides here. Okay, so let's just say here we're gonna have 2 times the strides, because we will specify the strides to be 1. So let's take this off. Here we're gonna have 2 times the strides, and we've defined here we have the pool size. So let's take this off, and let's take this off rather. Let's get back. So we take this off and take this off. So that's it. We've defined all that, and now we are ready to pass all these values. So we'll just simply copy all those values, and then in here we'll specify the number of filters. So here let's take 8, the kernel size, let's take 3, the number of strides, we have 1, the padding, here is valid, activation, relu, pool size is 2. So that's it. So we've defined all this. Now at this point, let's ensure that we have this times 2. So let's run this now again, and then we have our feature extractor, but we're getting this error. Let's try to understand why and how to solve this error. So there we go. Scrolling, we have this, Now the reason why we have this error is because of the order in which this conv2d takes its arguments. So if you look at this, I'm trying to get this to come up. Anyway, we just look at the documentation. You see we have filters, kernel size, strides, padding, data format. So you see we have the data format, the dilation rate, groups before the activation. So it's important that we specify that this is filters equal filters, and then here we specify kernel size equal kernel size. If not, it's going to take this to be the data format. So that's it. Strides, padding equal padding, and activation equal activation. So this should be fine. Now we run that again. We have this error, but this time around it's for the second conv layer. So let's just redo what we had done here and take this off. Notice filter size times 2. So here we have filters times 2. We try to do same for the max pool 2D. So here we have pool size equal pool size. That's it. Strides, that's fine. And then here we have pool size equal pool size. Okay, so now everything should work fine. We run that, and there we go, everything works fine. So now we've created our layer, our feature subclass layer. We'll now be able to use it in this model right here. So let's copy that and then get back to this. I'll paste this out here, and now here we have our feature subclassed. Let's take all this off. Subclassed, and then we could comfortably run this, and we get in this error. Now let's get back to check. We see batch 2. This is an error level batch 2. Now you see here we have this 2. This should be 2, and this should be 2. So that's fine. Let's run that again, and everything works well. So you see it gives us exact same output we expect to get with this feature extractor right here. Then one last thing we could do is, instead of doing this way, let's insert some code. Instead of doing this way, we are going to create a model using this model subclassing method. So here let's copy this out. So we copy that out, and then in here, instead of having layers, so here we're not having a layer, we're having a model. So instead of having layer, we now have model. And then we're gonna define a feature extractor. So our feature extractor now is gonna be the feature extractor we've just defined here. So let's go up, and there we go. So we're gonna get this feature extractor right here, and then what we do is we put it in here. So let's take all this off. We have all this off. That's now our feature extractor. So we've gotten this feature extractor. That's it. And then once we get X, we're gonna pass this through our feature extractor. There we go. Let's take all this off, and we're fine. Now we're done with the feature extraction. We could get the other paths which make up the model, like this flatten, the dense, and the batch norm. So let's take this here. There we go. We are in this model, and let's just copy it. Let's paste it out here. So here we're gonna have this. Also note that we're gonna have feature, or let's say LearnNet. This is our LearnNet model. Modify this here. We have LearnNet model. So that's fine. Now we've gotten this, everything is understood. We now check out this self.flatten equal flatten, and then next we have self.dense1 equal, let's copy this out from here simply. So we have this dense right here, which is our dense 1. There we go. We have our dense, and then we have self.batch1, which is our batch normalization. There we go. Copy this and paste. We move to dense 2 and batch 2. So here we have dense 2, we have batch 2. This is 10 actually, so we have that. And then finally we have this dense layer. So let's take this off. We have the dense layer, output 1, activation sigmoid. So that's it. We call this dense 3. So that's fine. Everything seems okay. Let's take this off now. And then there we go. We get into our call method. So yeah, we get into this call method. And this call method will basically call all these different layers. So after the feature extraction, notice how we've created this class, and this class makes use of this feature extractor, which was also created using the same model subclassing method. So there we go, we're using this here, and we're actually using it here. So that's it. Now we just make this calls. So we have x equal self.flatten, and then we pass x equal self.dense 1, passing x equals self.batch 1, passing x, and then finally we have this. So there we go, we now return x just as we did previously, and we have our model. So here we have our LearnNet model, LearnNet subclassed model, and we have this LearnNet here, LearnNet model. So let's take this off, and there we go. We've just built our model, which when we try to find a summary, so we try to do LearnNet subclass.summary. What do we obtain? You see, this model has not yet been built. Build the model first by calling build, or by calling the model on a batch of data. So we're gonna call this model on a batch of data. Right here we're gonna have LearnNet subclass, and then we have tf.zeros, and 1, 2 to 4, 2 to 4, and 3. So let's run this and see what we get. That's fine. So here we have our summary, and then we are ready to compile this model. Here we have LearnNet subclassed. So we compile LearnNet subclassed, and then we're gonna fit LearnNet subclassed. So we feed that, and everything should work fine. Let's take this to just 5 epochs. We can see that we're getting similar results when we compare this with what we have with the functional API and the sequential API. So we now move on to creating custom layers. If you could recall from the previous sections, the way the dense layer is built is such that if we have this as our dense layer, and then we have this input right here, let's call this I, or let's say it's X, we have this input X, then we have a certain M times X plus C. So this M is actually the weights, so the weights times X plus the bias B, let's call this B, and then this is now equal our output. So here we have an output of y equals mx plus c. So this simply means if we want to recreate the dense layer, then we have to take this into consideration, or the definition of the layer from scratch into consideration. That said, we could define a neural learn dense. So it's like our custom dense, neural learn dense. It's gonna inherit from layer, and then right here there's a class. So we have this class inherits from layer. Then from here we have our init method, init, and then we have the super. We pass in neural learn dense. There we go. We have that init. So that's it. Now from here, if you had noticed, whenever we're creating a dense layer, like let's come up here, whenever we're creating a dense layer, we generally had to specify at least, because this is by default, this is not by default, but so here we need to pass in this here to specify the number of output units. Now that said, we have to take that into consideration when building our neural net dense layer. So here we have output units. There we go, we have our output units, and then in here we'll define self.output units to be equal output units. So that's it. Now from this point, we're gonna build this layer. In order to build this layer, we have to take into consideration this definition right here. But this definition put out the way it is isn't very clear. Now let's make this, or let's break this up. So you suppose that we have this input of shape batch size by, let's say, number of features. So suppose we have this input. Now what happens here is this input is going to be multiplied by this weight. So it's going to be multiplied by this weight, which happens to be a matrix. Now we take this and multiply by that matrix, and for the multiplication to be valid, we need to ensure that the number of columns we have here matches with the number of rows of this matrix. But then, what are the dimensions of this matrix? We have to note that this matrix has to be defined such that we have a shape of f. This f here must match by the number of output units. So if you want your number of output units, for example, to be 1, then here you should have 1. And that's why when defining the dense layer, we don't need to specify this, as this value is gotten automatically from the number of columns in the inputs. Since if we don't take this, we are going to have an error. So TensorFlow takes this automatically, fits in here, and then collects the input you passed in the dense. So when you specify, when you say you have this dense like this, and then we say, for example, 1 and maybe some activation, then you have that. So let's say we have some activation here. Now once this one gets here, this weights matrix is now defined such that the input you pass into this dense is going to affect the number of rows we have. But then what you pass in as argument here is going to tell us, or give us the number of columns we're going to have for this weight matrix right here. So that said, we have f by 1, and then when we multiply this, we're going to have b by 1. So we now understand how we get this output, and then we have plus b by 1. So that's it, where this one comes from the bias. Now once we add this up, we have an output of b by 1, and that's our y. That's the shape of our y. If that's understood, we'll move on to building. So here we have our build method, we have self, and for now let's keep it that way. So there we go, we have this build method, and then we're gonna define our weights. So we have self.weights, let's specify weights equal that, and then here we're gonna have the self.addWeights method. So this actually comes with this layer class right here. So we're able to call this because we are inheriting from the layer class. So here we have self.addWeight, and then we specify the shape. So guess what? We are gonna have our number of rows, so n rows, which is gonna come from the inputs, and then we're gonna have our number of columns, which is gonna come from this output units you've specified, which you pass in when calling the neural net dense layer. So here we're gonna have self dot output units, so we get a number of output units. Now how do we obtain this number of input units? We're going to look at that shortly. For now, we have the weights, and then we have that, and then let's go to bias. So we have self.biases and self. This is also a weight, add weights, and then here we specify just the number of output units since it's one dimensional. So we have output units. There we go. And so at this point we've defined our weight and our bias metrics. This actually weight, just singular. So that's it. Now let's go into call. So we have our call method, which will actually get a job done, and then we have our input. So let's call this input. Let's add an S, or let's say input data, input features. So there we go. So we have that, and then what we're gonna do here is we're gonna return simply the matrix multiplication, as we've seen already, of the weights. So we have self.weights and this input features. We call it's actually the input features times the weights. Like, let's get back to this. Here, if we take the input, we need to take this input times the weights, because if we have the weights times the input, we will have F1 times BF. We call our weights this our weight shape, and then this our input shape. Multiplying this, you see that this isn't always the same, so it's not going to be, it's going to throw an error. And so that's set. What we're going to do is we're going to just simply have input features right here. So that's it, and then we add up the bias. So here we have self dot biases, which is from this one right here. Now the way we're gonna get this number of rows is gonna be easy. Here all we need to do is to specify here that we have the input features shape. We have our input features shape, which is gonna come automatically from this, and then to get the number of rows, what we need to do here is have input features shape, and then we get that last dimension. So let's get back to this. We call here we are having B by F. That's B F, and so here we need the weights needs to be F by the output. And so to get this F, we just need to take the input and then get this last element right here and get this the number of columns we have here. So that's set. We will just have that input features specify this, take this index, and that will be good. So that's how we obtain this value automatically, the number of rows we've been looking for. So now we've gotten this, everything seems fine. Next thing to do is to specify that it's trainable. So we have to specify that these weights are trainable, because in some cases we may want that the weights shouldn't be trainable. So self.trainable equal true. Now this one self here, this is an argument, like it's one of the arguments which I've been passing to this add weight method right here. So we just have that, and then here again we have this trainable equal true. Now apart from that, we could randomly initialize our weights and biases. So here we have random normal initialization. That's fine. And then we do same here. So we have our initializer equals random normal. That's good. We now run this. Here's our neural learn dense layer, and then after running this, let's get to integrate this. Let's make it quite simple. We just use our sequential API. So let's get back to this sequential API we had built initially. Copy that, and then we are going to integrate this new dense layer, this neural learn custom dense layer. So there we go, we have that, and then instead of dense layer, here we have neural learn custom dense layer. So you see that you can be able to create your own layers with TensorFlow. So that's it. Neural learn. So neural learn dense, neural learn dense. Now you see this should throw an error because we don't take into consideration the activation. And so what we could do is we could get back right here and say if the activation is equal relu, so if our activation is equal relu, we'll return this, and then else, let's say elif activation is equal sigmoid, we return that. Oops, let's get back. We have this, so we're gonna return this. Let's copy this and then paste out right here, and then we have else. We'll do the same. So now let's get into this and see the modifications we're gonna make. There we go. So here we have our relu. In the case of relu, what we wanted to have here is tf.nn.relu of that. So we're gonna pass this in to our relu, and then if the activation is sigmoid, we should have tf.mat.sigmoid. So that's it. There we go. We have that, and then this one we just maintain. So we've modified our code such that we now integrate the activations. There we go. That seems fine. So let's run this and then take this error. So here we have this double equals Python syntax, and then we come down here. Everything seems fine. Let's check this again. Here we're supposed to specify activation. So you're supposed to have activation, and then self.activation equal activation, and then here we have self.activation, self.activation. We run that again. Looks fine. And then now what we do is we just simply run this. So we run that, and we get in this error right here. To solve this problem, what we're gonna do is we're gonna include the shape here. So we're gonna have shape equal that, and then shape equal this. Let's rerun that, and we should have no error again. Oh yeah, we can't set the attributes weights, likely because it conflicts with an existing read-only property of the object. So right here, instead of using weights, we're just going to say w. So we have the w, and then right here we should have w. Now since we don't want to repeat this over, what we just say, we have pre-output. So we have our pre-output, which is this here, and paste that out, and then here we have w. Right here we have b. That's it. And now we have if this, then we pass the pre-output, and we do the same right here. So we have just a pre-output before the activation. Now here we just have pre-output actually, so we just have pre-output. We take that off. Now running this should be fine. So let's run that and see what we get. We run this, we run that, and there we go. We have our model, the same exact model we have been building right from the start, but this time around we're using a custom dense layer, which is our neural learn dense layer. Now let's go ahead and compile this model and then train it. Yeah, we've actually maintained this here, so we have to change this name. Here's Linnet model. Let's say Linnet custom. Custom model. Yeah, okay, we copy that. We have our Linnet custom model. Let's have it here. There we go. We run it. That's fine. Right here we have Linnet custom. We run that. Here we have Linnet custom. We run that, and then let's check out. As you can see with the training, there's a slight difference in the loss values and accuracy we're getting for this first epoch, and most probably this is coming from this random normal initialization we've chosen here. As with the standard dense layer, which you could see here, this kernel initialization or the weight initialization is using this Gloro uniform, and the bias initialization is the zeros. So here we have all zeros for the biases, and then here we use the global uniform method. So here, as you could see, this isn't performing as well as what we had previously. But scrolling up, there was this error. So here was meant to be sigmoid. So let's stop this. Let's interrupt this training and then get back and run this. So we will run this and compile and then start with the training again. This time around it looks better. It looks more like what we should expect. So even though we're not using the global initialization method, this training process looks quite similar to what we would have had in the case of the global initialization method, which is used with a standard dense layer. And here is what we get after training for over 5 epochs. Thank you for getting up to this point, and see you next time. Hello everyone, and welcome to this new section in which we'll look at other methods of evaluating our model other than the binary accuracy which we've been seeing so far. So in this section, we'll look at how to compare the true positives, false positives, true negatives, false negatives, the precision, the recall, the area under the curve, how to come up with convolution metrics like this, and finally how to plot out an ROC curve like this one, which permits us select the threshold more efficiently. Don't forget to subscribe and hit that notification button so you never miss amazing content like this. Let's now look at other ways of evaluating our model other than the accuracy which we've seen so far. To better understand why working with only the accuracy isn't always a great idea, we have to take into consideration the fact that our model on a test set has 94% accuracy. Now, this means that we have 6 out of 100 predictions which are actually false. Now, what if I get to the hospital and I'm told that I don't have malaria, when in fact I actually have this disease? So that said, the model predicts uninfected and I actually have the parasite in my bloodstream. Now, this particular situation becomes very dangerous because the patient gets back home thinking he or she doesn't need any treatment, whereas that patient actually has this parasite. You see that even with a 94% accuracy, we wouldn't be able to save ourselves from such chaotic model predictions. Now, in another example, you have a situation where the actual is, let's put it out here. So in another example, we can have a situation where the actual is unparasitized. So actually, you do not have this parasite, but the model predicts that you have the parasite. Now in this case, although we have a wrong prediction, we have actually a less chaotic situation as compared to this previous case here, since at least actually you are uninfected. If we consider negative, that's this negative to be uninfected, and positive to be to contain the parasite, that's P. So here we consider we have positive and then we have negative. So here we have negative uninfected and positive parasitized. Now if we let this, you will find that this first situation where actually we have the parasite and the model predicts unparasitized is known as a false negative. So here we have this false negative. And this is because the model predicts negative when it isn't actually negative. So since we have this wrong prediction for negative, we call it a false negative. And in this case where we have the model predicting parasitized, that is positive, when it's actually negative, we call this a false positive. So here we have FP and here we have FN. Now there are 2 other scenarios, that is with TN and TP. For the Tn, we have the true negatives, and the Tp, the true positives. For the Tn, we have the model predicting negative when actually we are negative. That is, we have the model saying this is uninfected when actually it's uninfected. So that's a true negative. And then for the true positive, the model predicts a positive that's parasitized when actually it's parasitized. So that's a true positive. Now, hopefully you've understood the concepts of true negatives, true positives, false negatives, and false positives. We could then summarize all this information in this matrix known as the confusion matrix. In this confusion matrix, we have the true negatives, the number of true negatives here, the number of true positives, the number of false negatives, and the number of false positives. This means that if we have a test set of, say, 2,750 different data points, and then we run this or we evaluate this with our model, we'll be able to get this number of true negatives, get this number of false negatives, number of true positives, number of false positives, and hence better evaluate this model. So if we take this example where we've evaluated our model on the test set, and then this model A produces this confusion matrix, and this model B produces other confusion matrix, where here we see we have for the true negatives and true positives, we have 1,000, that's 2,000 correctly predicted data points, and then here we have 1,000, 2,000 correctly predicted data points. And then for this model A, we have 700 false positives and 50 false negatives, whereas for model B, we have 50 false positives and 700 false negatives. Recall, we had defined negative to be uninfected and positive to be parasitized. And hence, if we had to choose a model between A and B, we'll try to choose that model which minimizes the number of false negatives. So, we are not saying that we shouldn't minimize the number of false positives, because we have to try to minimize all the false predictions. But then, since with the false negatives, we are telling a sick person that he or she isn't sick, this at least is worse than telling a healthy person that he or she is sick. And so we'll try to prioritize the number of false negatives, and based on this prioritization, we are going to prefer model A since we have the smaller number of false negatives. And so here we'll choose model A over model B. Now, as a quick note, you may decide to say no, negative is for parasitized and positive is for uninfected. It isn't a must that this must be tied together like this, but for clarity purposes, it's better to look at it this way, since saying you are tested negative means you're uninfected and tested positive means you're parasitized. Now, you should also note that depending on the kind of problem you want to solve, in some cases you will want to prioritize minimizing the number of false positive over the number of false negatives. So this actually depends on the problem you're trying to solve. But in this case, we are prioritizing the number of false negatives. Now, based on what we've seen so far, we're going to introduce several new performance metrics, and all this take up these different formulas we could see right here. We have the precision, which is the number of true positives divided by the number of true positives plus the number of false positives. Recall, true positives divided by the number of true positives plus the number of false negatives. The accuracy, the number of true negatives plus the number of true positives divided by the number of true negatives plus true positives plus false negatives plus false positives. So we'll stop in this first three for now. Now, what do you notice? You'll notice that in this precision and recall, we have this true positive, and here true positive, true positive. What differentiates them is the fact that in the precision, we have false positive in the denominator, and in the recall, we have false negative in the denominator. This means that if the number of false negatives is high, that is, we have let's say we have a constant k divided by a high value. So constant divided by a high value, so constant divided by high, here we're gonna have a low output. And so if we want to have a low recall, then we need to have a high number of false negatives. And if we want to have a low precision, then we need to have a high number of false positives. Now in our case, we're trying to minimize the number of false negatives. And since we're trying to minimize the number of false negatives, it means that we're trying to maximize the recall. Since minimizing this denominator will entail maximizing this overall TP on TP plus Fn. And so here we're trying to prioritize the recall over the precision. Now, if you look at the accuracy, you'll notice that we have Tn plus Tp and Tn plus Tp right here. Tn plus Tp, Tn plus Tp, and we have Fn plus Fp. If you are keen enough, you should see that this accuracy doesn't give any priority for whether the false negatives or the false positives. It treats these two as the same. But as we've seen previously, in the real world, in solving real world problems, many times we would have to prioritize. Hence, the accuracy may not always be the best metrics for our problem. In our case, we find that using the recall is even better than using the accuracy. As with the recall, we get to reduce, or with the recall we get to see whether our model does well at minimizing the number of false negatives. Now we also have this F1 score, 2 times the precision times recall, this precision this recall, divided by the precision plus recall, the specificity, the number of true negatives divided by number of true negatives plus number of false positives. And then we also have this ROC plot right here. ROC stands for receiver operating characteristics. Here we have the true positive rate and the false positive rate. The true positive rate is the number of true positive divided by number of true positive plus number of false negatives, which happens to be the recall. And then the false positive rate is the number of false positives divided by number of false positives plus the number of true negatives, which if you look carefully, you'll find that is equal 1 minus the specificity, which has been defined right here. Before we get into understand this ROC plot, which we've put out here, let's recall these two models which we had described previously. That's model A and model B, where model A had a smaller number of false negatives as compared to model B. Now, if we pick out just this model A and then we are interested in reducing this, or let's say we pick out model B. Suppose we pick out model B and we're interested in reducing this number of false negatives right here. Then one solution could be that of modifying the threshold. So if we have a threshold of 0.5, meaning that above, like we have this 0.5, below 0.5 we consider negative, above 0.5 we consider positive, that is parasitized, and then below uninfected. Then what I could do here is reduce this threshold. So if I take this threshold to say a value of 0.2, let's take this here. So I've reduced this threshold now to 0.2. You'll see that for most of the predictions, our model is going to say that this is a parasitized output, since now this threshold has been reduced. This means that if we have a model prediction of 0.3, which initially would have been uninfected, now this model sees this as parasitized. And so this makes it now more difficult for our model to have false negatives, since our model now has this tendency of predicting that given an input image is parasitized. That said, we now need to look for a way that we could automate this process. That is, we want to be able to choose this threshold correctly or rightly, because if, let's say, we take a threshold of say 0.001, it means that anytime our model predicts less than 0.01, it's uninfected, and then greater than 0.01 is parasitized. Then this will be very dangerous for the overall model performance, as now most times we would have the model predicting that the input is parasitized. And so our aim here is to pick this threshold such that this number of true positives and true negatives we've had right here don't get reduced. Now, the way we could look at this is now by using this ROC plot. With this ROC plot, what you actually have here is the different true positive rates and false positive rates you would have at a given threshold. So this means that a point picked here is just a given threshold. Now let's suppose that the threshold 0.5 is about here. So let's pick this. Let's suppose that this is 0.5. We could pick another threshold. Let's say this one is, say, 0.2, and so on and so forth. Let's say this one is 0.1. Now we could have another model with this different ROC plot, another one with this kind of ROC plot. But note that overall, our aim is to ensure that this false positive rates is minimized and the true positive rate is maximized. So if we have an ROC plot which is like this, so let's redraw this. If we have this kind of ROC plot, that is one that goes up straight like this and then comes this way, we have this right here. So if we have this kind of ROC plot, then we will be able to pick out this threshold right here, 0. Say x. We'll be able to pick this threshold because at this threshold, for this threshold at this point, the true positive rate is at its highest value, that is of 1, and then the false positive rate is at its lowest possible value, that is of 0. So here we have 1 and then 0. So here we go, we have this, and then we pick out this threshold. Now this value of x could be 5, could be 4, or whatever. So we have 0. Whatever value will lead us to this. Nonetheless, many times we wouldn't have this kind of plots, so we will do it plots which will look like this, this, and so on and so forth. Now, once given a plot like this one, let's suppose we have a plot like this one. The aim here is to ask yourself the right question. If I want to make sure that my recall is always maximized, which is our case, we will try to ensure that we pick out these points around this. So we'll try to pick out these points towards the top right here. Let's take some of this off. So as we're saying, if we want to maximize our recall, it's about normal that we'll pick out threshold values which will take us around this region, because it's around this region that our recall is maximized. Let's do this so you could see that clearer. Okay, now the problem with picking a point around this is that when you pick a point around this, the false positive rates is increased. So you need to find that balance between this false positive rate and true positive rate. So it will be much logical to pick a point around this right here. So we could pick around this region instead of this previous region right here. Now you could see that in this region, or let's say we pick this point. If you pick this point, your false positive rate now is smaller, while your true positive rate is, or your recall is maximized, though it isn't the best possible recall we could have. But trying to focus on getting that recall of 1 will lead you into trouble, since getting a recall of 1 in this case will increase our false positive rate. And then if we're dealing with a problem where we're trying to maximize the precision, then in that case we want to ensure that this false positive rate is minimized. And so in this kind of problems, we'll want to pick a point around this. So you see, we want to pick this kind of value since at least our false positive rate is minimized. But then if you want to go and pick a point around this here, you would have a false positive rate of 0, but doing this will get you this into trouble, because here you're gonna have a true positive rate which is very small, and so you need to get that balance. Now if you're having a problem where it doesn't really matter, that is, you aren't trying to prioritize the precision or the recall, and working with the accuracy is just fine, then you could pick out this point right here. So this is when you are having, or you don't have to prioritize on any. Here is when you're trying to prioritize on the recall, and here is when you're trying to prioritize on the precision. But at least one great thing is, with this tool that is the ROC plot, we are able to pick out this point and then automatically get that threshold we need to work with. And so when doing predictions, we will not, or we may not use 0.5, but we're going to use a certain threshold which will suit these objectives we've set initially. Now we'll now move to the area under the curve. For the area under the curve, we generally use this when we're comparing two models. Here we have this model, let's call it model A. It's not actually this model A, it's a different model A. Let's call this model alpha. And then we have this other model which we shall call model beta. So we have model alpha and model beta. It's clear that model beta is better because it gives us better options. Now you'll see that if I find myself here, I get a better true positive rate, false positive rate balance as compared to when I find myself at this position. And so if we are comparing these two models, we could make use of the area under the curve by calculating this area covered here. So let's bound this, and then for alpha we have this area under the curve, popularly known as AUC, A small u and then C, which will give us this. And then for beta, we're gonna have this area under the curve now, which covers this area plus this extra area right here. And so in general, if we have two models and then we want to compare them, then we could use this area under the curve, since it shows us how much freedom we have in playing around with these thresholds. We now get back to the code and see how we're going to implement this new matrix we've just talked about. So right here we have matrix, and then we have the false positives, we have the false negatives, we have the true positives, we have the true negatives, we have the precision, we have the recall, we have the AUC, and then since we're dealing with a binary classification problem, here we have binary accuracy. We run that, that's fine. And then right here, instead of having this matrix, we'll define this matrix list, which will contain these different metrics which we've just talked of. So we have the true positive, false positive, right up to the AUC. Let's run this, compile, and then feed our model. You'll see that as we train, we have the true positives, false positives, true negatives, false negatives, accuracy, precision, recall, and AUC scores, which have been given to us. As you could see, here are the results we obtained. We're gonna go ahead to evaluate our model. So let's get to the model evaluation. We run this, test data, and then we have our model evaluated. There we go, our model has been evaluated. As you could see, we have this loss 0.35, number of true positives 1323, number of false positives, number of true negatives, false negatives, accuracy, precision, recall, and AUC. So that's what we have for this model. For now, we have been showing you this binary accuracy, false positives up to the AUC. What if we plot out the confusion matrix and also the ROC plot? So we'll import scikit-learn and seaborn. Right here we have scikit-learn, and from scikit-learn.metrics we're gonna import confusion metrics, and then for seaborn we need to import seaborn and SNS. So that's it. So here we are importing scikit-learn and seaborn, which we'll both use in plotting out this confusion matrix. So let's run this, and then we'll visualize our confusion matrix. So we'll have to get the label that's the true values of the outputs, and then we'll also get the predicted values. So here we want to get the labels and the predicted values. Now let's start with the labels. So here we're gonna have labels. We have this list. There we go. And then for XY, or let's say for XY in the test data set, we're gonna take this as numpy iterator. So for XY in this, we have the X and the Y, we have that, and then we append every output to these labels. So here we have labels.append Y, and we run that. So that's fine. We could now print out labels. What do we get? There we go. You see we have these labels. Now let's convert it into a simpler form where we just have only these values in here and not this arrays which we have here. So in order to get that, we'll have labels will be equal labels, or rather will be equal an array, and in here we're gonna create this list. So in this list here, for every element of this labels list, so for here for I in labels, we're gonna do I the 0th index. So we're gonna take always this element right here. So that's set. We have that, and now we have labels. Let's print out the labels after doing this transformation. There we go. Here's our labels now. So we have that. Fine. Could take that off. We have this error actually because we tried we've converted these labels already, and then we're trying to reconvert them. So let's comment this right here. We comment that and run this, and we have our labels. Okay, now we have these labels. We could move ahead and get the predicted values. So to get these predicted values, we have our LeNet model, LeNet model, there we go, dot predict. What we're gonna pass in this predict method is our input. So we have the input, and then right here we add this input list, and then we do same as we did with the labels. So we have input.append x, which is this input here. Now we run this, and then let's add a cell. So we add this code cell, and then we're gonna pre-process our input. So from this, we're just gonna print out the input to see what it gives us, or what kind of shape we are having right here. Let's put numpy array while that's loading shape. Then we run this other cell right here. Here's what we get as shape. So we have to take this off, this one off here, and to do that, you see we would have the input will select this first index, so we take that, and then for this next we take only one, so we're gonna chop this off, and then we have the rest. So that's it. Now we run this again, and we should have put a shape here. So we run that again, and there we go. So this is what we expect. Now we've gotten the labels, and then we are now ready to get the predictions. So here we have this input. We take this, and then we pass it in here. We pass our input and we get our predictions. Let's print out the predicted here. Yeah, let's print out the predicted and see what we get. See what we get right here. We could print out a shape to better understand what this is. And as you could see, we have this. So how do we take this off, or how do we make it look like the labels? We could simply take this off. So we select the first, and then for this one we take it off. So we run that again, and there we go. So now we could do this, take off the shape, and then it should look like the labels we've had here. And that's it. So now we've gotten this. Our next step is to use the convolution metrics from scikit-learn metrics and produce our convolution metrics. Now let's comment this sections first. So here we've passed in the labels, we've passed in the predicted, and then we're specifying this threshold. So what we're saying here is all values greater than the threshold considered uninfected, and all values less than or equal to the threshold is going to be considered as containing the parasite. And then we're going to have this in this convolution metrics here. So we run that, and then as you could see, we have our convolution metrics, which shows us the number of true positives, true negatives, false positives, and false negatives. Getting back to our model evaluation, we'll see exactly which of those values are the true positives, false positives, true negatives, or false negatives. So let's just copy this out here. We take this up, and we shall see that below. So here we have this convolution metrics, which we've just seen. Here is it right here, convolution metrics right here, and then let's paste this out here. So we have the number of true positives, this one matches, and then number of true negatives 1298. Yeah, this is closer. So what scikit-learn gives us is quite similar to what we had with TensorFlow, but they're not exactly the same. So this tells us that this is the number of true negatives, this is the number of true negatives right here. So here we have true negatives, here we have true positives, then here we have false positives, and then here we have false negatives. We'll then see how modifying this threshold will either reduce the false negatives or reduce the false positives. So let's have, say, 0.25 right here. We run that again, and there we go. Let's print this. So we see that we now have a number of false negatives reduced when we reduce this threshold. We now go back and then take this to 0.75. We run that again. You see that this is now reduced. So here we have a an increased number of false negatives and a reduced number of false positives when this threshold is increased to 0.75. So that's it. Let's now print out, or rather let's now plot out this more elegantly looking figure with the CBun library. So here we go, we run that, and that's it. So here we have our same convolution metrics but more elegantly plotted. Let's take back to 0.5 here and have that. Okay, so that's it. Now you notice that when we're trying to say reduce the number of false negatives or the number of false positives, what we're doing is we're just picking up some values here. Like we could pick up 0.2, and then we see its effect, and we could do the same for 0.25. You see how this takes us to 58 and this to 130. We could continue doing this until we get our best results, but then this isn't very efficient since we're just trying out different values. Now the way we could do this more efficiently is by working with the ROC plots, where we'll be able to choose a threshold in a more efficient manner using the plots, and so we'll be able to reduce the number of false negatives or the number of false positives without having to try out all these threshold values manually. The very first thing we'll start with will be to import ROC curve. So we have ROC curve, and this is part of scikit-learn metrics. So we'll run this again, and then just right here we'll make use of our method. It's going to output the number of, or it's going to output a number of false positives, true positives, and then thresholds, which we'll use in coming up with the ROC plot. So we have that. We have ROC curve, and then this takes in the labels, and then the predicted. So we have this predicted value. Now if you print this length out, the length of FB, length of TP and length of thresholds, so we have exactly the same number thresholds here. We should have exactly the same number. Here we have 330. Okay, so now we have this. Now note that the reason why we need this is because when coming up with our ROC plot, like say we have this ROC plot, we want to have for each and every point the corresponding TP, FP, and then the threshold, which will lead to that TP, FP pair. So that said, we are going to make use of this data now and then plot out the ROC curve. So let's get straight into that. We have our plot, and then we do plotting. We pass in the false positives, true positives, just like x, y. So here we have x, and then here is y. Let's get back, that's fine. And then from here we have the labels. So we have x label, which is our false positive, and then the y label, our true positive rate. So we've seen this already. Now we have this. We could include the grid. So we have this grid, and then we show. So that's it. We run that, and here is what we get. So this is our ROC plot right here, based on this FP and TP we got from here. Now, how do we include these thresholds? In order to include these thresholds, we are going to make use of matplotlib's test method. So we have plot the text, and then here we're going to have the TP, or rather the FP, TP, and then what the actual text will be put in here will be the thresholds. So we'll be passing in the thresholds. But now note that we actually have to do this for each and every point, which is impossible since there will be too many text put out here and it's going to be choked up. So what we could do is we could skip some values. So we'll say for I in range, we're going to start from 0 right up to the length. That's actually going to be 330 length of thresholds, and then we are going to be skipping some values. So skip, and then we'll define the skip. So let's start with a skip of 20. So initially we're going to skip 20 values, and then once we skip this value, let's pass this in here. Once we skip this value, we pick in a given I, picking that given I, same here, and then we do the same with the thresholds. So we get the corresponding false positive rate, corresponding true positive rate, and then the corresponding threshold. Now that's done, we could run this. So here's what we get. We see this plot. Now we could see the ROC plot with the different thresholds. I think we could let it like this. It's fine. Let's increase the size, and then we try to focus just on this portion, which actually matters the most, because we wouldn't want to get into these regions, because in these regions our false positive rate is going to be too high, and these regions below this would have a very small true positive rate. So generally we'll try to focus on this zone right here. Now, depending on the problem you are trying to solve, if your false positive rate is what matters the most, that is, if you cannot afford to have a high false positive rate, then you tend to pick values. Let's say let's break it out like this. So here is like the midpoint. We have some sort of mid here. Let's draw this line. Okay, so we have some sort of midpoint here. So this like 0.5, 0.46, 0.62, and all of that. So we're breaking it up like this. And then if you want to ensure that you try to minimize as much as possible your false positive rate without reducing your true positive rates too much, then you tend to take values around this. But if you want to make sure a true positive rate remains quite high, even at the detriment of the false positive rate, then you tend to pick out values in this zone. So you have these two zones to pick your threshold from. This is the main zone, and then you have this zone right here, this other zone, and this other zone. So you have zone 1 and zone 2 from which you have to pick from. One other quick note is that if you have a problem like the one we're trying to solve, where parasite is 0 and then uninfected is 1, so this is how the data set was created, and this based on this we build our model. Then this means that this will be considered as negative samples, while this will be considered as positive samples. Whereas in the real world, we'll tend to look at uninfected as negative and parasitic as positive. So you have to be very careful with these terms and know exactly how your data and models have been built. And that's why in our case, where we're trying to avoid situations where our model predicts a fake uninfected output, that is a patient who actually has a parasite, but the model predicts that's uninfected. This is actually a fake uninfected. This is a fake or false positive in our case. So we'll tend to minimize this number of false positives. Now, if your model was built such that parasitic is 1 and then uninfected is 0s, then it's clear that you will try to instead minimize the number of false negatives, since uninfected is considered as negative. That said, coming back to our problem, since our data set was constructed in this way, we're trying to minimize the number of false positives at all costs. But while doing this, we have to ensure that the true positive rate remains at a reasonable position. And so we could pick out a threshold of like 0.6265 given right here. Getting back to this, let's take 0.6265. We run that. We have here a number of false positives to be 87, which is going to be smaller than when we're having a threshold of say 0.5. Run that again. You see 87 is going to be smaller than this 99, the value of 99 we get in now. And so that's it for this section on metrics. Thank you for following up to this point, and see you next time. What's up everyone, and welcome to this new section in which we'll build callbacks with TensorFlow. In this section, we'll look at how to build a callback from scratch by inheriting from the callback class. And then we'll build other callbacks made available by TensorFlow, like the CSV logger, early stopping, learning rate scheduler, model checkpointing, and finally reduce learning rate on plateau callback. Don't forget to subscribe and hit that notification button so you never miss amazing content like this. Callbacks are methods we call during training, evaluating, or prediction. These callbacks can permit us extract useful information from those processes we just listed, or even carry out changes on those processes. Here in this TensorFlow documentation, we have TF carriers and then we have the callbacks. So this is what we have for the documentation. We could go through each and every one of this, but for the sake of this course, we are going to look at the key ones. So right here we have this callback, but before getting to this, we are going to look at the history. The reason why we're looking at the history first is actually because we've used it already. So we use this callback without really knowing that we're using callbacks. So here we're told this is a callback that records event into a history object. So remember the times we were having this here. So after training, that's when we're training, we start some information in this history, and then after training we're able to come up with plots like this because we had this information stored in this history right here. So that said, as you could see in this example, which is kind of like similar to what we've been seeing so far, we have this history and it collects all values we've been storing during training, and then we could print out this params, history.params, we get the params, and then we could also get the keys. So that's how this works. We've seen this already, and then we could look at this callback class right here. Now the reason why this is like the most important of all this different callback classes is because this is kind of like the mother class, or that abstract based class which can be used in building new callbacks. So if you want to build a callback which isn't listed here, you could always get back to this and then build that callback from scratch. So here we have this callback class, which has attributes, as you could see, params and model, and then it also has this methods, which we'll see how to implement very easily. If you look at this onBatch begin and this onBatch end, you'll see that they take similar arguments. Like here we have the batch, and then we have this logs. Then for the next, the epoch begin and the epoch end, they actually take in the epoch and the logs. That said, we'll import the callback. So here we have from TensorFlow Callbacks, we're gonna import callback, this class which we're gonna be using in creating our callbacks. We run that. Then we define this callback class, which we'll note as called loss callback. We have this loss callback class, which inherits from the callback, which we've just imported. And then we will make use of the different methods which have been given to us in the documentation. Let's start with the on epoch end. So on epoch end, we're taking the epoch, and then what we're gonna do is we are gonna print out the loss values at the end of an epoch. So what we'll be doing is kind of similar to what we have already here. So let's do that and have print epoch number, let's say epoch number this, and then has a loss of for epoch number this. Our method, the model, has a loss of this, and then we just format. So there we go, we pass in the epoch. Let's have this here and the logs. So just as in the documentation where we had in the epoch and the logs. Now we are gonna pass in the epoch and then the logs, but since we want to get just the loss, we could get the loss from this. So we have this dictionary here and we pick out just the loss. Now let's run this, and then we'll see how to include a callback in the training process. So just right here, we're gonna have callbacks. So the callbacks argument, and we have this list. So in this list, we're gonna insert this callback we've just created here. So we have the loss callback, which we just pass in here, and that's fine. So now let's rerun this. Let's take this for say 3 epochs and then see what we get. We get in this error. We click search Stack Overflow and then click on this. You'd see that we have a solution just here, and what is said here is what you're gonna pass is the object and not the class itself. So that said, instead of passing the loss callback as we just did, we're gonna pass in this object. So we're gonna put in the brackets. Let's modify this print here and pass in a space. So we're gonna have that. So next line, and then we rerun that again. So let's run that, and that's fine. Then after training for over 3 epochs, here's what we get. We see that unlike before where we just had this outputted, now we have this message outputted. That is for epoch number 0, the model has a loss of this, for epoch number 1, and then for epoch number 2. Now what we could do is we could add this, so we have this formatted normally, so we don't start from 0 but instead from 1. So we could say +1 right here. So that's it. Now another thing we could do is we could have on batch end. So on batch end, we have that, and then we have the batch. We pass in the logs. This time around, what we want to do is kind of similar to what we've seen already here. So we just print this out. That's fine. Take that off. So for the batch number, for this batch number, the model has a loss of this. So there we take in the batch. So that's it. And then we log out the loss. Now, yeah, let's just pick out this logs totally. So we have the logs, and then that's fine. So here we've put in the batch, unlike here we're passing the epochs. We run this again and run this, You'll notice that this time around we have much more information which has been logged out. Let's take this here and get right to the top. What we have here is for batch number 1, the model has this loss. So you see that this is after each and every batch. So here, the first batch, we have this log, and then the next batch, we have this log, and so on and so forth. And since our batch size equals 32, this simply means after working on 32 different data points, we're gonna have this logged out, and then the next 32 we have this logged out right up to the end. Now for the epochs, you'll notice that as we go on, so we're moving on to, let's get right up to 689. We have that, and finally here we have 689. Okay, so for this last year, that's at the end of the epoch, we now have this logged out. So here we have 4 epoch, whereas previously we had 4 batch for all the different batches. In case you want to understand how we got this 689 right here, you could take the total data set size and then divide by the current batch size, which is 32. You should get this 689, which is given right here. So from this, we could look at the CSV logger. Now with the CSV logger, what we're actually doing is we're logging out this information in a CSV file or in some file which we're going to define. So what we'll do is just simply copy this. Now this time around, we wouldn't actually have to recreate a class as we just did with the callbacks, because there's kind of like a general way of creating this callbacks. Now with the CSV logger, we'll actually create the callback more easily. So here we have this, and then we're going to specify the file name. So here let's have the CSV callback equal that. Let's take this off, and we'll specify our file name. So yeah, we just have our file logs.csv, and that should be fine. So we take that off, and then up right here we have to import CSV logger. That's fine. We run that, everything is okay. We get back to our callback, and then we run this cell right here. Now note that this append is, as described in the documentation, a boolean which tells us whether the logs we are currently putting in the CSV file or in the file in general are going to be appended on previously logged content or not. So when we have this as false, we're supposing that this is empty, and so we are going to like be putting information in this file for the very first time. So we've run this, and then now all we need to do to take this new callback into consideration is to have here CSV callback. So let's make sure, let's take this batch logs out from here. So we are not going to take this loss callback into consideration any longer. We run this. After 3 epochs, we're going to open this up, and then we have this logs.csv file which has been created. So let's have that, and as you could see, we have this CSV file which we could now download and then view it later. So here we have the accuracy, AUC, and all the other metrics and loss values which we want to store. So that's fine. Next thing we could do is we could get back again here, and then I'll select append true. So if we've done training the first time and want to redo the training process, we don't want to erase all the values we had previously. So here we set this to append true. Run this again. After 3 epochs, we open this log.csv file, and what do you have here? You see we have this new information which has just been appended on the previous information. From this CSV logger, we could now move on to this early stopping callback right here. To better understand early stopping, let's get back to this plots which we had previously. So let's take out this plot of the model's accuracy, where we see how the train accuracy keeps increasing, while after a certain point, let's say this point here, let's take this off. After say this point, our models, or even this point here, our models validation accuracy doesn't increase any further. So what we have in here is something like this. We have this training accuracy, which increases and goes towards 1, and then the validation accuracy, which is something like this. Now in some other cases you would even have situations where this starts to drop. Nonetheless, in this case we have this plot where it just kind of like stabilizes and doesn't increase any further. Now note that this kind of situation is known as overfitting. In overfitting, the model starts to overfit the training data. So because the model has been trained on the training data and not on the validation data, at a certain point the model stops or ceases to generalize, because the aim of this training process is not to come up with a model which only performs well on the training data. We're trying to come up with a model which performs well on any type of data, be it the train, be it the validation, or the test data. So if we're able to have a model which does the same, or which has the same performance with the train and with the validation, with the test, then that model is an ideal one. But in this case, we see that as we keep on training, the model's parameters have been modified to suit only the training data. And this is very dangerous, because at a certain point, you may feel like because you're having high train accuracy, your model is performing well. Whereas this isn't the case, because when your model will be shown new data, like the validation in this case and the test later on, this model wouldn't perform as well as it will do, or as well as it's doing with the training data. So to avoid this kind of false measurements, we tend to stop the training once this overfitting starts to occur. So this means that if you training and then your validation, let's suppose we're stopping at this here. So we're training and then your validation data or your validation accuracy seems to be constant, whereas that of the training seems to continue to increase, then it's better for you to stop training at this point, because after this point the model parameters are just been modified to suit the training data and doesn't really generalize, which is the case here, because we're trying to extract some information from this data and make the model intelligent. So the model doesn't become intelligent by only modifying its weights or parameters based on the data it's been trained upon. It's intelligent because after being trained, it can perform well on data it has never ever seen. So here we have this L is stopping, where after we notice that the validation accuracy doesn't seem to increase any further, we just kind of like stop the training and then use the model parameters from this number of epochs. So we could say that after say 12 epochs, we just stop the training. Now let's take this off and then replicate something similar for the loss. So if we're having a loss, we could have something like this and then that. So here we have the number of epochs and then we have the loss. So you could have a situation where you're having your training data, which your training loss, which keeps reducing, whereas for the validation, you see, you would have something like this. So this is a typical plot for overfitting. Nonetheless, in our case, the model overfits, but not that much. In some cases, you will have a situation where this even starts to drop and where the loss starts to increase after a certain point. Here is a validation loss, and then here is a training loss. Obviously, the training loss will always keep reducing because we are training on this training data. So what we're saying is, at this point where the validation stops reducing, it's important to just stop this training, and this is known as early stopping. Now recall that the aim of callbacks is to be able to modify the training process, the evaluation process or the test process, that's a prediction process, in an automatic manner. So that said, we shall make use of this early stopping callback right here, which will permit us stop training automatically once we notice that a given parameter, like say the loss, the validation loss, doesn't drop any longer. So here we're just gonna copy this and then we just apply it similarly to what we had done with the CSV callback. So here we add this text and then we add that code. We just paste this out. Now we define this ES callback, that's early stopping callback, and then we look at the significance of each and every one of these arguments. Now coming back to the documentation, we have this monitor quantity to be monitored. So by default here we have this val loss. This means that this callback will simply check on this validation loss right here, and then once it stops reducing, like say at this point, we're gonna stop the training. Whereas if we change this to say validation precision or validation accuracy, then what we'll be monitoring will be that accuracy or the precision value. So if you have them like this, we'll see we'll stop around this right here to ensure that we don't go and overfit on the training data. The next argument is this mean delta argument right here. So with the mean delta argument, we are defining a minimum change below which any change is considered as no improvement. So if we're having a loss like this and that our mean delta is say a value of 0.1, then even if this loss reduces by a value of 0.5, then this callback will consider that there has been no decrease in the loss because the mean delta is 0.1. Now by default, the mean delta is set to 0. This means that any slight change is considered as a drop. So if we have even 0.0005, then we consider this as a drop in the loss. Now this is important because this has a patience. This callbacks make use of this patience. With this patience, we are defining the number of epochs above which, if we don't have a decrease in the validation loss, like in this case of the validation loss, we consider that we could stop that training process. And for the accuracy, is the number of epochs above which, if we don't have an increase in the validation accuracy, if we've picked validation accuracy for the monitor, then we'll have to stop the training. So we define this, or we predefine this so that this could run automatically. Now for the mode, by default we have the auto mode, but we could specify mean or max. Notice that when speaking about the loss, we spoke of a value or the number of epochs above which, if the loss doesn't decrease. So here we're supposing that the loss is meant to be decreasing, and in that case we are having a mode of mean. Now for the accuracy, we spoke of for the patience, number of epochs above which, if the accuracy doesn't increase. So in this case we're having the max. Now what TensorFlow permits us to do is to use an auto, and with this auto, TensorFlow automatically infers whether it's dealing with a mean or max. So this means that if you place in, for example, val precision, this auto should be able to understand that a precision should be increasing, and so it's going to use a max. Then we move to the baseline, where the training stops if the model doesn't show improvement over the baseline. Then finally we have this restore best weights. With the restore best weights, which by default is false, we are simply saying that the model is going to take up its final state. So this means that if we start monitoring the model, say at this point here, or at this point where we have the lowest possible val loss, and then the model, let's say we have a patience of 5, so we are going to train for further 5 epochs before stopping. So if after 5 epochs we are on this, let's suppose that the 5th epoch we are on this, so we've added from here plus 5 epochs we are on this, and then we are having this loss. It's clear that this model with this loss is less performant than this one. Now if this restore best weights is set to false, then we'll just take the model's weights here, or the model weights which give this loss value here. Whereas if it's set to true, then it means we're gonna take the best weights we've had throughout the training process, and which happens to be the weights which provide this loss right here. That said, here we go, we have this, we have, let's say, the patience to 3, verbosity 1, mode auto, baseline known, restore best weights false. So let's run that, and then all we need to do is to just include this here. So here we're gonna have ES callback. Now we could take off the CSV callback, but you could always put all this together. Let's just let it, so we could see how all that works. So we just have this list right here, and we have this ES callback with the CSV callback. Now we run the training. We didn't train this for long enough to be able to observe any callback changes. So let's take this to 10 epochs, and then we reduce this to 1 or 2. Let's take this to 2. We run that again, so that's fine, and then we fit our model. After training for 8 epochs, we see clearly here how the early stopping callback stops the training process. Now let's understand why this is, or this training process has been stopped. If you take a look at this validation loss right here, you would find that there was a drop here, increase, but after this increase there was a drop, and since the patience is equal to, that's the patience we had defined here, equal to, we have to get 2 successive increases, or 2 successive same loss values before the training process could be stopped. So since after this we have a drop, the training process continues, then we have this increase, and then we have this drop, so it continues, then here we have this increase, and then here again we have this other increase. So because now we have had this 2 successive increases, as we could see in the plot right here, you see right here where we have this increase, drop, increase, and then increase, we now have the training process which is being stopped, as we could see here. That said, we now move on to the learning rate scheduling. Up to this point, we've been used to training our models with one fixed learning rate throughout the process. So we could fix our learning rate as we did to say 0.01, and we use this same learning rate throughout our whole training process. But it happens that if this learning rate is too large, then we risk diverging. And if the learning rate is too small, it would take too long for our model to converge. So let's consider this plot right here. It's actually a very simplified plot, as actually what really happens is way more complex than this. So let's consider this plot, and we have this, and here we have the loss. Recall our aim and the weights. So here we have loss and then weights or parameters, and our aim is actually to modify this weights such that the loss is minimized. So our aim is to get to this position right here. Now we start with a case where we have a high learning rate. So if we are dealing with a high learning rate, then it will be easier for our model to find its way to this minimum position right here, or to some position close to this minimum position, let's say at this point here. But the problem here is, once it gets to this position, it could also very easily diverge from it. So you could very easily get back to another point around here, and then repeat this kind of process again, where the model just kind of diverges. So you could have something like this. It could come down here and then get back to some point around this, and so on and so forth. So we may have this case where the model doesn't really converge because the learning rate is too high. And then for the small learning rates, we may start training, and then if, say, the model, or if we find ourselves at this point here, that is, we've modified the weights such that the loss value happens to be at this point here, it becomes difficult for us to get to this ultimate or global minima, since the learning rate is too small and the changes we're making are very small changes. So we may find ourselves just staying around this local minima here instead of going towards this global minima, which is this. And so to bring in a balance, what we could do is, when we start the training process, we could use a relatively high learning rate such that the model kind of approaches this global minima faster, and then after a certain number of epochs, we start or we modify the learning rate such that it becomes, or it takes in very small values. And since it now takes in small values, we now start taking up very small changes such that we can get towards this global minima now without risking divergence. Now, one way of doing this is by, say, you could fix, let's say you could suppose that for the first 10 epochs you train your model at a learning rate of, say, 0.1, and then from 10 to 20 you're going to train a model at a learning rate of, say, 0.01. Let's say we're dividing by a factor of 10, so we now move to 0.01, and the next 10 again, let's say we're training all this for 30 epochs, and then the next we go to 0.001. So you could train your model, and then after 10 epochs you restart the training by modifying the learning rate in your optimizer, and then again you do this same year. But now the problem with this is you always have to be there to ensure that after the training, that's after the 10 epochs, you modify this manually. Now what if we're able to do this automatically? As usual, this is made possible by TensorFlow Callbacks. With this callback, that's the learning rate scheduler callback, we could define a function which takes in the number of epochs and then modifies the learning rate based on the current epoch, or based on a mixture of the current epoch and some predefined function. So as you could see here, we have the learning rate scheduler. It takes in a method schedule, and then we could specify the verbosity. Now this is an example of this scheduler method which has been defined here. What it do is, if the number of epochs is less than 10, then you're going to use this predefined learning rate. And then in the case where the number of epochs is greater than or equal 10, then we start to reduce this learning rate in an exponential manner. So there we go. Let's take this off. Now what we're saying here is we're modifying the learning rate such that after that we're having, before 10 epochs, we're having this fixed learning rate. That's it. And then after this we start to reduce this, so the learning rate starts dropping as we continue with the training. So now we don't really need to be monitoring the training manually, because this callback will automatically modify the learning rate for you. We could simply copy out this example which has been given to us right here, and then make use of it in our training process. So here we have to include this text and then our code. So here we paste out this scheduler. Let's delete this, and then for this one we have our learning rate scheduling callback. So learning rate scheduler, and then we do this import. So here again we just have learning rate scheduler. We run that and then get back to this position right here. Let's do this 1 2 3, so that's fine. So notice that here we have this ordered, so we have the callbacks, learning rate scheduler, and we have CSV logger, L is stopping, learning rate scheduler under the callbacks, so that's fine. let's get back to that, and then we are gonna define. So here we've had the learning rate scheduler, or this scheduler method, but we're yet to define our learning rate scheduler callback. So we have our let's say scheduler callback equals learning rate scheduler, and then it takes in this scheduler method right here. So that's fine. Notice how the scheduler method takes in the current epoch and the current epoch number and the learning rate. So here we have this given to us already, and so we'll modify this to take, say for example, 3. So after 3 epochs, we're going to modify the learning rate, and then we could print out the learning rate. So we could say, for example, the current learning, or actually what we could do is, let's take this off, let's not have that, let's specify the verbosity to be equal 1. So here we have the verbosity specified as 1, and then we'll take off this. So you could also check out the CSV logger, the logged CSV file. So you'll notice how throughout we've been logging these values, since we're just adding up or stacking up the values on the previous values we've had already. So for now, what we could do is take this off. Now let's take this off, all this, and then focus on just the scheduler. So we have scheduler callback, and that's fine. Let's ensure that the cells have been run already. So that should be okay. Now we're having this error, verbosity, unexpected keyword arguments. Let's get back to this here, and then we have always variables. So let's modify that as variables equal 1. We run that again. That should be fine. Now we could now get back to our training. So we're expecting that below 3 epochs, let's say equal 3 epochs, we have a given learning rate, and then above that we have a learning rate which decreases exponentially. So that's it. You see here that as the training process starts, we did not really need to print out any value, because when we set our variables to 1, it outputs this. So here we have learning rate scheduler setting the learning rate to 0.00999. That's practically 0.01, which is what we had given here in this learning rate. So it's practically this learning rate setting, and then as time goes on, it's going to decrease this value and then always output the current learning rate. So as we carry out this training process, recall that the aim of having to work with this kinds of learning rate schedulers is that we want to actually get the best of both worlds. So what we want is speed, because a very slow or a very small learning rate doesn't assure speed, and so we want speed, and then we also want stability when training. So because we want this tool, we are going to use modify our learning rates such that we always get this throughout our training process. And so that's why whenever we start on with training, we have high learning rates which could ensure speed, and then as soon as we've trained for a given period of time or for a given number of epochs, and that we're trying to approach this global minima right here, we now seek for stability by reducing the learning rate such that we don't get to this point and have to diverge. So if we want a more stable kind of training process, what we do is reduce this learning rate. After the training is complete, here's what we get. You could see that we have this learning rate which is now modified after a given number of epochs. So here you see how the learning rate starts decreasing as we go on with the training process. And so that's how we implement learning rate scheduling. But before moving on, let's check out this tutorial provided by the MXNet project developers, which talks of other different learning rate scheduling techniques. So here we have this learning rate scheduling with warm-up. Here's a slanted triangular, and as you could see, the learning rate actually falls between these two values here. So we have our learning rate between 1 and 2. So you could always define your max learning rate and then your mean learning rate. So you could always have this, and then with the warm-up, what we do is we are going to increase this learning rate linearly up to the max for a given number of epochs, and then once we attain this, once we get to this number of epochs, we now start decreasing this learning rate. So here the decrease is linear, so it's a linear function we're using, and then once it gets to the minimum learning rate, we just maintain that constant value right up to the end. So another learning rate scheduling technique we could use here is we have this linear increase, that's the warm up, and then we decrease this exponentially right up to this minimum value. Now this technique of warm up was developed in this paper by Priya Goyal et al, and they found that having a smooth linear warm up in the learning rate at the start of the training improved the stability of the optimizer and led to better solutions. Then from here we move on to the cosine aligning scheduling method, where there is this smooth decrease in the learning rate, which is kind of resembling the cosine function. Now this is what a cosine function actually looks like. So here we have this and that. So here is our cosine function, and then if you notice, you'll find that this portion actually looks similar to what we have here. And now after we get to a given number of epochs, we just maintain that. So we have defined the mean and then the max, and then once we get to the mean, we just maintain that mean throughout. Then we also have this stepwise decay scheduling. Let's take this off. Here you see how we start with a warm up. So this warm up is kind of like a method used very much in practice, and then from here we have this stepwise reductions. So we go in for this fixed learning rate. After a given number of epochs, we now drop the learning rate, and then we drop it, and so on and so forth. So here's our stepwise scheduling with warm up. Then from here we have this cool down, where we follow the stepwise method, and then after a given number of epochs, we now reduce the learning rate linearly, hence the term cool down. We also have this one cycle scheduling technique proposed by Leslie N. Smith and Nicolai Topin, and here's what it looks like. You see that we increase, that we have this warm up and then this linear decrease. Once we get to this initial position, we also have again this linear decrease with a different slope, with a smaller slope, and then once we get to this minimum or this final minimum, we now just maintain the learning rate. Now finally we have the cyclical scheduling methods, originally proposed by Leslie N. Smith. The idea of cyclical increasing or cyclically increasing and decreasing the learning rate has been shown to give faster convergence and more optimal solutions. So as you could see here, we are having the learning rate, which is going to be bouncing from the minimum to the maximum, as you could see here. So we have this linear increase to the max, and then linear drop, linear increase, linear drop, and so on and so forth. And then finally we have this cyclical cosine annealing scheduling right here. We see how we have the cosine annealing, and then we have this full cyclical process as we go from the highest to the lowest, and then this next cycle from the meet between the mean and the max, that's this, right to the mean learning rate, and then we take up this final cycle from this quarter of the total. So we had 0.5, which is a quarter of 2. So we start from this and then right to the mean. Now notice also that as we go into the cycle lengths keep increasing. So we move from this to this length and finally this length. Based on the scheduler you want to implement, all you need to do is to modify this scheduler method right here. The next callback we'll be looking at is that of model checkpointing. In this model checkpoint callback, we are able to save the model's weights at some frequency. So unlike previously where after training, like with this, after training our model, we get to load, or rather we get to save the model like here. So here we saved our model, or we save our weights. After we're done with the training, here we could be doing this weight saving during the training process, and thanks to this model checkpoint callback. Now as usual, we just copy this, and then we could check out on this documentation for the significance of each and every one of these arguments. Here we have the file path. So this is the file where we are gonna be saving our model. So here we have our checkpoint callback, and that's it. We have model checkpoint here. We're gonna define this file path, and then what are we gonna be monitoring? We're gonna be monitoring the validation loss, which is what's given to us by default. Just like with the early stopping, where we had this monitor right here, we are gonna look at our validation loss. And supposing we have this validation loss and then our training loss, so we're gonna look at our validation loss, which is this, and then save the model weights when we have this minimal or the smallest validation loss right here. And then if you set the save best only to true, then we'll save only this weights, whereas when it's false, we'll save this and also save the latest weights. And then for this argument save weights only, if it's set to true, then we're gonna save only the weights, whereas if it's set to false, then we're gonna be saving a model. That's a full model with its parameters. Then we'll have the mode, which is automatic. Like since it's validation loss, since it's a loss, automatically this will be a mean. Whereas if this is an accuracy or precision, we're gonna have a max right here. So let's take this back to auto, and then we have validation loss. Now the save frequency when set to epoch simply means we're gonna do the saving after each and every epoch, but we could modify this to say 3. So after 3 epochs, we're gonna verify if our current model is the best of all the previous models. That's if we've set this to true. So if we've set this to true, we're gonna verify if this model, the current model, is the best. If it's the best, then we overwrite this file path. That's overwrite the file, the weight file we've saved. And if it's not the best, we continue training. So that said, let's modify our file path, and then let's call this checkpoints. That's it. So we have this checkpoints, and then we run this cell, we have that, and then we add this callback right here. So we have the checkpoint callback. That's fine. We run the training now and see what we get. After training for over 10 epochs, we have this 2 logs, which you could notice here. This one where we've been told assets written to checkpoints assets. So you could open up this checkpoints here, and then you see that we actually saving this model. And then we also have this logged here, that's after the seed epoch. Now let's understand why this logging is done after the first and also after the seed epoch. Just when training starts, we have a validation loss of 0.47, and so we're supposing that since this is the first, then the model is at its best state. Then it moves to 1, which is greater than this. So the model state, or the best state, is this one after the first epoch. The model, the first epoch, or the model state of the first epoch is to the best. This doesn't beat the record. This doesn't. And then you'd see that here we have this validation loss of 0.24. That is why the model is now saved. From this model checkpointing section, we'll look at the reduced learning rate on plateau. And then later on, we'll have a dedicated section for TensorBoard. the way this learning rate, or rather reduced learning rate on plateau works, is that if you start training with a fixed learning rate, and then say you've trained for over 100 epochs, and that the model performance after 110 epochs, so let's say we have 110 right here. So after this 110 epochs, our model performance doesn't improve, so we still fix our learning rate. But since for the past 10 epochs we haven't had an improvement in the model's performance, what we'll do is we'll reduce the model's learning rate by a given factor. So here is the factor. The patience, our patience here is 10, meaning that we're going to wait for 10 epochs before deciding whether we're going to reduce the learning rate or not. The verbosity, as usual. The quantity to be monitored, in this case the default is the validation loss. The mode, automatic. So if you want it to be mean, you could specify mean or max, but setting it to automatic allows TensorFlow to automatically decide whether it's a mean or max. In the case of validation loss, obviously it's going to be a mean, since our aim is to reduce the validation loss as much as we can. Then we have the mean delta, which takes in a default value of 0.0001, and this means that if after say 10 epochs we have a change in the validation loss, but this change is less than this mean delta, then we'll consider that that isn't a change, and hence we are going to still reduce the learning rate by this factor right here. We also have the cooldown, and then the minimum learning rate, below which we wouldn't want to drop our learning rate. As described here, this cooldown is the number of epochs to wait before resuming normal operation after the learning rate has been reduced. We are going to create this callback very easily, and this time around we're going to monitor the validation accuracy. So if the validation accuracy doesn't increase after 2 epochs, we are going to reduce the learning rate by a factor of 0.1. Meaning that if we had a learning rate of say 0.01, and that this validation accuracy hasn't increased after the 2 epochs, we are going to reduce this such that this becomes 0.01 times 0.1, which is this factor right here. Just as before, we are going to add this plateau callback and then train our model. After training for 5 epochs, we can observe that we have this learning rate which has been reduced after the 3rd epoch, and this is because after this 2 epochs there is no improvement in this initial validation accuracy, and so that's why the accuracy is going to drop from 0.01 to 0.001. Now that's it for this section. Thank you for getting up to this point, and see you next time.
Hello everyone, and welcome to this new section in which we're going to look at different strategies of combating overfitting and underfitting. These strategies will include data augmentation, as you could see here, dropout, regularization, early stopping, smaller network usage, hyperparameter tuning, and normalization. So far in this course, we've mentioned the terms overfitting and underfitting without really getting in depth to what these two actually mean. Now, for overfitting, we'll consider this plot of the loss versus the number of epochs, and then precision versus number of epochs. With a loss versus number of epochs, what we'll generally have when a model overfits is something like this. So here we have the validation loss, and that here we have the training loss. So this is just like a general way of looking at this, though this may take different forms. Now that said, as we could see, we have this 2 sets and their loss versus number of epochs plots. Clearly we could see that the validation and the training set initially start up with a similar pattern. Sometimes you may even have the validation which comes up like this. So you can even have a situation like this where the validation performs even better than the training set initially. But generally, when a model overfits, what we'll have will be this kind of model where at some point the model keeps doing well at the level of the training and starts doing very poorly in the validation set. We could replicate this with a precision epoch. This could be precision, accuracy, recall, or some other metric which we've chosen. And what we could have will be something like this. Obviously, you saw in the practice it isn't always like this, but something in this sense. So you would have this here. You see, you have the training, and then you have the validation right here. So what goes on is your model keeps on doing very well for the training, and then with the validation, at some point it starts doing even very, very poorly. And so the danger with this is if you're considering working only with a training set, you may feel like you more epochs or training over more epochs is a good idea because you keep having this great results. Like supposing we have fixed this here and that your training is like say 99%, so you have 99% precision score for on your training data, and you're like, wow, this model will do very well in the real world. But this isn't generally the case because this model actually has been overfitted on your training data. Your model has learned instead to modify its weights based on the training data instead of being able to extract useful information or some intelligence from the data which has been used in training this model. The main cause of overfitting is having a small data set and a large and complex model which contains so many parameters. Now, if a model like say a deep neural network has many parameters and you're giving it a small data set, then obviously it's going to adjust its parameters such that on this small data set it performs exceptionally well. So you may come across a model which has say 99.9% precision or accuracy just because the data you've used to train the model has or was very small. Now in another case, you may have say a moderate sized data set and then not just this kind of model but a very large model. So at the end of the day, we notice that there has to always be a balance between this data set and the model size. So this means that even if you increase the data size and then you also increase the model size, your model may still risk overfitting. To better understand this concept of overfitting, let's take this simple example. Supposing that you have 3 subjects to master at school, let's say math, English, and sports. But when kids get to school, they are only taught mathematics, or they only taught English, or only taught sports. Let's choose, for example, mathematics. So these kids get to school, and from the first year to the last year, they taught only mathematics. It's clear that when you evaluate this kid, or when you pick a kid at random and evaluate that kid in mathematics, the kid will tend to have a better or an above average result in mathematics compared to kids from other schools. But when tested on subjects like English and sports, that may not be the case. And this is because the English and sports weren't taught at school. And so if you are evaluated on only what you were taught, you would tend to have very high scores like this. And then what if we start to evaluate on stuff the kids were not taught? You'll notice that those kids will then start having poorer results because those kids haven't taken out some time to master English and sports. And so you may end up with a kid who is able to show, for example, that sine square x
plus cos square x equal 1, but can't tell you the past tense of it. Now it's clear that to readjust this situation, the kids have to be taught all the subjects such that there is the balance that these kids need. And obviously this balance will come in a way that the kids now perform better in these two subjects, and because they have had part of the time they used to study maths allocated for English and sports, they may perform slightly less than before in maths, but at least what's important to notice this time around, they can now express themselves better in English or practice some sports. Let's now take this other example. Supposing we're training a model which predicts the presence of a car in an image, and then you feed your model with this kind of data. Then after training your model, where you get to test that model is on this kind of real world data. It's clear that even if you had very great results with the previous data, in this working with this or testing on this new data set right here, you wouldn't have those amazing results you had previously. And so it's important that not only should your data be large enough or gather as much useful data as you can, but ensure that your training data represents or looks like your test data or looks like what you're gonna be having in production, as that's really what matters. What matters is the fact that you have a model in production which works well or which has high accuracy, and not a model in your notebook which has, say, 100% accuracy on your trained data, whereas on production it doesn't perform very well. Now moving on to underfitting, it turns out that here our model becomes way too simple for it to even be able to extract information from our data. So we may have our validation data and then our training data like this, and then there is this huge gap between our current loss and the minimum possible loss. We could also have this at the level of let's say accuracy. So here we could have accuracy, and then we have our validation and then training, and we have, say, accuracy 100%. Let's say we have one right here, and then our model is still too simple that we just end up, say, at 0.6 or 60% accuracy. In this kind of situation, our data or the relative size of our data as compared to the model may be too large. So you could even have a situation where this data is smaller than what we had here. So your data could be small like this, but if your model is way too simple, say we have just this very small model, then you may face this problem of underfitting. It also turns out that sometimes you may have a situation where you have even a very complex model, but that model still underfits, and that's because that model hasn't been built in a way that it could extract useful information from this data. Now, if you could recall in the section where we're predicting the car price, we had a situation where a model, we use a simple dense layer. We use a simple single dense layer with just two parameters, and we had this fixed data set. But once we increased or stacked up more dense layers, we found out that we're able to get better training and validation mean average error values. There are several ways in which we could mitigate this problem of overfitting. The very first one we'll look at is that of collecting more data. So it's important to lay hands on as much data as you can. This data has to be representative of what the model would see in real life, and this data should be as diverse as possible. Even after collecting more data, to solve this problem of overfitting, we could use data augmentation. Now, what is data augmentation all about? Supposing we have this image cell right here, the cell image we have here, which happens to be parasitized. Now, instead of having just this in our data set, we could have this image right here modified such that we now have more data to train on. So this means that in the case where initially we had, say, 20,000 images, so we have 20,000 images. Now, after doing data augmentation, after modifying each and every image, we now have a data set of 80,000. Now we're considering 80,000 because we're supposing that each image is going to be flipped as we've just done right here. So we take this image, we rotate it, we have this other image, the same level, obviously still parasitized, and then we flip again and get this image. We flip, get this image, flip, get this image. We see that we now have, instead of just this one, we have 4 others. This actually means, oh, we're multiplying this by 5, so this is 100,000, since we have it now 1, 2, 3, 4, 5 examples for this single example we had initially. It should also be noted that there are many other data augmentation strategies for this kind of image data. So apart from flipping as we've just done, we could crop just a portion, we could add some noise to this data, we could modify the contrast, we could modify the brightness, and carry out so many other operations. And there is no particular data augmentation strategy which works for all problems. This means that when you have a particular problem, you will have to try different augmentation strategies and then be able to select the one which works for your data. Now, that said, we have dropout. To better understand this notion of dropout, we'll consider this simple neural network right here. Now, if you could recall, the reason why we have models which overfit is because we are working with very complex models with many parameters. Now, in order to reduce the complexity of this neural network, what we could do is take off, for example, this interaction between this neuron and all these previous neurons right here. So this means that when training our model, we are only going to consider that we have in this hidden layer just these 2 neurons right here. So all those connections here become useless. Now, this has the effect of simplifying our network, as what we have as output now, that's after carrying out the dropout operation, looks like this. So we have now a connection which look like this. Now, this particular case is an example of a dropout with dropout ratio equal 0.3, or let's say 0.333, as we're dropping out exactly 1/3 of all the connections, or rather 1/3 of all our neurons right here. And if r equal 2/3, what we'll be left with will be this. So we'll take this off and we'll be left just with this neural network to train right here. We see that we could leave from this very complex model to a simplified model via this dropout operation, and this has that overall effect of mitigating overfitting. The next step we could take is that of regularization. To better understand regularization, suppose we have this model with weights wj. So we have say n weights, and these weights are free to take up any value. As we've seen previously, the fact that these weights can take up just any value may lead to overfitting, as now these weights can be adjusted to fit on the training data in a very perfect manner. So this means that we could have a model which picks out each and every point like this. So we have this kind of model, and we have this. So we have this model which picks up every point like that. Whereas if we restrain these weights to stay in a given range, then we may end up with something like this. So we may end up with a model which looks simplified like this, because it doesn't have as much freedom as this other model. Now the problem with this model is, if now you put in this new data, you find that this one will try to pull out like this, and then your prediction will be somewhere around here. And so if, for example, we're having horsepower on the x-axis, and then here we want to predict the price of a car, let's do same here. We have the price and then the horsepower. Then it happens that we have this car with this very high horsepower. This model, because it is overfitted on this training data, will predict this very low price, whereas this model, which is generalized on this training data, will tend to predict a more reasonable price. Now it should be noted here that because this model was able to go through each and every point, we would have a training loss of almost 0, whereas now when we give it this new data, it doesn't perform well. Whereas with this, we wouldn't have a training loss of 0, but when given new data, at least we're gonna have reasonable predictions. So coming back to regularization, our aim is to ensure that this weights, because this model can be represented as this function, and this function is made of this weights. And so since when we're doing training, our aim is to ensure that we minimize the loss, then we could include this weight in the computation of the loss. This means that we have our loss, which is now equal the loss we would have normally, plus this regularization constant times the sum of this weights of each and every weight square. Now this is known as L2 regularization, whereas here we have L1 regularization, where we're summing up the absolute value of each and every weight. For now, we're just gonna explain how regularization helps in mitigating that problem of overfitting by restraining those weights in a given range. So let's have here loss equal L, that's initial loss, plus let's call this R. Now if our aim is to minimize this loss, then obviously this L will be minimized and the R will be minimized. And so if we're trying to minimize this here, or this sum in general, then it would have that overall effect of restraining these weights in a given range. Especially as we know that when we square very large values, these values become even larger. And so to avoid this, our weights will tend to take up smaller values which fall under a smaller range. This L2 regularization is also known as weight decay. It should be noted that the main difference between this L2 regularization and the L1 regularization is that in trying to restrain the range of values which these weights can take up, the L1 regularization has that negative effect of making many of those weights to take up values around 0. That's values very, very small, or take up many 0 values. So this will lead to sparse models as compared to the L2 regularization. And that's why in practice we generally use the L2 regularization. That said, we move on to L stopping, which we've seen already. In L stopping, as we have seen, if we have our model, let's say we have precision, validation precision, and then the training precision, which keeps on increasing, and then we have this limit here of 1 or 100%. So we have the precision and we have our epochs, and then after a while this starts dropping, and this starts dropping simply because our model is now trying to overfit on this data it's been trained on. And so we have to stop training once we notice that the validation performance isn't improving any longer. So this means that after a certain number of epochs, we are going to stop the training. And we've seen this already in the previous section. We've seen it both theoretically like this, and then we had seen it practically. Then another thing to do is to reduce the size of the network, or use a less complex network. Our next step will be to properly tune our hyperparameters. Hyperparameters like batch size, dropout rate, regularization rate, and the learning rate can affect our model and dictate whether this model will overfit or not. Now, if we look at the batch size, training with a larger batch size may speed up our training process, but working with smaller batch sizes have a regularization effect which help reduce overfitting. And so, according to Yann LeCun, friends don't let friends use mini batches larger than 32. For the dropout rate, we've seen this already. Increasing the dropout rate means we are making the model simpler, and the regularization rate, increasing the regularization rate means we're reducing the effect of overfitting. And then finally, picking too small of a learning rate may lead to overfitting. So in general, we have some hyperparameters to tune, and they are not only limited to this, as you may have many other hyperparameters depending on your problem. Now, the fact that normalization introduces extra parameters mu sigma, which bring in some noise in the model, has that regularization effect which help reduce overfitting. So if you're including batch norm in your model, then you could feel free to reduce the dropout rate, since this normalization layer already brings in that regularization effect. From here, we look at ways of mitigating the problem of underfitting. So with underfitting, we could use more complex models. We could also collect more data. We see that this solution falls in the two, that's both overfitting and underfitting. Here is always a good thing to collect more data, or more clean and representative data. So from here we have, you could also improve the training time. Now note that you could have this model, like let's take this, and then we have here you've trained, and then you have the validation. So here you have the val, and then you have the train, and then you've been training for over say 1,000 epochs, and then you feel like the model may not perform any better. Now, several scientists have reported that many times they've given up on a model and then come back later after forgetting to stop the training process and notice that this model kept on performing much better. So sometimes you don't have to give up on your model, so you could train, or you could increase this training time. Then again, we have hyperparameter tuning, which could help in making your model more performant. And we have normalization, which stabilizes the training process and leads to better performance in the model. We now see practically how the dropout could be implemented with TensorFlow. So here we have this dropout layer, which takes as argument the rate, the dropout rate, noise shape, and the seeding. To better understand how and why we need to use seeding is simply in the case where we want a reproducible experiment. So if we want to apply dropout in this layer with a dropout rate of 0.2, then we'll be taking off 1 neuron out of this 5 neurons to make our model simpler and avoid overfitting. Now in doing so, we may take this one, or this, or this one, or this, or this other one. So it's a random choice. Now if we want to fix this choice so that this experiment can be reproducible, then we can set this seed so that each time we run that experiment, it's going to be exactly the same neuron which is going to be taken off. Getting back to the code, the way we could use this is by importing the dropout layer. So here we just have this dropout, we run that and it's fine. And then we could include this dropout right here. So we could have here dropout, let's say dropout rate equal 0.2. Now you could always increase this rate. So let's have that, and then we have the dropout, and then dropout, or rather rate equal dropout rate. That's fine. We could paste this out here, but wouldn't want to add dropout here. Anyway, you could always include the dropout at this level depending on how the model responds to this dropout which has been added here. So let's add this dropout and then add the dropout right here, bearing in mind that we could always add more dropout layers and increase the dropout rate or even reduce this rate. So that's fine. We run our model, and as you could see right here, this dropout has no parameters. From this, we look at regularizers. We'll see how to implement the L2 regularizer and the L1 regularizer. So here we have TF keras, and then we have this regularizers right here. So if you select L2, you should fall on this page. Now, once you get this, you see you have this TF.keras, the regularizers, L2, and then you specify the regularization rate. So let's copy this out and then get back to our model. At the level of our model, let's come back to the definition of the conv2d. So here we had this kernel regularizer, and this kernel regularizer that we use in carrying out regularization. So here we have this conv2d, and then we simply specify the kernel regularizer. We have kernel regularizer, which is equal this regularizer right here. Now let's take this off, and there we go. We have this kernel regularizer, which is now our L2 regularizer. You could always take this off, and then from here, and you have from TensorFlow.keras.regularizers import L2. So that's it. You could also import L1. So run that. Let's correct that. That's regularizer. Okay, so that's fine. We get back to our model right here, and then we have just L2. Now you could have this taken off from here, and then you add it out here. So pattern valid, activation relu, and that. Okay, so we have this, and then we add our regularizer, and that's fine. Now you could also do this for the dense layers. So just right here, you could have kernel regularizer, and that should be fine. So this is how we implement the weight decay with TensorFlow. Now you could always modify these parameters. So let's have decay or regularization rate 0.01. So that's it. And then we will run our model. That should be fine, and we could go ahead and retrain this model.
That's it for this section. Thank you for getting up to this point, and see you next.